geteld?
Ja.
Ja? Hey, ja, ja, ja. Hey, ja? Hey. Ja. Peter?
Wat vind je ervan? Zeg eens wat?
Ja, daar ben ik. Hey, goedemorgen. Check.
actie. Dat is best donker, Stevie. Heb je niet een beetje meer dan dit? Oké. Ja, voor de spreker is het goed hoor. Is goed. Ja. Ik voel hem.
Slide deck that you cycle through between sessions?
Yeah, it's running at the moment.
Okay, I need to add this slide to it. How should I do that? No, I do have Wi-Fi now, so I could email it to someone. Who is it?
Oh, there he is. There he is. We need him.
Yeah, I'm fine. Okay, not sit on it. I get it. Or, I mean, we can also put it in the front. I don't know. Yeah, I think front is better. Test it, like, or already? I'm number one. Test. Hello. How is this? Was it like? Okay.
do anything? Do I have to do anything?
Dezelfde laptop tegen.
Yeah. It's good? Cool. Thank you. Yes. No, I won't. So I can plug the laptop? Yeah?
Are you still with that?
Yes.
When you're done, I want to.
Cool. Sure. Yeah, okay.
Great so far.
If I have any problem, I'll...
Batteries.
Yeah. Thank you. Funny look sometimes. Yeah. How do I take this? Oh, okay. No need that. Yeah. Me. Good.
So, how shall I introduce you?
Caio?
Many names.
Yes, that's the first one.
Yes. Good. And your last name is Brito.
Yes.
Kyle Brito. And you're working with Pierre?
Yeah. Yes.
You know, right before I just changed jobs, last year,
Okay. Cool. Cool.
I think you're coming back.
I will join you if this is fine. Is it fine that if I join you? I think this way it's better. Yeah, that's the idea.
Cool. Hope you enjoy.
See you soon.
Yes, thank you.
Now it is. Na du? Ja.
Das ist ganz toll. Das wird ganz viele Leute kennenzulernen. Richtig schön. Ganz schön. Ganz schön.
Ja, nervt ein bisschen, aber so ist halt eben. Ich hoffe, meine Haare streicheln dann nicht das Mikrofon und dann ist die ganze Zeit aber ist halt. Bin mir bei Matthäus immer nicht sicher, wann er einen Witz macht und wann er es ernst meint. Ich krieg das nicht raus. Macht mich ein bisschen fertig oft. Ich habe unser Paper noch nicht hier gesehen. Ist entweder sehr schlecht oder sehr gut. Vor allem das ist das gleiche Grün wie Nvidia, ne? Facebook. AMD ist übrigens
Okay, can you switch to my slide? Okay, welcome. We survived the first hour and a half. This is always a drama for the HPG committee, getting to the first moment. Plenty of drama today. I'll spare you most of it. I'll come back to Wi-Fi in a minute. That's probably the part of the drama that will be most relevant to all of you. Let's see. But we're happy to be here. We're happy to be back in person, and it's great to see all your smiling faces. Okay, so let's talk about Wi-Fi really quick. How many of you are on Wi-Fi at this point? Okay, 17. That's not too bad. Let's see. If you are an academic, you can use EduRoam and log right in, no problem. If you have a Dutch phone number, then you should be able to text a certain code and get back an EduRoam login and password for the day. If you do not have a Dutch phone number, then texting that will give you a fail message. It'll say, sorry, access is not allowed or something like that. So the solution to that is go down 2 flights of stairs to where you first came in the door. There's the coffee shop on this side, and there's like a rack of balls for rent or something like that on the other side. You go to that The papers were great, the talks were great. But we're back in person, and this is the largest in-person HPG ever in Europe. By quite a bit, I think. In the past, it's ranged from about, the lowest number I can recall is 43, and it seems like the high was somewhere in the 120s. So 151 of us is pretty good news in my opinion. So welcome all of you. To my mind, the best thing that came out of COVID for HPG is that we got YouTube working. So we're live streaming our talks. Francois is our online chair. So thanks to Francois and our AV crew from the university right here, who are live streaming this session and all HPG content as was done during COVID. And also, since 2020, all of the live streamed content is also available permanently on YouTube. And Francois has broken that up into individual talk videos. Before that, it was a video per session. So now if you want an individual talk, it's easier to find it, or if you want to find all the videos by Karsten Benteen. His talks will now come up individually. So thanks for that slicing and dicing, Francois. There's been a lot of views on YouTube. Francois, you've probably seen YouTube more recently. Is this number okay? Okay, so this is pretty awesome. 100,000 views of the HPG YouTube videos over the years, and I want to thank especially Jem Yüksel, who has put a lot of effort into the YouTube platform over the last couple of years. Also, about half of these views are Brian Karas's talk at HPG last year on the evolution of nanite, or the formation of nanite. That was a great talk. It had 46,000 views last time I checked. Okay, so where did HPG come from? Our roots started in the Graphics Hardware Conference from clear back in 1986. And then SIGGRAPH became a sponsor of that as well, starting in 1997, and it started, and then the IRT conference in 2006, 7, and 8, that was started by guys from Saarbrücken and guys from Utah, and a lot of you joined in and made those three into great conferences. And then those two merged for HPG 2009 in New Orleans. And it's been going every year since then. The three differently colored dots there were our online years, and here we are in 2023. We alternate every year between the United States and Europe. Okay, and this conference, at a technical level, it's all about performance-oriented graphics, and performance matters in mobile devices. It matters all the way up to top 500 supercomputers. So all of that is very relevant to HPG. We care about algorithms, we care about hardware architectures, we care about implementations of those two, and then we care about applications sitting on top of those. You'll find all of those things each year at HPG. We also try to strike a balance between industry and academia, between North America, Europe, and the rest of the world. So we have, especially in this attempt to strike a balance does not appear in the paper reviews, but it appears in how we form the committee. If we have two papers chairs, we try to choose one from academia, one from industry, one from NVIDIA, one from AMD, right? One from Europe, one from North America, et cetera. So we try to keep a good balance there. And we have the papers program, and then the program chairs drive panels, keynotes, and the Hot 3D session. Our Hot 3D chair this year, Aaron Knoll, unfortunately couldn't attend in person. Okay, and then our philosophy in how to get at those technical goals is to connect I see HPG as all about connecting, first and foremost about connecting us with new ideas. And we also use HPG to connect with potential and current collaborators and past collaborators, right? A lot of us who've been here before look forward to seeing the people we've worked with before. Also, HPG has been invaluable at finding new jobs. I found a job, at least one job. Yeah, I found one job through going to HPG and talking to someone and ended up getting a great job. Also, we as employers come here looking for great people to hire, and I have hired probably 4 people who I know from HPG. So HPG really plays a role there. And so how do we use HPG to meet those goals? We have long breaks so that we can talk to each other. We have long lunches. And so I've met people in line at lunch who I've since invited to be on the HPG committee and who I've talked to about working for me. So these techniques really do work at connecting us and furthering our employers' goals and our personal academic goals. And the banquets, we have dinners every night. This is up from, in the past we had one exceptional banquet. Now it's that plus, maybe you would call them social networking dinners, whatever. Okay. And then, okay, yeah, the last way in which we meet our goal of connecting is the YouTube. Making the videos available online is a great recent contribution. Okay, now I'll turn the time over to Jaco Bicker, our co-papers chair, to tell us about the papers session.
Yeah, so it's very good to see you, everyone here. We've been working with many of you over the past months, and finally seeing everything come together is quite amazing. I mean, we have a large number of attendees today and the coming days, but it should not really be a surprise when you look at these numbers. I mean, we got 28 papers that were submitted for this conference, and then we got a massive amount of reviewers for that. Almost everyone that we approached for this was available to actually review a paper, which meant that we were able to have no less than 4 reviewers per paper, which also guarantees the quality, I believe. By the way, I'm standing here also on behalf of Christian Gribbel, but he's delayed in transit, so he should be around later today. So of those 28 papers, we got 17 that were accepted, often after some changes, and we are very grateful for all the hard work that went into that and the rechecks that were done. And we are aware that this was a somewhat painful process sometimes, because it was short, and in some cases we asked you to respond extremely quickly to requests. So we are sorry for that, and we are going to try to learn from that for upcoming years. But it did result in a rather interesting program that you can now find on the conference website. So it boiled down to something very concrete, and of course we are very much looking forward to all the presentations. So 7 papers got submitted to CGF, and more details on that will follow later, because that was a complex process, and we are still handling the details of that. Right, so we will have 5 sessions, and we have very interesting chairs ranging from extremely experienced to pretty new, so that should be a great way to get introduced to this kind of setting, and I definitely look forward to that as well. So finally, to put some things straight, there is indeed, I mean, this is about disappointment and misconceptions and so on. There is indeed a coffee shop downstairs, but it is not a coffee shop, all right? So you can just get coffee there. Sorry about that. I think, yeah, so finally a big thank you for all the reviewers and all the authors, and we look forward to the fruits of your work today. And with that, I would like to give the floor to Alex.
Thanks, Jaco. I'm going to go really quickly because I think we're running a bit behind. I just want to say thank you to our nurture level sponsors. You'll see there's a 5-minute sponsor session each day. There's a chance for each of these companies to say something to this audience, because I think it's really crucial there's a connection between the HPG audience and industry as well as academic research. And the program has been organized mostly by Christoph Peters. I'm basically just the hype man. And because I don't have long, I'm just going to say, like, I'm really looking forward to the keynotes. What I like about it is that you have someone from games with an art background. You also have academia, and then you have, industry, academia, crossover with Tammy. All of them are, I think, the thing to take away for me is that HPG isn't one set of requirements or one set of goals. Different people have different uses for high-performance graphics, and I think that comes across in our keynotes. Also, each day we have special sessions. So, for example, Zerrin, Shaba, and Zerrin are doing a Women in Graphics panel, which I think is fantastic, and that's happening today. The poster session tomorrow, I'm looking forward to hearing the theories that you will have. And Simon will be talking about ray tracing stuff in Hot 3D, which is going to be amazing. So please, bring all your attention to those amazing sessions. And finally, today I just wanted to highlight that the Vulkan course, which I'm looking forward to attending because I'm a Vulkan noob, is a great way to kind of get up to speed with Vulkan. And if you're a greybeard and know your Vulkan forwards and backwards, then you can kind of branch off and go and hang out in the Royal Delft Museum. So there's a sort of fork in the road there that you can take your pick. And with that, I think it's Ricardo's up next. So thank you very much.
Thank you. Dave, so should I switch? Where's Dave?
Yeah,
All right. I did switch here, but not there. I think I have to put this one down, maybe. The slideshow.
What's that?
Maybe.
Okay, so we can kill that.
Yeah, exactly. Then.
Okay.
Just Windows.
Okay.
Okay, no slideshow. It should work, right?
Yeah. Okay.
Yeah, yeah, you can just click here. Okay. Well, thank you, Dave. In the name of the local organization, Elmer Eisman, who's sitting over there, and myself, Ricardo Marroquin, welcome to Delft and to the TU Delft. I will quickly go over the logistics for these 3 days, so hopefully no one will get lost. First thing, we're here today and tomorrow. On Wednesday, we are receiving also EGSR, so you see that we will not fit here, so we're going to the Ivy Tower, very easy to see, the tallest building probably in Delft. So just look up, and there we have a larger auditorium. So for today and tomorrow we're here, coffee breaks and lunch downstairs. On Wednesday we go to Ivy, the Ivy building. So let's quickly go over the program. So this is for today. As Alex already mentioned, during lunch we'll branch off. So if you know everything about Vulkan, you can go, for example, to the museum. And it's really close by, 15 minutes walk. We have here on the map, you just exit the left and right. And there will be someone also leading the way so you don't get lost. And then it's not a very large museum, so you have enough time to visit and come back for the coffee break. It costs 15 euros, and that's not included in your registration. It's also optional. You can just hang around the campus if you like. And then we come back here for coffee break, the keynote, and we take off to downtown or the city center for the reception. That will be in the Stadthaus, that is the town hall of Delft. Don't mix with the town hall meeting, that is tomorrow, Wednesday. This is actually the municipality of Delft. It's in the very large square. It's called Market. You'll see also the big church, and then you can just follow from there. You can walk from here 30 minutes or get a bus to the station in 10 minutes from there. Very easy to find also. That will be at 6:30. Now, tomorrow, we also have a branch. So after all the program and the keynote speaker, some of you have bought tickets to the boat tour, and that will happen at just before 6. If not, I'll give you some tips in a while. So the boat tour, if you're taking it, it will be very close to where the museum is. There's a bridge there, so you just go all the way to the end of the campus. When you hit a traffic light, turn to your left, just go straight, straight, straight. You get to the river. On the other side of the bridge, the boat will be waiting there. Okay? So it will start around 10 to 6, more or less. Takes 1 hour. And then the boat will leave you next to the station. We don't have the precise location because he needs to see where there's a parking space. And the reason is that from the station, you can go to the social event. So the social event will be on the beach. We still have good weather tomorrow, so that's in Scheveningen. If you cannot pronounce it, it's just the beach at The Hague. So at the end of the Hague. It starts at 7:30, so for the people that are not going on the boat, you have some welcome drinks, but the real event will start at 8 until 11. And if you get there early, you can also just walk around the beach side. It's very nice. There's also a museum, but we'll find it closed by the time you get there, but there's some things outside that you can visit. So how to get there? Now, the easiest way and the most indicated way is you get this tram that is called number 1, direction Scheveningen. And it will take you directly to the event, well, almost there. You can get it just by the train station, so it's indicated here in orange, and that's more or less, I hope, where the boat will leave you, or in some canal very near to it. And you just take this tram, and you get off at this stop here. I'll give you the slide so you don't have to memorize it. Scheveningen is klaar. I'll get some Dutch people to pronounce it. Beelden and Zees, the museum. So you just get off there, and then 3 minutes you're at the event. You will get one of this. They will be downstairs now. You can get it with the program that is also being brought now. Don't use it today. This is a one-day pass. So you can use it tomorrow. You can also use it to come here, to go downtown, but it's only valid until midnight the day you first use it. And with this, you can get in the tram. The event's finished at 11, so you still have 1 hour to get back on the tram and back. It leaves every 15 minutes. With this, we get to the last day. So the last day is, as I said, in the Ivy Tower. So that's the big tower with the TU Delft logo. On the other side, there's a big clock. So after the keynote here, we have the coffee breaks, and those will be outside. Just to the, if you look into the tower, just to the right, we'll see some white tents there. So that's your place to go for coffee and lunch. And then when EGSR starts, don't run away. You're mostly invited to follow the sessions from EGSR on Wednesday. That will be on ray tracing and neural rendering. And you can just stay with us there. And then we have drinks, everyone together, HPG and EGSR. And we are then expecting a very large crowd. And where do we have drinks? Well, we made it very close so no one gets lost on the way. You just cross the street. It's 3 minutes from the event. We'll also lead you there. So this is the reception. So people that are coming for EGSR. Intermission for those that are here and stay for EGSR. And farewell for those that are only for HPG. And with that, I think I cover everything. If you have questions, just ask one of us around, and we'll lead you the way. Don't forget to pick up your tickets, and thank you. I guess I will give it back to Dave.
Thanks, Ricardo and Elmar, for all your work over the last half year or more to prepare to host this event and EGSR. It's greatly appreciated. And we're in a beautiful place. Okay, if there's an empty chair next to you, can you please raise your hand? We've got people in need. Okay, so all of you on the sides who are looking for a chair, look for the raised hands, and if you'd like to take a seat, feel free. On the front row, this second chair is available. Just kick that backpack out of the way. I don't know whose it is. Let's see. Just kidding, it's mine. Okay, goodness. Okay, we're attempting to transition into the sponsored session. All right. Okay, as Alex explained, our three top-tier sponsors, one of the benefits that they get for donating $8,000 to the conference is that they get 5 minutes to talk about their company. So this is my company, and I joined AMD just over a year ago. It's the 6th graphics hardware company that I've been at, and I love it. It's a great company. The first thing I'll say about AMD is that the culture is distinct, and I noticed that from the interview process, and fortunately what I observed proved true once I joined, and it stayed true for well over a year now. It's a mature culture. The people have high emotional intelligence. They're good people, good to work with. They're expert in their field, but management is mature. They know what they're doing. The company's going in a good direction. There are way fewer jerks at AMD than at prior companies that I've been at. It's hard to hire for that, but AMD has attempted to hire for that. And it makes a difference to your stress level. Even when you have a big deadline going on like my team does right now, it helps to know that management's got your back, that your coworkers are expert, and that you have the same values as your coworkers. And among top tech companies, AMD scores like 5 percentage points higher than the average on I can't remember the exact term, but something about the culture of the company, the attempts to measure culture, and I can attest to that. AMD is a great place to do machine learning. It's a great place to do ray tracing. We're not the leader in either of those things, which is the thing that makes it a great place to do it. It means that when you come, you will make a difference. When I came, I was able to make a difference. When each of my team members came, they have been able to make a difference. And the same will be true if you join us. We've architected a great GPU ray tracing architecture. I'm excited about it. There's a long latency before products hit the market. So as you see AMD products hit the market in the coming months and years, just ask me if that's the one that my team designed. And I'll say no for the first few, and then I'll say yes. We're excited about what we've architected there. Come and join us. We're hiring in ray tracing and in machine learning. In ray tracing hardware architecture, we've already met our hiring plan, but in drivers and compilers, there's constant need, and those are very much HPG related disciplines. So I'm hoping some of you are compiler and driver guys that I can work with in the future. Okay, that's it for AMD. Now we're going to jump straight into our first paper session, and the venerable Peter Shirley will be the session chair, and he'll take it from here. What's that?
Hold the mic here. Hey, do you hear me? I don't know if I have this mic in the correct spot. Do you hear me? It's my pleasure to introduce the first session to HPG, back in person. This is my favorite graphics conference. Don't tell EGSR. And I'm delighted that we're in such a fine venue, and good job to the organizers on getting us together. Our first speaker is Bastian Kuth, who is talking on Catmull-Clark surfaces, one of the most staying power structures in our field. It actually was disliked by both the committee and the graphics community when it came out. Keep that in mind when people don't like your stuff. And here we are. Pleasure.
Okay. Test, test, this works. Yes, I'm trying. I'm working on it. Test, good. All right. So, hello and welcome. This talk is about EdgeFront, a novel data structure for Catmull-Clark subdivision surfaces. And this is joint work with Max Oberberger, Matthäus, Chajdas, and Quirin Meyer. Let's dive right in. So what is Catmull-Clark subdivision about? So the idea is... Okay, good, fine. So the idea is that you have a coarse mesh as input, and then you subdivide it to a smooth surface using subdivision rules until you're satisfied with the resolution. How does it work? So the concept is based on B-cubic B-splines. So here we have a context of a grid of 4 by 4 points, and then you can evaluate the smooth surface of the centering quad using the B-spline formula. But what to do about these kind of configurations where you have, for example, a vertex with valence 3 or a pentagon, and here you only have the subdivision rules from Catmull-Clark. And the idea is that you create new control points and then just do it over and over again until you have enough points. There are 3 different kinds of points. So first is the face point, which is just generated from all the vertices that make a face. Then there's the edge point, which is generated from all the points which are kind of adjacent to the edge. And then you finally update all the vertex points of the input mesh with all the adjacent vertices. All right. And then you take your new points and connect them with quads. So the refined mesh is always a quad mesh. And then you get your refined mesh. Okay. How to render such a surface? So the most common technique rely on the observation that the directly evaluable portion of the surface increases the more you subdivide. So here you got 3 new patches which are cubic B-splines, and only 1 corner is still extraordinary. Other techniques rely on the observation that extraordinary vertices isolate themselves after 2 subdivision iterations, and then Stam found some lookup tables to directly evaluate the surface of the extraordinary patch. What we are interested in about is to directly implement the subdivision rules on the GPU in an efficient implementation. And here we take the half-edge refinement by Dupuy and Van Hooy from 2 years ago as our base. And the idea is that they take the well-known half-edge data structure and just subdivide it on the GPU in an efficient implementation. And well, this technique has kind of some attributes, and we want to keep them, so let's write a to-do list. So we want to run fast, right? We want to allow for real-time topology changes. So, for example, they just take the half-edge data structure, and if your, for example, modeling software already uses some kind of half-edge data structure, you're good to go. You don't need any pre-processing. We want to do something similar, and half-edge is really easy to implement, not that much code, and it is extensible to semi-sharp creases, for example. So we want to do that as well. Right, let's take a closer look at the half-edge. So a half-edge is essentially a struct that has a reference to a vertex, a reference to the previous half-edge and to the next half-edge, some IDs, and a reference to the twin half-edge. And if you look at this from the perspective of a quad, you get these 2-way references to all adjacent quads. And we thought this 2-way reference was kind of redundant, and so let's add this to the to-do list. We want to reduce the neighborhood information, if possible. All right, so this is the core half-edge implementation. So it consists of 4 kernels, and you can see all these kernels essentially for each half-edge do something. And you cannot merge these 4 loops or that run in parallel because, for example, the edge point computation requires knowledge from the face point computation. So you need your synchronization barrier in between. And this slows down the computation, so let's add this to a to-do list. We want to merge everything into a single dispatch if possible. All right, next, here's how a new point is created, and this is essentially an atomic float add. So if points are floating point, and you need an atomic synchronization because multiple threads add onto the same memory address. And this is a special feature in most APIs, and also it's not available on every hardware. And so we don't want to do that. And there's one more thing about it. Atomic floating point arithmetic is in fact not deterministic. So let's take a look at this code example. So here we define 3 floats. And if we just add them in 2 different ways, right, we change the brackets, and we cross it to an integer and print the result, we can see that, in fact, 1 bit is flipped. Why is that? Well, floating point arithmetic is not associative. And if a scheduler changes the order of execution of threads, the resulting mesh, in case of subdivision, will also change a little bit. Is this a problem? Well, you can decide. Here's a visualization of that. So what we did here is we took 2 identical cubes at the exact same position, and one is blue, one is red. And if we subdivide them using atomic floating point arithmetic, here we can see this artifact. It's a constructed example, but well, you can at least visualize it. If it's a problem for you, you can decide, but we wanted our algorithm to be deterministic and not rely on special hardware features, so let's add this to our to-do list. All right, finally, we noticed some problems with the memory layout. More on that later, so let's add this to our to-do list. We want to improve it. Okay, this concludes the to-do list. Let's start with the first item. We want to reduce the neighborhood information. So we talked about this. We have this 2-way reference. And when we want to reduce this to a 1-way reference, we quickly realized that we need this alternating pattern. And a different way to look at this is to say that each quad receives 2 edges, and the 2 other edges of the quad are referenced by these arrows. And we call these arrows the edge friends, so that's the name of the data structure. That way we get our neighborhood information. So you notice for this we need quads, and well, we know that after 1 subdivision iteration everything turns into quads, so we need a preprocessing iteration. And we additionally want to build this alternating pattern during this preprocessing iteration. How do we do that? So we always start a new quad at the original corner of the old quad. And if we do this for all the new quads, we can see that always the first and the third edge are owned by the quad, and the 2 other quads will get the edge friend. Okay, and if we do this for the neighboring quad or for the pentagon here, you can see that this pattern always works out. By the way, if the mesh is not closed, we just close the mesh and then just ignore the unused or the redundant faces when rendering. Okay, so let's show the edge friends again. So we successfully reduced the neighborhood information, essentially halved it. So let's check that one. Okay. Let's talk about how we subdivide our data structure. And essentially, we split our subdivision into 2 tasks, the vertex task and the quad task. This is the quad task, so we spawn a thread per quad. And then first, we just compute a phase point, pretty straightforward. And then we can use the 2 edge friend references to compute 2 edge points. And if we do this for all the quads, we can see that all the edge points are computed by someone, none are missing. So again, this pattern. So this concludes the quad task, and we now have successfully computed the edge points and the phase point. Let's talk about how we update the vertex points. So we talked about this. We need to collect all the vertices that are adjacent to the vertex. And how we do that, we again use the edge friends and just start at an arbitrary phase and just loop around so to say, the valence of the vertex and collect all the data that we need in a do-while loop and end the loop when we are back at the original corner. And if we visualize this, you again see this alternating pattern. So we can go clockwise, counterclockwise, clockwise, and so on. All right. So we have successfully removed all atomic floating point arithmetic because we just gather all the information that we need for the point update in a single thread, right? So we don't need any synchronization there. But we still have 2 separate dispatches. We have the quad task and the vertex task. So let's talk about how we merge these. So for a mesh, we have with F faces, we have F quad task, and with V vertices, we have V vertex tasks. And then remember this guy, and he found a ratio between the vertices, edges, and faces of in this case, closed topology homomorphic to a sphere. There's also a formula for other genera of topology. And we know that we have assigned 2 edges to each quad. So we can just plug this in and rearrange a little. And then we can say, well, the number of vertices is approximately equal to the number of faces. So we can just plug both in the same kernel and just exit early if there's this edge case when one number is greater than the other. Well, then we're done. So let's check that one. We've merged it to a single dispatch. All right, let's talk about the memory layout. So this is the memory layout of previous work. We have the vertex point and then just append the face and the edge points which are newly created to the buffer or to the memory. And if you do this, look at the next generation, we interpret this buffer as the new vertex points, and here you can see the exponential growth of the problem. And we notice that a new quad will always reference 1 vertex point, 1 face point, and 2 edge points. So the distance between the memory addresses of the vertices that make a quad grows exponentially. And this is really bad for cache coherency. What we do instead, we again remember that the number of vertices is approximately equal to the number of faces. So we just interleave the buffers and just say we put 1 vertex point, 1 face point, 2 edge points, and then repeat. And this had a great effect on runtime performance because the cache is more coherent. All right, so let's check that one. And let's talk about results. So here are subdivision timings, and in this case for 5 iterations, so we multiply the number of phases by 1,000 approximately. And our technique is in blue. The previous technique, half-edge refinement, is in orange. And the red bars are the half-edge refinement with where we had to simulate floating point arithmetic for example, hardware or APIs that don't support it. And as you can see, we are approximately 3 times faster than previous technique. So we wanted to run fast. We're about 3 times faster. Let's check that one. So we wanted to allow for real-time topology changes, and I mentioned that we need some preprocessing. We need 1 preprocessing iteration. So we measured our preprocessing. These measurements include the generation, like the input is a vertex buffer and an index buffer, and we generate a hash map for like getting neighborhood information, and then we subdivide once into edge friend geometry. And these are our preprocessing times, and as you can see, we need less than 3 milliseconds even for our biggest mesh. So we call that real-time sufficient. All right. Finally, we wanted to be easy to implement and extensible. So we successfully extended our technique to semi-sharp creases, what was pretty straightforward. And, well, easy to implement. We have basically all pseudocode in the paper, and we are aiming on publishing at least the shader in open source soon. So stay tuned. So let's check that one. All right, this concludes our to-do list and my talk. Thank you for your attention, and I'm open for questions.
We have a question here.
Hi, yeah, that's a great talk. Just one question. You were talking about making sure that the mesh was always closed. So does that change the behavior of the end surface as you subdivide?
It does, but we allow semi-sharp creases. So we have added support for semi-sharp creases, and then we just add, or we just set all the edges that are actually borders as infinitely sharp, and that way they have the same rules, so it works out. Yeah.
We have a throwable mic.
Oh, I did. It's awesome. Okay. Should I stand up? Either way is fine, right?
I can see you.
Okay, perfect. Great talk. Any thoughts on adaptive depth-first subdivision?
Yes, we thought about it. Don't have a solution yet.
Okay. But it should actually kind of work, right? If you collect the one ring, right, and then do it locally.
Not sure if it's me or someone else. Okay. Yeah.
We can follow up later.
It's a similar problem than like with unclosed, with open topology, like with borders, right? Because you need to, like in our case, we only can loop around a vertex one way, and if there's like a face missing, we kind of need, we're kind of missing this reference. I thought about solutions, or we thought about solutions. We put it in previous, in future work, So maybe we can come up with something.
Okay, thank you.
Time for one more question.
Anyone?
I'll take the liberty of asking the final question. So what do you think the future for Catmull-Clark is versus triangulated kind of approaches, just in our field in general?
So I mentioned, for example, like current techniques always use the tessellation shader, and I'm like interested in about whether using mesh shaders might be better, but I can't say yet. So, but I don't have any more to say about it, I fear.
Let's thank our speaker again. Who's talking on ambient occlusion. That's the Energizer bunny of graphics hacks. And I think we've all come to love ambient occlusion now. It's simply not going away. It turns out to be one of the best perceptual techniques ever. And why it works so well isn't exactly clear. And it is worth making faster, because I'm sure, as our speaker knows better than I do, there are more battery-powered graphics devices in use today than all other graphics devices put together in the history of humanity. It's kind of amazing. We don't emphasize it enough often, but in this conference in particular, we should, as our speaker agrees with, I'm sure.
Thank you so much. Yeah, exactly. Ambient occlusion is kind of like one hack that works really well, is not super related to physics, but let's just dive into it right away. So this was like my final topic throughout my PhD, worked in collaboration with Meta throughout my internship. So let's talk about AO for a bit. So this is just a render of one of the test scenes we have been using, and this is just using standard shading. There's nothing else applied to it, no like shadows and stuff. Oh, it's auto-advancing, sorry. I'll just deal with it. Essentially, you have this image without any shadows, no direct shadows, no indirect shadows, and once you add ambient occlusion to it, the sense of depth is much more immersive, and it's essentially just a metric or a measure of how occluded each surface is on average. Now, this topic is about split rendering in context of ambient occlusion, so let's talk a bit about split rendering to contextualize our work. In modern real-time graphics, you nowadays have at least millions of triangles, but for high-end systems, you have billions of them. So in addition to that, you also have expensive and complex effects, and these include like global illumination, reflections, volumetrics, and all of that is happening at a very high refresh rate and resolution. So if you think about it, running something like Lumen or Nanite in Unreal Engine 5 at full fidelity on like weaker devices such as phones or standalone AR/VR headsets is not really feasible. And this is where we start talking a bit about split rendering. So splitting up the workload of the render to make the computation on the weaker devices somewhat manageable, but still utilizing the hardware to its maximum effect. Now imagine you have a server that's running at like 20 frames a second. Could be a bit lower, could be a bit higher. Now the server prepares a split rendering representation. So this can consist of geometry, textures, buffers, or anything else. Could also be points. And it sends this representation, usually via some compression or encoding, to a client. This could be a phone, this could be like a weak edge device connected to your TV, could be a standalone VR headset. And what this client does is it has its own kind of somewhat weak chip, but that does very rudimentary standard graphics things, and it can do decode, render, and composition things, and it does this to render autonomously, and it just sends back transforms and scene updates to the server so that the server knows exactly how to prepare this split rendering representation. So for split rendering, both the server and the client contribute to the final image by utilizing simple graphics operations and a suitable split rendering representation. Now there's different ways of representing the data. So you could, for example, just use voxels, or like a dense 3D grid of points, for example. Can be very efficient, especially to look up if you use 3D textures, but can also be memory intensive. You could use probes, as is commonly done for global illumination. Like this could also be a suitable representation for streaming and splitting up the render workload, especially for like low frequency things like lighting using spherical harmonics. The thing that I'm going to be talking about a bit, because we are also going to be comparing about it, and because it gained some popularity in recent years, is texture space representations that essentially try to map a consistent representation of the surface into like a texture. So texture space shading, just to give a brief overview, is a consistent mapping from an object surface into a 2D texture. And once we have that, we can compute pretty much any surface material function inside this texture space, for example, the full shading. And then we have this kind of texture cache. And once we have that, the client can autonomously use this information to render new views. So we have effectively decoupled the shading and the display stage between the server and the client. So there are some limitations to texture space shading, and this is kind of the core of the motivation for this work for us. So texture space shading, in particular, many of these geometry-based methods, like shading atlas streaming, they are very sensitive to the underlying geometry of your meshes or your scenes. And sometimes, for example, with shading atlas streaming, you pack these groups of 2 triangles each into rectangular blocks. And as the example here illustrates, if you have very non-uniform triangles, this will end up leading to distortion of samples on the object surface. So this is something we do not want, and it also includes like expensive pre-processing passes, so it's kind of a hassle to deal with. Now what about points or circles? So recently, circles have gotten increasingly popular again, for example, for real-time diffuse global illumination. There's this amazing SIGGRAPH 21 talk by EAC's team about global illumination based on circles, where they just distribute a bunch of circles in the scene, scale them dynamically, and adjust the workload based on how far or close things are to the camera. Actually, like point-based global illumination has been really popular for a long time in the offline rendering space, but not necessarily in real-time spaces. But some of the advantages of it are that we can completely decouple these points or circles from the geometry, and we have the possibility of adaptively spacing and sizing them. And this gets us to our point-based split ambient occlusion pipeline. So again, we have our server. We have a point generation system, so we initially generate a bunch of points in the scene. So this is just an overview of the pipeline, more on these individual things later. Then the server runs again at a lower decoupled frame rate. It does some memory management on the GPU, it does some update and rendering of the points, and it prepares all of these points for networking for the client. Then we have our point representation, which in our case is a hash grid. So we have a hash table that maps a 3D grid for each mesh instance towards a virtual cell data array. So this is very efficient to look up, but also saves memory compared to like using a dense grid. And the client then receives this point representation and can then render autonomously at whatever frame rate it wants to produce the AO reconstruction, so a final AO buffer that it can then composite on top of the color information of the scene. Now let's dive into some of these individual blocks a bit deeper. So for our point generation system, we first spawn points fully randomly on object surfaces. We do this on the GPU, so it's quite fast. And we keep the point density consistent on average. So we just have a scaling factor that decides how many points we want to use per unit area. And we also take double-sided materials and masked materials into account so that we don't spawn points there. And to prevent points from clustering on top of each other, we use Poisson disk rejection to make sure that they're very uniformly spaced. So here's an example of just using the uniform point distribution where you can see that points are clumped up together. And with the Poisson disk rejection, the points are much more evenly spread across the surfaces. So here the points are visualized as these white quads on the surfaces. Then for the server task, for the first one that's happening every server frame, we first determine course visibility. We use an extended field of view as a standard for these kind of split rendering systems to determine which points are visible. Then we determine the new point positions using, for example, the updated skinning matrices and new transforms that we get from the client. Then we ray trace all of the visible points to determine their ambient occlusion value. So for example, here, if we have the frame N and some sort of mesh, we just do ray tracing for each point. This is quite expensive on the server, but nowadays with modern ray tracing hardware, this is kind of feasible. Then we quantize and encode the position of each point and normal and the AO value such that everything fits into 32-bit. This doesn't really affect the quality from our experiments. It can probably go quite a bit lower, but this is up to future work. And importantly, if any of these values change, so if any position of the point changes or the normal or the AO value, we mark it as dirty for the subsequent memory management and networking passes. So let's get to the memory management. So again, we have this kind of 3D grid for each mesh instance. And how we get to our actual point cell information is that we hash the coordinate of the grid cell, which gives us a hash bucket. And this hash bucket has a point cell offset into like a large buffer of point cells. And it also has a physical cell ID, so not a virtual one, that we basically just perform a linear search over to find exactly which bucket we have in case there are multiple cells hitting the same hash bucket. Once we have this offset, we basically just go into a large linear array containing a bunch of cells, and each cell simply has 7 points and some additional bookkeeping data that follow exactly this point data structure. So all of that is very tightly packed, and the lookup is quite fast on server and client. Now let's get to some examples if you want to add or remove or update cells. So for example, here we have this cell at location X, Y, and Z with 4 points in them. If we want to add a new cell, we first find the first free hash bucket by just looking linearly over the hash table and seeing which one is free. Then we figure out a new offset in the point cell data structure where we allocate a new cell. This cell then contains the information of all the points within it, and then we send this hash bucket and the point cell as an update to the client. The next thing is if we want to remove a cell, for example, if all of the points within a cell have been removed. And in this case, we just look up at where exactly we are in the hash bucket and just clear the entry and send an update to the client. And the final thing we can do is we can update points. So if, for example, another mesh moves on top of these points such that their AO contribution is a bit darker, we do exactly the same thing. So we follow the hash table, we find the bucket that corresponds to this cell, we find the cell, and we update all of these entries within it. And for the client, we simply send the full point cell. In our experiments, sending the full cell is actually slightly more data efficient compared to sending individual points, but it depends on how many points you store within cells. Now, in terms of networking and compression, all dirty point cells and hash buckets are delta encoded and compressed via off-the-shelf compression, such as LZ4 or Z-standard. And the client data representation stays consistent with the server representation. So both of them use the same data structures, and we just compress them and send them to the client as is. Now let's come to the interesting part in terms of performance on the client. During rendering on the client, we query the hash grid of the current surface fragment. So this is exactly the same thing we do on the server to figure out which kind of hash bucket we land into and what kind of, in which kind of cell we are and how many points are in there. But only using a single grid cell would introduce block sampling artifacts. So we actually use a 2x2x2 neighborhood of cells, and we blend the contribution of these cells based on the distance, position, and normal. So if the normals deviate too much, we don't use these points, and similarly for like distance and position. And then once we do that, we end up with our final AO buffer on the client that we can then composite on top of the color image. Let's get to our evaluation. So we have 3 test scenes with 2 camera paths each. Each camera path is 15 seconds at 60 Hertz. And we compare a variety of quality metrics, so like PSNR, LPIPS, and FLIP, when compositing our AO that is rendered at 1080p on top of a 4x supersampled shaded reference. So our color buffer is 4x supersampled, and we compare the AO contribution of different methods compared to a reference that is just brute force ray traced with 512 samples. And then we measure the network bandwidth in split rendering and streaming mode for approaches that can be split, and we compare against Shading Atlas streaming, which is a texture space shading variant, and against screen space ambient occlusion, which cannot be split up, but we can just compare against it in terms of performance and quality. Let's get to some numbers. So here, SAS 32 and SAS 8 denote 2 different configurations of Shading Atlas streaming, where the 32 version is a bit larger and doesn't constrain its texture space layout that much. And the PSAO variants, the increasing numbers mean how many points on average we have. So larger numbers mean more points distributed in the scene. And SSAO is screen space ambient occlusion. So if we look at the quality metrics, it's not our point-based split ambient occlusion achieves the best quality compared to the other approaches. Mostly, SSAO doesn't deal that well with large distance ambient occlusion, so it tends to produce halos there. and our shading atlas streaming system struggles with the fixed shading budget that we employ in this evaluation, so it tends to overly blur the AO contribution, which hurts its performance numbers. Now, more interestingly are the bandwidth numbers. So here we have the network bandwidth required in megabits per second. For all of these evaluations, the server was running at 30 frames a second. So if we compare like the medium configuration of our point-based split ambient occlusion versus the large configuration of shading atlas streaming, we can see that we outperformed them in terms of quality by quite a substantial amount, even though we save quite a substantial amount on bandwidth as well. And this even follows through to our lowest configuration or lowest quality configuration of our point structure, where we save even more in bandwidth, but in terms of flip and LPIPS metrics, we even still beat the shading atlas streaming system. So here's a video of a point-based approach. You can see it handles like animations quite well, and there's no like flickering artifacts going on. Everything is like temporally coherent. There's some blotchiness going on that can be tweaked based on the amount of points that you're actually using in the scene, but overall it matches the result or the quality of the ray traced reference quite well. In terms of performance, on our test system, performing the hash lookups for a single 1080p frame takes around 0.5 milliseconds on average. And this does not significantly change with larger point clouds, as roughly a consistent number of points are sampled on average on the client. And in contrast to that, screen space ambient occlusion on the same system requires around 0.2 or 0.3 milliseconds per frame. This is without a depth or normal prepass, which can or cannot increase the overhead if you don't have that in your engine. But overall, the sampling, the raw sampling of our method on the client is comparable to SSAO in terms of order of magnitude. Shading atlas streaming only requires a single bilinear texture fetch per fragment, which is pretty much as fast as you can get for like a split rendering system. But this obviously doesn't account for like the decoding and all of the networking overhead that this texture space representation has. So in terms of limitations, we currently only do static point generation, and future work could dynamically allocate and deallocate points based on demand or compute constraints. Additionally, our update heuristic is currently quite simple and operates on a per point basis. So as I've talked about, the server just ray traces all of the points and figures out which values have changed, which is quite expensive on the server, of course. So considering mesh bounds instead could help with server performance and scalability. And we currently also do not use any explicit countermeasures against AO leaking, which is a common artifact you see with like point-based methods or server-based methods. So in practice, a sufficiently dense point distribution kept these artifacts at a minimum for us. But with additional compute headroom, you could use highly compressed coarse depth estimates for remedy of leaking by doing simple depth tests. Now we've shown a point-based split ambient occlusion, a point-based split rendering system for ambient occlusion that outperforms other split rendering systems at costs comparable to per frame screen space approaches. And this demonstrates that points could be an attractive data representation for decoupling of rendering tasks going forward, especially given that we now have hardware to ray trace these points, which was quite a bit more expensive previously. Now to conclude, here's a QR code that leads you to the eventual code release. Currently this will lead you to a 404 because we haven't made it public yet, but hopefully we can do that soon. And before we go to Q&A, shameless plug, I'm currently a research scientist at Luma AI. We're hiring, so if you're interested in the new generation of 3D tools and 3D generative tools and nerfs and things like that, feel free to reach out to me or join, or visit our join link. And with that, I'm happy to take any and all of your questions you might have.
And we have the throwable mic again.
Good talk, thank you. Given that you're doing like a final gather style ray trace on the servo, is there any reason you didn't look into like a GI type thing, like over AO? Like you could go and grab the colors from the ends of those rays?
Yeah, essentially, I think this could extend quite well to GI as well, especially like to the low frequency components of it. Initially, we were planning on doing that, but kind of like wanted to keep the focus on being more simple. Like I think you can extend it. It's mostly about figuring out how to efficiently compress it in that sense. Like most of the gains that we have here is because AO is just so good or so easily compressible. If you have like more complicated information like full colors, you might want to have like a different compression scheme or maybe pack things into like an MPEG texture or something. But there's no reason why that shouldn't work if you figure out some smart representation of doing that.
Cool, thank you.
Yeah, I wonder what the performance implications for dynamic geometry are, like when you have to recompute the Poisson points and so on.
Yeah, so currently the point generation, which is like the biggest limitation, this is currently static. I feel like, so we do have like skinned animations in there, and for those currently we just allocate an additional headroom of points that can move around and deallocate and allocate. If you want to do the point generation on the fly, I think the Poisson generation is quite a bit too expensive, but I'm pretty sure you can get really close with just some clever heuristics and doing it on a GPU.
Oh, thank you.
More questions? Okay, I'm going to close with the last one then. Oh, was there another?
Yeah, over there.
Test your throwing arm. That was a good throw.
Hi, thanks for your presentation. So you mentioned that for AO you get very high compression ratios and you're not sure whether you would get the same for GI. So
yeah.
What kind of compression ratios are we looking at?
I'm sorry, could you repeat? I didn't quite...
What type of compression ratio do you get with AO that because you mentioned you might not be able to get it with GI?
I think I don't remember on top of my head, but I was at least somewhere between 5 and 10x compared to like sending it just raw. Like most of the compression ratio that we get is just by quantizing the things such that you don't actually see it. And there's like an additional 2 to 3x when you use like LZ4 or C standard. So you end up with somewhere between 5 to 10x. Yeah, especially like the AO values, you don't, if you have so many points, you don't really notice the differences between all of these, so you could go even lower. And that actually could also apply to GI. So if you have a ton of points, that makes like your overall contribution of each point lower. So it's kind of a trade-off between how many points you have and how large each point is going to get. But I assume for GI it's going to be a bit lower, but you could still kind of compress it as efficiently such that it is comparable to like a texture space representation.
Right. Thank you.
Okay, let's save my great question for the coffee break and move on to our next speaker. Let's thank our speaker. You're the keeper. Say your first name again.
Caio.
Our next speaker is Caio Brito, and he's talking on a completely different subject than the first two. Oh, talking to the mic better? How about now? He'll be speaking on a volume-based representation, which is something I actually worked on a couple of years ago. This is something I'm a true believer in long run. And like neural nets, it keeps working off in the wilderness while it tries to displace triangles. And I can tell you at the very first HPG, if you'd taken a survey, I don't think any of us would have voted that triangles would still be the dominant way to represent geometry because it's so bloated. So we're still setting up. This is the one constant of all HPGs that I've ever been to. You good?
1 second.
Okay,
Sorry.
1 second. It's all right. So while we're waiting, I'll give a spoiler for the question I was going to ask. So we've developed in graphics nice looking graphics. Oh, here we go. I'll save it for the break.
Yes. Okay. Hi. Can you all hear me? I hope. It's really loud, but yes. Hi, my name is Caio. Thank you for the introduction. And I'm going to present a voxel-based representation for improved feature appearance. I'm a PhD student at the University of Montreal, and I've been working with Pierre, Poulin, and Veronica Teichrieb. So the complexity, yeah. looks great. So the complexity of a scene in computer graphics application has been increasing over the years. Just to give an idea, a car from Gran Turismo had 300 polygons in its first version, and now have 500,000 in the current one. But not only that, but the quality of rendering has been increased. So to render high quality scene like this one in the image would be quite challenging due to rendering time and memory consumption. So in any scene, as objects are far away, fewer details are visible. However, rendering these objects, even if they are really far, is still quite challenging in both rasterization and ray tracing. In rasterization, you need to visit all the polygons to render such objects. And in ray tracing, you need to properly cover the pixel in order to get the correct final color. So if you do undersampling, details like the building antennas in the image could disappear, and aliasing proves to be a major issue. However, sampling more rays per pixel might jeopardize the rendering performance. So finding ways to improve the performance and memory consumption are needed, and a common way of doing that is to apply level of details. As the objects are far away, loading every asset is not fully necessary, and some form of simplification and approximation can be used to render these objects. So although LOD is a common concept in the CG industry, it's not fully solved. For instance, Burley mentioned in his paper about the Hyper renderer that if any artifact would appear in the image, they will ask, oh, did you try to disable the LOD? And then eventually the feature that they have was removed. So one way of performing LOD is to do mesh simplification, as to reduce the number of primitives that will be rendered. However, this approach suffers from appearance loss. As you can see in the image, the diffuse and specular shading does not fully appear after a few simplifications. And sorry, in a scene like this one of the tree, after a few simplifications, the small leaves will disappear, causing occlusion miscalculation. And also, mesh simplification has issue with excessive noise, and ultimately could rely on manual intervention, adding some extra work to the artist. So another solution is to approximate the scene to a volumetric representation. A voxelized representation presents a natural hierarchical model and has a fixed cost per voxel. However, presenting one approximation that can handle both volumetric and surface-like appearance, like the one in the image, you have the trunk of the trees as a surface-like, and the leaves has a more volumetric appearance that could be quite challenging to handle. So over the years, several volumetric approximations have been introduced. So back in 1998, Neff introduced a volumetric representation that fits the distribution of normals into an ellipsoid. And more recently, building the same idea of using an ellipsoid, Heitz and colleagues presented SDGX, a macroflexible representation to approximate the distribution of normals. And to render both surface-like and volumetric appearance, Loubet and Neff identified the surface-like parts of the scene, like the tree, and they will find the trunk and render as the original polygon, and the volumetric part will be rendered as voxel. So in order to use only voxels for both surface-like and volumetric appearance, Vitin and colleagues introduced a new transmittance model that can transit between linear transmittance and exponential transmittance. And they both use SDGX to approximate the distribution of normal. And more recently, Baco and colleagues and Via and colleagues use neural network to learn the appearance and visibility of a voxel, and also to perform data compression. While providing nice results, they surface from long pre-computation at the learning phases. So now for the rest of the presentation, I only mention the first name of the author to reference them. So building from previous work, we want to pay particular attention to the directional distribution of normals, colors, and visibility. And we only use local volumetric data to build our representation, and we only use volumetric information. We want to handle both large and small occluders without any artist intervention. So to achieve these goals, we propose a virtual mesh that encodes colors and normals in its faces and vertex, and that will approximate the appearance of the voxel. We also propose a low-resolution subgrid to encode opacities to approximate both surface-like and volumetric appearance. And finally, we rely on simple but efficient random methods to sample the virtual mesh and compute the opacity from a voxel from a given viewpoint. So to build our representation, I'll give a brief overview. We have the input scene, then we voxelize that scene, and for each voxel, we sample rays from outside to get the normals and the color of the hits, and we keep the occlusion as 1 if it hits an object. If it doesn't, we just keep the occlusion as 0. Finally, get all the normals to create the oriented virtual mesh, which will store the distribution of normals and colors, and the subgrid of occlusions will be created to approximate the occlusion due to the voxel. Now I'm going to add each step individually. So the first one is the vox sampling. We want to unbiased sampling of its content, and to achieve that, given a voxel with an object inside, we sample point P and the sphere that surround that voxel with direction D towards the center. Then we project the voxel into the plane defined by P and D, and we randomly shift P to P dash, keeping the direction D. We shoot a ray from that position direction. If it hits, we set the occlusion to 1, and we keep the normal and color of that hit. Otherwise, we just set the occlusion to 0. So from all gathered voxels, we build the virtual mesh that approximate the distribution of normals and colors. And the virtual mesh is an octahedron, triangular shape that store up to 3 voxels and 1 color per face. And note that the virtual mesh does not approximate the actual mesh that is within the voxel, but approximate the appearance of the voxel. So given a voxel like this one in the image, you have a blue and a green object. In the end, after the first step, and all the data are gathered, and we have a set of normals, and the color relate to each normal. After that, to build the virtual mesh shape, we estimate the ellipsoid that best fit the distribution of normals using SDG estimation method, and we approximate the ellipsoid shape using octahedron as a triangular mesh. So the octahedron faces divide the space into 8 octants, and each gathered voxel is assigned to one of the octants. That gives a distribution of normal per face. And for distribution that has more than 3 normals, we compute the cone that best fits each distribution. And we assign the color of each face as the average color of the samples that are in each face. In the end, we store 3 extremal normals for the cone of a face, and we compute and store the average color of each face. Note that the face of the octahedron may not contain any distribution, like the one in the image, and we handle spatial case between 0 and 3 normals and colors. Now that we have the shape of the virtual mesh, we need to sample. So doing rendering, given a view plane and with a view direction V, we project the octahedron to the view plane, and we randomly pick a point in the projection and create the corresponding ray. Then the ray intersection with the virtual mesh gives a normal from a barycentric interpolation and a color that is the color of the face. We typically shoot 160 rays and shade the voxel accordingly. So now, regarding the occlusion, we take inspiration from previous work on Vicini, who sampled the neighboring voxels to get a correlation between voxels. However, this approach is hard to generalize. So we apply the same concept, but instead of looking to the neighboring voxel, we look to the information within the voxel. So given one voxel with a few objects inside, we subdivide it into a low-resolution subgrid of 3 by 3 by 3. And then we populate the subgrid. We compute the intersection of the sampled rays from previous step, and we add the opacity values of each subgrid traversed by a ray. After ray tracing all the rays and compute all the intersections, we compute the average opacity for only non-empty subgrid elements, the one in cyan. And for empty subgrid elements, we have a 0 opacity. So now to compute the occlusion in real time, so we have a voxel with a 3 by 3 by 3 subgrid elements, and then we define the square window that bounds the parallel projection of the voxel and divide it to a 4 by 4 pixel. Then we replace each subgrid element by an enclosed sphere, and each pixel of the window is approximated by its inscribed in sphere. So we project each sphere to compute the occlusion contribution, and the opacity of the subgrid elements multiplied by the coverage area. We only keep the largest contribution for each pixel, and in the end, we compute the average of the pixels to get the final occlusion. So our representation requires 143 bytes of memory per voxel. Our virtual mesh, we have 3 eigenvectors and 3 scaling factors in order to reconstruct the virtual mesh, and 3 normals, 1 color, and 1 Boolean per face. And that Boolean is to encode if the face has a distribution of normals or just a fixed set. And for the subgrid of occlusion, we store one value per subgrid element, giving a total of 27. So we ran our test in an i7 with 32 gigs of memory and a NVIDIA RTX 2080 GPU. And our scene varies for 100,000 to 3 million triangles approximately. And the pre-computation took on average 22 seconds at 128 cubic resolution and 101 seconds at 256 cubic resolution. And we rendered the scenes at resolution fit 1 voxel per pixel. And on average, rendering achieves 59 frames per second at 128 and 27 frames per second at 256. So we compare our representation with the average of color, normals, and opacity, and occlusion, sorry, and with Vicini's approximation. However, we only use local information for each approach, which is different than the improved method of Vicini. The reference image is rendered with 1024 rays per pixel. So our representation can reproduce different appearances. You have the buildings and the street as large occluders, and the trees and the antennas of the buildings as a volumetric appearance. And the other approach have difficulties to reproduce surface-like appearance, as can be seen in the holes in the buildings and the streets. So in this scene, you have the island, and the tree trunks has a more large occluder appearance, and the leaves of the tree are more volumetric occluders. So given a closer look, we can see that our representation reproduces the island as a large occluder, as others might fail in that. As you can see in both average and Vicini, you see some blue that is behind the island, from the sea that is behind that should not be visible. Also, we can better reproduce the trunk appearance. Meanwhile, other methods produce discontinuity in the images. So here, the light source is behind the object. Our representation can reproduce the correct shading, as most of the visible bunny is not visible to the light source, given the dark appearance. And the approach from Vicini fails to reproduce such shading, because the object is not fully opaque, and the white background leaks through the bunny. And even if we set the occlusion to be full occlusion, so we still have problems. So for our representation, for objects like the bunny, that the normals are one-sided, our virtual mesh will fit the normals into a few faces without any symmetry. Meanwhile, SDGX distribution has a symmetrical shape, which creates a set of normals that are not part from the original distribution, generating the normals that are highlighted in red, and that can lead to incorrect shading, as can be seen in the red highlights. So our representation can reproduce diffuse and specular shadings, although SDGX is also able to reproduce both shadings. However, the leak of opacity, or by the method of Vicini, reduces the shading quality. And quantitatively, our method produces smaller errors and large SSIM compared to previous work in both 128 and 256 resolution. However, in some cases, due to the extended occlusion factor, it may be less accurate. So here, the average methods produce a higher error all over the place in the scene. Meanwhile, Vicini produces a mix of low and higher errors within a small pixel neighborhood. And our representation produces better results overall, but we are not free from issues. So as we use a conservative maximum occlusion, we make small occlusion larger, and which makes more prone to error in test scenes that are mostly like the one with the tree, that has a lot of small occluders. And here the result from Vicini produce a better appearance of the tree. So to conclude, we introduce a virtual mesh and an opacity subgrid to capture variations of appearance of a volume. We only use local information, and we have a more general approximation compared to previous work, and we believe it's one step into integrating volume rendering for general scenes. We reproduce both surface-like and volumetric appearance, and only using local data. So for future work, we would like to investigate how to merge the distribution of normals and colors and opacity from finer resolution without the need to resample all the resolutions individually. And we'd like to integrate our representation into a more complete line transport simulation to render a scene like this one in the image, that you have multiple light sources and they interact with the buildings around and create that glow aspect. And finally, animated scenes are challenging due to the variability in volume distribution. Thank you very much. The code should be available soon. Thank you. 。 . 。 。 。 。 .
。 . 。 。 . 。 。 . 。 。 。 。 。 . 。 。 . 。 。 . 。 。 . 。 。 . 。 。 。 . 。 。 . 。 。 . 。 。
We have time for a couple of questions. Are there raised hands back there? Any questions? We have one.
Did you, nice talk, thank you.
Thank you.
Did you consider the performance of just rendering the octahedrons not virtually, like actual octahedrons?
Sorry,
so like, I was just curious about the rendering performance. If you, instead of having virtual octahedrons, you actually just instantiate them as polygons and rasterize them all. Did you experiment in that direction at all?
No. So we focus on the actual appearance, but even with ray tracing, like you have GigaVoxel, for instance, that I saw 300, 400 frames per second. That could be much better, but then there'll be another focus on the research. But yes, we could improve.
Okay, thank you.
Over there.
Test your arm again.
Yeah.
B plus.
Hi, a very nice talk. I was just wondering on slide 16, where you basically do sampling by a sphere.
Yes.
This is basically you are trying to do uniform uniform distribution of rays.
Yeah. So it's on slide 16.
Slide 16, yeah.
Yes. Okay.
And I was wondering why you are not using standard algorithm, because the standard algorithm is that you take a sphere and you put the points uniformly on the sphere surface, and then you connect basically all the pairs of these points, and then you get uniform distribution of rays in space. So this is like from the book of Santalo, which is called Integral Geometry and Geometric Probability, which is, I think, very good book to read if you work with the distribution of rays or points. So it's perhaps a point for you that you can improve on the performance of this point, of this part of the algorithm.
Yes. So what we did, we want unbiased sampling.
So you just waste some rays that they cannot contribute to basically to the solution if you do it this way.
Yeah. Okay. That's interesting. We can probably talk later.
I will give you the reference to the
Yes,
book.
please. Thank you.
I'll ask the last one before coffee break. How come 3 by 3 by 3 and not 4 by 4 by 4 for the voxel cells? Because 4 is a very powerfully magic number in our field.
Yes, true. Yeah, so we tried different resolutions of the subgrid. So we tried 2 by 2, and then there was like really weird stuff working on. And then we did 4 by 4 and on. But we tried to find a sweet spot between the rendering quality and the performance. So 3 by 3 by 3, it worked well in that case.
So Goldilocks.
Yeah.
Okay, enjoy your coffee, and let's thank our speaker.
Thank you.
check, check. Check, check. Check, check. Ja. Misschien is het... Als je dit, check, check. Als die gaat, dan moet je de logo even in de midden even wat wegdraaien. Ah, juist wat meer. Ja, je moet hem, als je een bepaalde zingende frequentie eruit draait, dan zingt hij niet meer. En dit is niet zo precies natuurlijk, maar je kan wel iets doen. Check, check. Check, check. Beter? Ik hoor hem nog steeds een beetje hoor. Maar je kan hem als je hem dicht bij je mond houdt, kun je hem zachter zetten. Gewoon zachter. Check, check. Ja, nou dit is een beetje zacht, maar als je nu ietsje harder draait. Ietsje harder. Ietsje harder. Check, check. Check, check.
Hij moet hem opvreten. Tata.
Test. Yeah, it works. Okay, thanks. Oh, yeah, now I hear it.
I don't have. Yeah, it's exactly 1 hour. So.
Can you do a quick mic check?
Okay, I'm okay. Fine.
Can you hear me? Yeah.
Okay. No. It sounds. Oh, okay.
Welcome back, everyone. Before we start, just 2 quick announcements. The bus tickets are downstairs. You can pick them up. Please don't forget to in-check and out-check. Get in the bus. You put the ticket in the machine before you get out. You do it again. Otherwise, you will lock your ticket. And lunch is downstairs also, especially for the people that are coming for the course. You can just go downstairs, grab lunch, and come back. And those were the 2 announcements. I will now give the word to Stephen.
Okay, thank you very much. Welcome everybody for this panel, a wonderful panel we will have today. This will be presented by my friend Christina Nader. She's from Google, but she didn't manage to come to Delft, unfortunately. So I'll be making her place, being her place. So I want to introduce three wonderful and very productive researchers in the field of computer graphics. And for this diversity panel, we have chosen the theme of women in computer graphics. So they will convince us about the importance of women's working in computer graphics. So just a small introduction of these wonderful panelists. So Zerrin Yumak is from Utrecht University, close from here. She is an assistant professor in Human-Centered Computing Group at the Information and Computing Science Department. And she's the scientific director of the Motion Capture and Virtual Reality Labs that was founded in EDA committee, and founding member of the EDA committee of her department. She has 15 years of experience in socio-interactive 3D digital humans. Her latest work focused on generative AI methods for motion synthesis, in particular non-verbal behaviors such as facial expressions, gestures, and gaze. Should speak a little bit more during his talk. Then we have Professor Zerrin Kademi. She's from here. She's from Delft University. And she's assistant professor in the Architecture and Built Environment, ABE, and co-director of the AI DAPT lab, AI for Design Analysis and Optimization in Architecture and the Built Environment. She has a long curriculum, and among different things, she was honored by the research in the Residence Fellow for the Royal Library of the Netherlands, working on visual recognition for children's book collections. So she's also a lot of interesting and remarkable works. And finally, Noshaba Chema. She is a PhD candidate at Max-Planck-Institute for Informatics and researches at the EFKI. She's dealing with animation for 3D characters using AI, computer games, films, and interacting with humans. So thank you very much for being here, all of you three, and we are delighted with this panel. I promise that since we have a very strict time for lunch, we will finish exactly at 12:30, okay? All right, so for the panel, we have selected 4 questions for topics that we will lead you talk about. But if we have time enough, at the end, we may open for comments for the audience. So my first topic will be, first of all, what are some exciting things you're working with right now? So in order to present and introduce yourself, maybe you can talk about that. So in order to follow some more criteria of ordering, let's perhaps start with seniority. And Professor Zerrin maybe can start talking about.
Thanks a lot, Esteban. It's a pleasure to be here, everyone, and nice to meet this audience. Well, admittedly, this is not the main conference that I usually attend, so a lot of the faces here are new for me. But yeah, it's very, very nice to be here today and talk about women in computer graphics and animation. But I'm looking at the audience and I don't really see many many women on the audience, just to start with, with that. My background is from computer science. I started with AI algorithms maybe 15, 20 years ago, yeah. And I did my PhD in a graphics VR lab, where I first got introduced to graphics topics. And I'm mainly working in the area of 3D digital humans. I earlier also worked on social robots, so in general, socially interactive virtual characters that are game characters or other type of embodied entities that can socially interact with people. So this is quite an interdisciplinary area combining AI, machine learning, deep learning, and graphics techniques. So my latest work is really focusing on data-driven approach, like a lot of people that is working on deep learning algorithms. So I'm developing deep learning-driven algorithms for generating animation for game characters. I'm mainly focusing on nonverbal behavior. So that means facial animations, gestures, like that is happening in a social interactive context, or gaze behavior for characters, to make these characters more believable, more with social presence in VR or in games. So for this, what we are doing is combining latest deep learning algorithms. We collect data in the motion capture lab. We are working with motion capture data mainly. But of course, there are challenges in this area because collecting data is not the most easiest thing. Even though you have all the setup, it's a very tedious process. And we are also looking into constructing data from computer vision, using computer vision methods and 3D construction methods. I'm in general teaching pattern recognition, deep learning, computer animation topics, but I'm mainly focusing on the social interactive part, even though I also do some work like regarding locomotion, for example, or other type of animations. I think that would be a start.
Nice,
yeah.
nice. I have a lot of questions, but I'm not
Yes.
going to make it now. Okay, Zerrin, please.
Thanks for the introduction, and thanks for having me. I'm happy to see you all here. My name is Zerrin Kademi, and my background is computer science, but I'm working at the Faculty of Architecture and the Built Environment here. I think if I go really back in time, I started with statistical signal processing. It was, I was doing my PhD. It was around 2013 when deep learning really took off, and it was really disturbing, I have to say. So I started looking at all this machine learning, pattern recognition literature, and it was quite obvious to me that I really want to move into that direction. It was sort of the pointer to the future of data-driven whatever algorithms. So all started from there, and I found images and videos and visual data fascinating because of the high dimensional nature of this data. So I started working on a computer vision lab here at TU Delft. And at the same time, I was very much interested into looking into the data, because as Zerrin also mentioned, with all this data-driven AI algorithm, you have to understand the type of data that is used to train and to develop these kind of models. And data by itself, it's a bit different than technology to me. So technology is very technical matter, however, data is social, technical matter. So you have to understand the context of the data and people who are actually working with data and generating and curating this data. So that was basically the point of the introduction to the world of architecture. We had a common project together with the Faculty of Architecture for understanding the visual data from architectural design, architectural drawings, buildings, images of the buildings, in the context of urban design, for example, street view images, satellite views, all these kind of visual data is there, and they are trying to understand it. And also generation is, I think, very important and kind of a trendy part of computer vision right now. How do we generate or visualize data? And if you look at the domain of architecture, perhaps a house is the most expensive thing that we might buy in our lifetime. So it's a very, I would say, expensive endeavor to go through the process of a design of a building and implementing it. So they need a very good visualization of design ideas. And I think in this context, computer vision and computer graphics are very important to help designers to bring in their design ideas and their imagination into present, so that they can present their ideas to people, to different stakeholders, not only the users, but also the policymakers, urban planners, etc. So I'm at a very interdisciplinary intersection of computer graphics, computer vision, and architectural design at the same time, computer science as an umbrella for this whole. So.
Nice, interesting. Yeah. Okay. And finally, Noshaba, please. Noshaba is the young researcher, probably the youngest in the panel. Thank you.
Hi, my name is Noshaba, and thanks for having me. Thanks for inviting. I'm also not really from this community, although I know a lot of people in this community. My main focus is also, just like Professor Zerrin, in animation. Okay, so I don't know how far I should go back. Since I'm an early career researcher, I guess I could start from a bachelor's or something, maybe. So I initially didn't really, I was initially kind of afraid of going into computer science. I wanted to do something with computer games or, well, computer, or like, let's say, game design. But then I thought, okay, maybe there isn't too much money in it or something. Then I looked into programming and I enjoyed it a lot. So I started with creating my own games. Then I started with creating my own game engine, then my physics engine, because I was so interested in that. And then my bachelor thesis was also around 2012-13 when the deep learning stuff hit, right? So it was about image synthesis, mainly about, synthesizing textures, essentially, but from a forward point of view, sort of. And then from there, I went into the master's program at MPI. And there I wrote 2 master theses, one in, motion segmentation, which got a Best Poster Award at SCA, and then another master thesis with Aalto University, which won the Telecom STEM Award about with reinforcement learning for animation, mainly about arm synthesis for, let's say, gesture synthesis. But now I am looking into full body synthesis, mainly looking into what can be done outside of data. So you are looking into like what can be done with data, right? But I'm more interested into novel stuff that is not within the data. For example, our recent submission was about synthesizing fatigued movements over time, and we did not capture these motions. These were all emergent behavior. These were all discovered by the agent itself. And my current project is going further into this direction, looking into what can be done, for example, with intrinsic motivation, which is a concept in reinforcement learning, based on, let's say, novel rewards or increasing entropy within the motion. And the difficulty there lies into how do we make this motion look still natural. So there can be a lot of diversity, right? Anything essentially can emerge, but how do you make it look natural for animators?
Okay, well, thanks. Now I'm going to the second question. I actually will put 2 questions in one. So I would like that you mention about what inspired you to become a researcher in the technology field. But if you, Noshaba already talked a little bit, but you could also maybe convince this audience what is the importance of having women in the field, in the research groups. Okay, so.
Shall I start? Yeah, okay. So first of all, what inspired me? I think it was a pretty natural process, I have to say. So yeah, I'm originally from Turkey. So, you know, when you are going to high school, you have to make a choice whether you go to the social sciences or the exact sciences. I was a good student, obviously, and I was more interested in exact sciences. That's I realized, I think consciously at an early age, that I want to pursue this line of studies. And I enjoyed it a lot, actually, which started my journey as an engineer. And at first, I didn't really have in mind to be a scientist. I always admired that, but that was not the first idea. I think many of you can relate to that as well, this choice between industry and academy. But then when I stepped into the world of science as a research assistant, I thought this is for me. It's really like curiosity, discovering things, and there's a lot of things to learn and explore. And I think I should spend my time, my life, on something more meaningful. That was a choice that I started to make at an early age, I think.
You mentioned to me before that you went to many different research centers during your life.
That is true, yes. I was in Turkey first. I did my master's there, and then I also did different majors, industrial engineering and computer science. And then I went for my PhDs to Switzerland. I was in the University of Geneva and the EPFL for my postdoc. And I went to Singapore. I have been in 2.5 years in Asia. That was a very interesting experience as well at Nanyang Technological University, one of the top engineering schools, together with EPFL as well. So that gave me, of course, a lot of different perspective, and I have met a lot of inspiring people on the road. So that was really, really nice to see. And your second question?
The second question was the importance about women in the field.
I think let's start with a little bit the challenges, and then I will turn it into why having women is important. So first of all, in this field, somehow, there is not enough women, as we see the audience here as well. This is difficult to identify. What are the reasons for that? I'm in the Equity, Diversity and Inclusion Committee of our department, and we discuss these things a lot. There are a lot of articles about this, why this is happening. And it's really difficult to find out. But I can say from my personal experience that from an early age, I remember, for example, when I was doing my PhD, there was like only 1 or 2 women in the whole lab. So that was kind of always the setup in engineering schools that I have been, and there was not really enough women. And I think there is a lack of role models in this area. So it's not only men or a certain group of people that can do engineering, math, science, or things like that, but there is more a need for role models, different type of role models, not only women, but a diversity of people are needed in this area. And the importance is actually, I think, we kind of reflect this area very well as well, because we work on interdisciplinary areas of computer graphics, animation, architecture. And that requires different type of thinking processes. It's different viewpoints, and different expertise is needed. And possibly, or probably, I'm not really sure of the answer, but maybe women are more into more holistic thinking, not only one type of task, but making connections between different areas. I don't want to restrict it to only women. I think there are a lot of very good male scientists as well that do interdisciplinary research, but somehow I think there is a inclination in that direction.
Yeah, I completely agree with you. Okay, Sarah.
I think that the first question was what
inspired you for?
Yes, I think if I really look back, it wasn't technology, so it was science. For me, it was a safe haven to understand the word. And stepping into computer science, maybe by chance, I realized that there is a small gap between product and science. So you can basically start your own product as you did also. Creating stuff easily with code, you don't have a lot of infrastructure, and I think it's nice for impatient people to actually see the outcome of science. So that was one way actually to close the loop, to see how science can contribute to the everyday life of people. And as I said, not only technology, but I think data is fascinating. I think how can we support different kind of decision making, and how can we use technology to make the world a better place, basically. That was a bit my, let's say, introduction to science and technology. And I'm very happy that here at Delft we have the opportunity and we have the chance to explore our curiosity with lots of support. And I'm very happy. I think there are lots of challenges of being odd anyway in any context, being a woman in computer science being one of them. But it's also nice to get lots of support. I mean, there have been challenges, but also opportunities for women in computer science. And this has been supported very well, I think, in the community, I can say. Coming from Middle East, definitely that's the case here. And I think, why do we need this? I mean, again, I'm a female in computer science, which maybe is a bit underrepresented, but going to the architecture, there is a better, let's say, gender balance in there. However, there's lack of international, I would say, students and researchers. So there's a different kind of diversity, and you see that when you have imbalance or underrepresentation in maybe in a very severe way, then you see that the one point of view dominates, and that blocks the way for creation and innovation. And that's why we need diversity. We need different point of view, being women, being people from different backgrounds, from different cultures, and that brings new way of doing things, because we have different brains, we have different trainings, we have different backgrounds. And I think it's important to have these point of views to avoid any sort of harmful biases at the end, because again, technology is really at the front end of what people use every day. And we want to avoid certain biases to make sure that everyone enjoys the outcome of our research, our efforts.
Nice. Thank you, Shaba.
Yeah, I mean, I talked a bit already about like what motivated me, but I can talk a bit more about this. So it's interesting because you guys said that you wanted to, like, you know, that technology interested you or science. For me, it was like art interested me. Like I always drew. I always like I started with like learning Photoshop or something for well, for character design, etc. I wanted to create my own game characters, and I loved gaming, and that's how I got into computer science. I never really thought that I would really be a researcher, but then, I don't know, I wanted to create my own, well, I started with creating my own engines, and then I wanted to learn more and more about this, like how does this stuff work? So through my own curiosity, I got into research. It was just natural. And what I really like about research is, that, for example, the stuff that I'm researching right now is basically, well, curiosity-driven learning, right? So with intrinsic motivation. And I mean, well, it combines a lot of things because, for example, I also love dancing. I'm a dancer. So I feel like dance is like the perfect use case for this type of, well, animation or work, because it is only intrinsically motivated, like almost only, at least when it comes to improvisational dances. And I feel like this is also like an example why a female mind sort of is helpful also like in this within this field, because a lot of ideas from reinforcement learning also come from psychology. And I led, in my first year, I led a grant proposal. It wasn't even a small grant proposal. It was a grant of 3 million euros, and the main focus there was social interaction in VR, and our main use case was actually dancing, because I wanted to make it about intrinsic motivation. That was just the perfect use case. It combines social interaction, it combines difficult movements, and combines creativity, intrinsic motivation. It was.
Okay. All right, so let's go for another topic, and then I'll open for the audience if you want to ask something. So it's what are some of the exciting things? What advice would you give to other women who are interested in pursuing the same career as yours?
Yeah, that's a good question to conclude. Okay, so what advice? I think I thought about it a little bit, of course, apparently before coming here, what could be useful for the audience. I think it's difficult to give a recipe, right? So it depends on the person. I think it really depends on you knowing yourself best, what you want to achieve in life, what you enjoy, where you want to spend your time. Things like that are important, but I think finding role models is really important. Like, try to team up with people, find allies, and enjoy the process together with these people. And if you are kind of distracted on the way, or there's some sort of things doesn't go as you are expecting, don't be discouraged about that. Put your goals and work towards this goal. Because sometimes you are not maybe talking to the right people. You need to find your people. The second thing I find really important, of course, is both male and female, but I think your close circle is really important. Who you are spending your life with. It could be your family, your partner, your close friends. Try to keep around inspiring people. That really helps you to achieve your goals and to enjoy this process at the end. Okay.
Yeah, I think those are very useful, I think, advices. What I can add is not anything specific. Just trust yourself, and the reason that you're doing something differently doesn't mean that it's wrong or it has to go inside, this norm that has been defined. Stay away from a stereotype. It's your own way. You can find your own way. And don't be discouraged, because again, it's about diversity. People think differently. They have different approaches. They have different understanding of the word. Yours is unique. So I'm sure if you put the effort and the interest that you think you find in yourself, you'll find some place that you can serve the community or your own interests. So don't be discouraged. Trust yourself.
I think these are very good advices. I think as long as you do something that you really enjoy and love, you're gonna get somewhere. That's what I think, right? So I started with art, but then I got into this field, and I really enjoy it. So.
Great. Okay, so I think now we have some time for the audience questions and points of view. Or you want to comment something else? It's more than welcome. There's a microphone for.
Thank you. I was struck listening, a bit embarrassed on behalf of this sort of field, that all of you mentioned that you were from adjacent fields, but not necessarily familiar to the sort of high-performance graphics crowd. And obviously, it's a very male audience. So my question is basically around what levers we can pull as aging out white, male people, what we can do to improve the diversity of opinions and backgrounds. The one that I was aware of before this talk was maybe people hiring. You look for different voices, you look for different backgrounds. But I was also struck by all of you talking about the interdisciplinary side of things. Is there something that the HPG community could do to improve those connections to other disciplines, and that might help diversity of opinions? And it's a general question, but I'm curious how we can help improve diversity.
That's a very interesting question. Actually, that's something the diversity track also is thinking during these years in HPG. So, well, do you have some comments?
Yeah, that's a great question, I think. It's of course relevant for this community, but in general to attract women in computer science. I have met myself very inspiring male colleagues on the way that are sometimes even more inspiring than female colleagues. So it really depends, right? So in the personality. I think what could be interesting is, I think, to have an open conversation with female colleagues. What are they thinking? What are their inspirations? What kind of contribution they wanted to give to the field, rather than just expecting the norm and be open-minded. I think that is the key in everywhere. So how these people can bring something different on the table. So I think that is the simplest thing to do, right? Have a friendly, open conversation. Yeah.
Right. This completely makes sense.
Yeah, I think the conversation is the key. But I think there's also this mindset and maybe a culture that needs to be worked on, is seeing the science as well as people doing science as a spectrum, not as categories, female, male, computer science, graphics. So we are really at the intersection of all these things, and seeing that, okay, some parts are maybe more easier to handle with more feminine approach than the other sides, and the same with solving a problem, whether this is really within the core of a discipline or at the boundary of different disciplines, and being open, because I feel, I kind of, I feel like this discipline thing, it comes really from our bottom of, identity that we have. If you work long enough in academia, I think that this feeling that, okay, I belong to this community, and it's difficult to sort of work on this fluid status of this identity. I think this is important to play with it a bit, to challenge yourself about the biases that we might have in different areas, whether it's about our discipline, is this computer vision or computer graphic, or is this visual, these kind of things, and being open to actually see it from a different angle. I think that helps a lot.
And that's coming from you that work in architecture. I mean, it's impossible not to do that, right?
Yeah, true.
I mean, a lot of things were already said. I don't even know what to say more, technically. Yeah, it's interesting to see, because generally when it comes to computer science, I think there are like 30% graduates who are women, right? But then here I don't see any women. So it's not even a third, or even just 10% or something. And that's a very interesting observation. And I feel like it's still a lot about, that maybe women need to also look and you have to get them more interested also into the hardware side, maybe, or the low-level computer programming side, maybe, and find beauty there, right? So.
What topics you think that if we include an HPG would attract more women?
Well, I mean, you already do rendering, right? So rendering is already pretty nice. It's just that a lot of the papers then also get accepted to SIGGRAPH or EGSR. Then some other synthesis papers are then also accepted to CVPR and ECCV, right? So when it comes to hardware programming, I don't know, how. I feel like if you visualize it super nice, if you're able to visualize it nicely, you will get a lot more attention. Yeah.
Okay. I think we have a question here. Dave.
I'm wondering if any of the three of you can identify a moment when you were inspired in a direction that led you here. So, to give us an example of how to inspire people who follow after us. So for example, I grew up with the mindset that in this family we get bachelor's degrees. Turns out that wasn't even accurate. Turns out none of my grandparents ever went to college, but both my parents did. And so I just grew up thinking, I'm going to get a bachelor's degree. That's what I'm capable of, and that's what I'm going to do. And then around the time I was finishing my bachelor's degree, my mother informed me that I could get a master's or a PhD. I'd never thought I was the type of person who could or would do that. And so she's the only person who ever told me I was someone who could go to grad school. So I'm wondering if any of you have any examples of inspiring moments that might help us spot such opportunities to inspire people in the future.
Yeah, absolutely. Yes, there are many moments, I think, like that. But the first moment for me was I had a university teacher. She was a very inspiring role model for me. She was a professor herself, and in engineering, and she was doing optimization type of work. And she was also manager in the academic area, you know, like department head, rector, vice rector, things like that. So that kind of really inspired me. I think the way she was able to carry herself in the academic world and position herself as a strong woman, that was a good moment. From family side, my parents were always very supportive. Coming from a Turkish background, I have a really, we are 3 sisters, so there was always support for women in my family. But admittedly, my parents didn't have any university education. So I'm a first generation student, which adds extra challenge on top of being a woman in this area. I can say that there were a lot of male and female colleagues on the way that inspired me, either in the way that they were supportive, or the work that they were doing was very, very inspiring, or I also get inspired by the work of people that I didn't know at all. That's also very important, right? Reading the work and getting deeply into the lives of these people, what made them come there. I read a lot of biographies as well from other people, which really, I think, kind of inspiring and helpful to find your way. So if you cannot find these people in the vicinity, look beyond. You will find them somewhere, especially in this era of connected world. Everywhere you will find them.
Well, for me, I think it was mostly intrinsic. So I've always looked what actually interests me and then trying to make that profile, somehow convincing people that this is what we need to do. But I think for sure, when I started going to the conferences, let's say from after my master's, and I saw people with different profiles, especially female role models, I think they were really inspiring me that this is a space for all kind of approaches to science, to mathematics, to programming, even though that the stereotype might look like different or they might act different. If you are passionate enough, I think you could. So I think it's important to have different role models here in this places. PhDs are coming here and then they say, okay, yeah, you could be that person that you want to be.
I guess for me, inspiring people came much later. Actually, when I started my PhD, so that would be probably Sebastian Starke or Jason Peng. You know, those are my role models. But before that, the motivation was mainly in seeing things move. So I wanted to always create my own worlds. So as soon as something worked, I was super happy. Or whenever my character walked or something, just that just made me super happy. Yeah.
Okay, we have one question there.
All right. Well, first, thank you for answering so many questions already. I wanted to ask, when I started my bachelor's, which was here at the TU Delft, in computer science, we had 5 women on a population of 300, so awkward. But I always noticed that that was not necessarily the case for adjacent fields. We shared a lot of space with the mathematics department, for example, where, to my understanding, that was not the case. Now, I don't know why, I haven't the foggiest, but I wanted to ask, are there other fields, or do you recognize other fields which might have at one point had this challenge, this diversity challenge, and managed to overcome it? Or are there other fields that you think we can learn from, like not necessarily saying mathematics, but any examples of this?
Yeah, just go ahead.
Well, I think I just mentioned, for example, architecture, especially artistic architecture, is quite female even dominated. But if you go up on the ladder, it comes to the managerial position, then you see again the bias starts taking off, which shows that still the evaluation system is set up to amplify those biases. So I think, and they are trying to bring in more female researchers into, let's say, higher positions in academia to be able to tackle this. I think all we know that this, well, positive discrimination is one way to sort of reinforce it, not only for female, but all kind of diversity is important. And I think the other way around, so maybe in some other disciplines it's the other way around, so it's more female, let's say, dominated, and then I think seeing and really bringing this, let's say, underrepresented people will help a lot. So if you see in dance lots of male dancers, I mean, then it's not odd anymore. It's not weird to be a male dancer. If you're a female engineer, a female computer scientist, and there are lots of them, then you see, okay, I'm part of a community. So this sense of being, like having this connection with the community is very important.
Yeah, I can yes add to that. Actually, in our department, when I started in 2015, I think there were like 3 women, something like that, and then our department started to hire a lot of female in the last couple of years, and we are trying to balance these numbers right now, which makes it a completely different environment. It's much more supportive. You feel much more at home. You enjoy more being in the department, things like that. So it has a very, very positive impact, I have to say. But coming up to your question on mathematics and computer science, what we can do there, I remember one report from some university in Australia working on diversity, and they were looking into this problem. Of course, it's a speculation, but it made sense a little bit. Computer science is a very young field. It started with programming, right, in these old days with like Microsoft garages, things like that, like a little bit of a different profile of the software engineers and programmers. And for mathematics, probably at the early ages, it was the same situation, but it's a much older field of study, and maybe things improved on the go. But computer science is still a young field, and I think we should do some deliberate efforts to attract women there, and there's not like a single stereotype that fits the computer scientist profile.
One more question?
Bit of a pipeline problem, and so do you guys have any ideas for how to attract young girls into this field, because it's almost too late in college, like not too late, but like it would be easier if people were interested earlier.
Yeah.
I mean, as I already mentioned, you know, the graduates in computer science, the female percentage is 30%, but there are not 30% of women here, so I don't think the college is too late, right? So you gotta sell the hardware component a bit better to, or like the low-level programming parts a bit better to the girls that are already in college in computer science until you get to 30%, and then you can think about what you can do in high school.
Yeah, something maybe I can add on top of that is, of course, we are always talking about what can we do for the girls, but I think girls can also think for themselves what is interesting in this field for me, and how I can see a relevant role model and how I can contribute to this field, like rather than just sketching a computer scientist profile that is very standard. If from early age, like even elementary school, you start with introducing the capabilities of computer science, computer graphics in general, and the beauty of it, right, from a more female perspective, and make it attractive for women. Because things that attract men and women are different things. That is the main distinction, I think. And at the early age, then women probably deviate to other directions. On top of there are like maybe other challenges like discouragement, things like that. So the women that usually survive in this field is, I use the word survive because sometimes it goes for survival category. You have to kind of find things that are motivating you on a daily basis in this field, at a personal level. I think that is very, very important for girls, for women in general, to think of.
I think I want to add something because I also started to thinking about maybe the way that we teach actually programming, computer and maths behind it. It's tailored towards a bit male brain. That's why we need to teach it differently already from elementary school. Why is that boys are more interested in maths? I mean, apart from the stereotype, maybe there's something in the... Now we know that there are different learner profiles. I mean, people learn differently, and maybe the way that we actually design this curriculum, it's towards reinforcing this bias, but we need data for that, and I think people should work on that part as well.
Yeah, actually on this note, I think if I had done a normal undergrad degree in computer science, my undergrad degree was in media informatics, so already a combination of, well, media design and computer science, right? If I had gotten into a normal computer science program, I'm not sure if I would have finished it. I'm not sure if I would have enjoyed it. In the media and computer science field, I started with programming games, or like with something visual that I could see, okay, it's doing something, right? It's giving me input or like some feedback. And that's what motivated my curiosity even more to look into this deeper, etc. Then through this, I got into, well, deep learning, and then, well, now reinforcement learning and doing a PhD in this field. I think if I had started a normal computer science degree, I'm not sure if I would have gotten here.
Okay, I think we are almost on time for finishing the panel, this wonderful panel. So I think I will just invite you to give a final message.
Yeah. Yeah, I think the final message for me would be that women should turn this process something enjoyable for them. Enjoyable and happy and learning and curiosity. So really try to find your thing, your place, and don't be afraid of being courageous and take the extra leap when you have to do. So if you have to learn hard stuff, you should also learn that. That's also important because there's never easy thing. You have to also feel the pain while learning things. So you have to take the extra step as well, but also enjoy the longer process. I think it's the same for everybody, not only for women.
Yes, well, if I look at the audience here, I would have a different message if it was a room full of female researchers, but I think we should do this together. So we need your support. We need you to understand the way that female researchers, especially in academia, can make their own ways. We are in charge of other things, among them reproduction as well. So I think it's important to understand that the situation and get enough support from you.
So weird.
Final message?
Yeah, my final message. Okay. Yeah, I guess my final message is really do something that you're passionate about, and in order to get more girls, well, I mean, making things attractive towards them, I guess that is something that we need to do. but I think there's something in this field for everybody, right? So you can, I feel like, especially nowadays, computer science or like computer graphics, let's say computer science, you can find your niche in anything. So if you love music, you can use computer science to do music, right? Or if you love, well, in my case, it's dancing, right? You can do that to synthesize dance, whatever. Or if you like gaming, etc. So there's something that motivated you guys to pursue this career, right? And there's something for everybody in this field. So that's my final remark.
Okay, thank you very much. And so let's give a huge applause for these wonderful finalists. Thank you very much. And after lunch, we will have this wonderful short course about Vulkan, so don't lose this, all you need to know about Vulkan. Okay, thank you very much. It's Lucas and Bernard here.
One very quick announcement before everybody runs out. So those of you that still struggle with the access to the wireless, there is an option to send an email with Wi-Fi as a subject, and then your name, first name, last name, and telephone number to registrar@highperformancegraphics.org. They will then send a list to Front Bali that will input this manually for you, because the technical service has not figured out yet why it doesn't work with foreign telephones or with some of the foreign telephones. So there are two options. You can either go to the Bali yourself, or you can send this email to the registrar@highperformancegraphics.org. Thank you.
Okay, awesome. Great. And I can have presenter mode? Yeah, should be. Hi. Hey, finally. Man, at last we meet. Let me just make sure, because I have my presentation open here. Hi. Super good to meet you. How are you doing? Nice. Yeah. I mean, it doesn't, so usually in this setup, it's not that easy, right? Now to bring out my laptop some nights, but I don't expect many people. So I'll just do it like a hybrid, and then where the source code is. And we have to check it out afterwards. But it's fine for everybody, for streaming, they don't go down. So there should be enough interesting stuff there, hopefully, for everybody.
All right. Hello. So, welcome everybody to the tutorial, HPG tutorial. We are very excited to have this Vulkan in 3 hours. So let's, first of all, thanks the tutorialist, Lucas Lipp and Berno Kerbel, I don't know how to pronounce it. So I will just introduce themselves, and I will introduce them, and then I'll give the word for them. Lucas Lipp is a third-year PhD candidate to IVN. His area of research centers around both real-time and offline rendering, with particular emphasis on differentiable rendering. Besides working on his own research framework, which is based on Vulkan, he contributed to the development of a Vulkan programming framework used in an introductory graphics course at UIVN, as well as for a hands-on tutorial at Vulkanized 2023 conference. He also gave lectures about Vulkan at universities and Vulkanized. Bernard is a postdoc please, Bernard. Yes. And Bernard is a postdoc at INRIA University Côte d'Azur in Graphic Deco Group. He obtained his PhD from the Graz University of Technology, followed by postdoc position at UIVN. His past and current research focus on point-based rendering, high-performance computing, differentiable rendering, and novel view synthesis. Bernard has taught GPU programming lectures at several Austrian universities. So these guys were highly recommended by the community to give the Vulkan short course. So we are strong. I mean, we are very happy to have you here today. And this guy, when we invited them to give this course, they said, we need 6 hours of course. What? 6 hours a whole day? And we said that 3 hours. Oh, come on, 3 hours. But then
you said 2 hours.
Oh, then we went to, but then you claim it, and we'll give you 3 hours. Okay. So okay, thank you very much, and I hope all of you have a nice tutorial.
Yeah, thanks for the introduction. So we will today talk about the gentle introduction to Vulkan. First of all, what is Vulkan? Wikipedia says Vulkan is a low overhead cross-platform API open standard for 3D graphics and computing. Especially compared to maybe OpenGL, the low overhead aspect is very important here. So what actually means low overhead? It means how much code sits in between the calls from the user and then the actual execution on the GPU or the device. And Vulkan is in this sense very low overhead. Vulkan is already in its third version. We have 1.3. It's a C API, and it's very explicit. This is in comparison to, many of you probably know OpenGL, which is not as explicit. There's a lot of magic happening in the background, and with Vulkan this is not the case. And it's more like a high-level hardware abstraction layer. That is maybe one of the points that makes it so difficult. But the developer has all the controls. So the idea behind Vulkan in the beginning was to shift all of the complex logic out of the driver into the hands of the developer. And it is community-driven, so everyone can participate and bring the standard forward. If I'm allowed to cite Chris Clover from last year's Vulkanized, where he cited himself, Vulkan is a broadly implemented specification that provides APIs to program accelerator devices. And that's kind of true, because Vulkan is becoming a central hub for instance, graphics API, for graphics, as most of you know, but it is also a GPU API. And recently it also is becoming a video encoding and decoding API. And maybe in the future it will become a machine learning API too. When Vulkan launched, it only had 119 commands, and with Vulkan 1.3 it now has 200 commands and over 180 extensions. And this brings us to the support for Vulkan. It works basically everywhere and with everything. On desktop, on mobile, on Apple hardware thanks to Molten VK, which is a translation layer, and also on low-end devices like the Raspberry Pi, for instance. It allows exchanging resources with OpenGL, CUDA, DirectX. For instance, you could use Vulkan as a front-end for your GPU application in CUDA. You can launch CUDA kernels from within Vulkan. Sadly, it's not documented yet. But this is, I think you can also debug this already in Nside. And you can, in general, mix graphics APIs. A good example is Crysis Remastered, which uses DirectX 11 for rasterization and only uses Vulkan for the ray tracing effects. Another important aspect is extensibility. So Vulkan comes with a very customer extension system. It does not require special vendor tools or intrinsics to allow these extensions. Extension has the form of such a form, like it starts with the VK namespace, then the author, and then the extension name. So there is quite a complexity in the notation, but KHR stands for Chronos extensions, EXT stands for extensions that are mostly developed by multiple vendors, and often the Chronos extensions get integrated into the next version of Vulkan. But there are also vendor extensions, for instance, NVIDIA, AMD, Qualcomm, or Google. There are experimental extensions like KHX, which is the counterpart to KHR, or NVX, which is the counterpart to NVIDIA's extensions. And there are instance and device extensions, which we will see later on. Another very cool feature is layering. So it allows you to intercept all the Vulkan calls. It looks like this, where the loader forwards the function call to the ICD, or if there's a layer activated, it forwards it to this overloaded function, and then it passes through to the ICD. ICD means installable client driver. And you can overload one of them, all of them. You can really mix this. So this is useful for validation. Most notable the validation layers, where you can check if a function is correctly called. You can layer Vulkan over another API. You could call DirectX in the background or something. And for monitoring and profiling, you could track the memory that you allocated, for instance. And the notation for it looks basically the same as with the extensions. Just you replace the extension, you add layer to the string, and then you have the author and the layer name. There's a pretty cool website where you can check all this, all the features and probabilities. All the features of the devices that Vulkan supports. And you can check for extensions, there are layers. You can check what formats are supported. And this is a pretty huge database. And we will use this in the examples later on quite a lot to get different types of information about the device. So Vulkan in the wild. What are great applications out there that use Vulkan? Maybe the holy grail of a Vulkan application, a Vulkan game, is Doom Eternal. I've never seen a game that is this optimized. For instance, ultra settings, 4K without ray tracing, you get 60 FPS on RTX 2060 or over 300 on 4090. I really would like to see this game run on a Raspberry Pi. Another example is Red Dead Redemption, which came with a DirectX 12 backend and a Vulkan backend, and people reported that they get more frames with the Vulkan backend. And most recently Proton, which uses Vulkan as a way to translate DirectX 12 calls and older versions of DirectX to Vulkan. They use it on Linux to play Windows games or on the Steam Deck. And most modern games seem to work pretty flawlessly. So let's talk about today. All of this started when my dear colleague Johannes made this Vulkan lecture series on YouTube. Maybe some of you know this. And this happened because we tried to transition from our OpenGL only introductory course to this to a optional Vulkan flavor of it. And then he wrote an educational paper about this, and the second one, and then Kronos contacted him if he would like to hold a tutorial at this year's Vulkanized, where we developed this educational framework, which was also used by our introductory course. And we got pretty good feedback there. And then today happened. So today's agenda is we will talk about basics first, then some rasterization, ray tracing, and then Bernhard will take over and will do some compute and maybe also some more in-depth stuff on some things that I just briefly talk about. There will also be optional homework if you're willing to do this. It's based on the Vulkanized tutorial, so and on the Vulkan Launchpad that we created for this. You can just join this Discord, for instance, and since we also use this for our lecture, our university course, please keep everything private, especially the solutions. Yeah, just join this Discord. There's some text channel where you can insert your GitHub name, and then we will invite you to the repository that contains the task descriptions. The Vulkan launchpad itself is open source, so it's just because of the task descriptions. And there will also be optional compute homework by Bernhard, which is a suite of 12 compute tasks. And yeah, you can get it also through the Vulkan Discord, Vulkanized Discord. And please also keep the solutions private. The restoration homework should require you about 4 hours. It's 4 tasks with 1 hour each, and the compute homework is 1 hour per task, so 12 hours, which seems like a lot. So before we start, Vulkan is a shared library. There are stubs for Windows available. Usually you load these functions. You need to load the functions from this dynamic library. You load the library, then you load the entry function, then you load the global functions where you get an instance, then you load the instance function, and then you load the device functions. But luckily you don't have to do this because there are better ways to do this. For instance, Vulk or the Vulkan HPG bindings, they all have function loaders included. So how is this Vulkan API designed? I would say 90% of the code looks like this, where you have some struct that describes or is for settings, and then you have a function which takes the structs and does something. And it gives a result, you check the result, and if this is successful, then you get the handle, for instance, in this case, the instance handle. So there are 2 fields in the struct that are present in nearly every struct in Vulkan, which is the S-type and the P-next. And the S-type is important because you can cast a void pointer basically to the correct struct. And the P-next is important because you can chain structs after each other. So if some extension comes out that adds some new features and you need some new settings, you can just add the pointer to a struct, to a pointer from this configuration struct to this already to this original struct. And of course, always initialize the struct, because it could happen that you have some values in there that are not 0, and then you get weird errors that are sometimes hard to find. There's a second pattern, which is the VK command function pattern. This means these functions are only there for recording commands to a command buffer, and they always these functions always take a command buffer as the first input. And this is maybe something that is easy to forget, especially when you're working maybe with CUDA in its most easiest mode, that the communication between the host and device is mostly asynchronous. That means both of these devices, the host and the device, can run simultaneously. And you try to feed the device from the host side, and you don't want that the device starves because it doesn't get enough work. And this is sometimes not easy to do. Also, always activate validation layers when you're developing, because in this example, it's hard to see what is wrong. And even the function returns success. But the validation layers say we need to set the depth to 1. But it is 0 because we 0 initialized it. And this also gives us a link which we can look up online. And we fix this and everything is all right. So, are there some questions already? Then let's continue. So let's start with the setup. We need to get a hold of all these handles in order to start doing serious stuff. we start with an instance, which is our current Vulkan context. This is the complete code that you need to create this instance. It has the same pattern that we already saw before. But here we pass another struct into this struct, which specifies the Vulkan version. And we also need to specify the extensions that we want to use. And one good thing about the Vulkan version is that if you choose some specific Vulkan version, then you also get all the structs that come, all the extensions that come with this Vulkan version. Because sometimes extensions get promoted and then are included in the next Vulkan version. And we also activate the layers. We create our instance, and we're basically done. So now we need to select the device, and for this we call this physical devices. These are the devices that are actually in your system. But we can have multiple of those, and other APIs like OpenShell sometimes just select a device on its own. But in Vulkan you need to explicitly select one device. So we could use the dedicated GPU number 1, but we could also use dedicated GPU number 2 and just use the first GPU to display this stuff. We can use both of them, so they share the work. Or we could even use the iGPU and use 3 GPUs. So we start by curing all these device handles, or these physical device handles. This is also a common pattern in Vulkan, where you, when a function returns some array, then you first pass only a pointer to an integer and no pointer for the actual data. Then you get the count of it, and then you can allocate the array with this size and then pass this array pointer again to this function, and then you get the filled in, or the array with the actual data. And we do this to get all of the physical devices in our system. We can use this handle to cure many different properties of the device. There are really 10 or 20 such functions. You can get memory properties, you can get format properties, you can cure what extensions are supported, what layers are supported. And then based on this information, you can choose one of these devices. In this simple case, we would just use the first device, because it does not matter for this example. Oh, I forgot to click. And here you can see all these different, and there are even more, but these are all the functions that can be used to get features and properties of the device. So another important aspect is the queue, because the queue is used to execute commands. And when we record commands, they get recorded into a command buffer, and the command buffer is then queued for processing. And we can see this in this example. The command gets executed by the queue. We can also submit multiple commands, or multiple commands can be submitted. And commands are processed in an independent order. So a command that is first queued could be executed last, and this can be a problem because it leads to memory races, for instance. We can also submit from multiple threads, but in multi-threading submissions we need to have multiple queues, because one queue can only be submitted from one thread. And this is one advantage over, for instance, OpenGL, which made it really hard to do multi-threaded command recording. So what is a queue? And it's not so simple to say, but a device has multiple different queues, and so to say, multiple different queue families. And each of these queue families has different properties. For instance, some of these queue families can present. That means you can present an image to a window. Some of these queues can do graphics operations, some of them can do compute operations, and some of them can do transfer operations. Some of them can all of those. And the less specialized the queue is, usually the better it is for these operations. But we don't know for sure because this stuff happens in the driver. And you can only get a certain number of queues from this queue family. And we can look this up from this website that I told you before, which has all this information. So just a bit of code. We would set the queue family index and the amount of queues that we want to queue. And then we would pass this to the device creation info struct. And that's it for now for the queue, because the rest happens when we create the device. So there's a bit more. And we also need to activate extensions if we want to. And then we pass this struct again into the create device function. And if everything works out, we get a device handle. And this device handle is quite important because we will use it for everything that now comes. And so we only activated the queue so far, so we also get to get the queue handle back, and this is done by this function with vkGetDeviceQueue. Yeah, it's not so important. So, and here's a summary quickly. What we did so far, we have created a Vulkan 1.2 instance, which has these 3 physical devices, and we created a logical device from one of these 3 physical devices, which has a queue and some activated extensions. And you can see if we would have made or created a Vulkan 1.3 instance, it would also include these extensions on the right too. So far, any questions? Yeah.
To make sure that that happens, or do you just wait for the operation to complete and then?
We will talk soon about barriers. So there are ways to synchronize. There are ways to synchronize on the GPU with the CPU, and between different queues, and yeah, there's a lot to talk about synchronization.
Maybe one short question. You mentioned that the more generalized a queue is, in general, the more better it is at doing a lot of things. And what is a transfer queue or a copy queue or whatever it's called?
So the graphics queue is for rasterization tasks. The compute queue is for launching kernels, and the transfer queue is for copying data. You can copy data from a buffer to another buffer, for instance, or from a buffer to an image. Such things are transfer. But we will talk about memory shortly. Right. So I think we continue. So now, since we have our device created, we can start with working with that device. And there are multiple different resources that we need or can use, and we will start with the memory, which is the most fundamental one, I think. So, allocating a memory is quite easy, but there's this one field, memory type index, which makes this a whole lot more complicated. So what is the memory type index? A GPU has multiple different memory heaps, and we can have device local memory, which is memory that is only accessible from the GPU. We can have host visible memory, which is accessible by the host, and we can have device local memory that is also host visible. And again, some information from this website that I mentioned. And here we can see we have around 6 gigabytes of device local memory, but we also have host visible memory. This is the memory heap 1, which says none. And the size of this heap depends on how much RAM you have in your computer, because it's memory that is on your RAM, but the device can read from it. And recently, there's also this device local memory that is on the device, but is readable from and writable from the host. This is the memory heap number 2 here. And this, for iGPUs, for instance, this is often called unified memory, because the iGPU shares the memory with the CPU. And on dedicated GPUs, this is often called bar, which is base address register. Bar is not that new. I think AMD GPUs were the first that used this, but they could only address 265 megabytes of the memory. And now, I think since 2 years or 3 years, they support also this resizable bar, which allows the CPU to access the whole device memory. But for now, I think mostly you need to activate this in the BIOS. And also, I think mostly all vendors support this now. So, now that we know about heaps, how do we create a buffer? So first we need to create the buffer, and then we can use this buffer to get the memory requirements that we need for this buffer. And we get this VK memory requirements struct back, which has some content which tells us what this memory requires. And when we use the physical device handle to get the memory properties of our device, we can compare these and find the correct memory heap that we should use. This find memory type index function, which is the custom function, does that, but you can find some implementation of this function in the Vulkan specs. But it just goes over all the memory heaps, compares some bits and some flags, and then returns the correct memory index. And then we allocate this actual memory, and we bind it to the buffer. So a buffer is backed by some memory. But normally you don't do this yourself. You can use the Vulkan memory allocator for this, which is a library that simplifies memory allocation. And when we have device local memory, this gets loaded into the L2, L1 cache, and then the individual threads can access it. So host visible memory is good for data that is often updated, maybe also more on the smaller side, while the device local memory is better for fast data access from the GPU. For instance, images, most of the times you don't write to images that often, only the GPU uses it, and then it's great for that. Now let's talk about images. They are basically the same as buffers. At least when you create them, they are similar. Here we have the buffer creation code again, and this is the image creation code. So instead of the buffer create info struct, we use the image create info struct. This, of course, has different members. For instance, you set the extent. This is the size of the image. And you also set the initial layout. We will talk about layers shortly, but for now, let's look at the vkget image memory requirements. In the previous example, it was vkget buffer memory requirement. This time it's image memory requirement. And on the bottom, you can see bind image memory. And in the previous one, it was bind buffer memory. So these layouts are quite So these layouts are quite complicated, but there's also tiling. So when you read an image on the CPU side, it's probably tiled linearly. That means that the rows are one after the other in memory. And this is not very good for the GPU access, because on the GPU, you often want to have the 4 adjacent pixels so that you can interpolate them. And when we transfer this buffer on the CPU side to the device local image, we can change the styling. We can change it to tiling optimal, which has exactly this property that neighboring pixels are close to each other in memory. And when we access this image somewhere in between these 4 pixels, the GPU reads these pixels and then, for instance, filters them when you use a sampler. But there's also the layout, which we can change. And before, we had image layout default, which is default. And for memory reads from the GPU, it's better to have the image layout as shader read optimal. It's not really clear what the driver does in the background, but you could think of it like this. If you read memory, this memory needs to go over the bus, and this requires bandwidth. And when we kind of compress these pixels, we can move more data over this bus. And this shader read optimal probably compresses the pixels in a way. And you can't always do this. For instance, if you write to this texture, maybe this compression makes it more complicated to write to this image. So you, depending on the use case, you would change the layout of these images. And this is something that, for instance, OpenGL also did not have. And that makes it a bit complicated. So, and then the pixels get more easier over the pass. So, we don't specify the exact memory layout, we just specify the usage scenario. In this case, it was shader read optimal, but there's also one for transfer source or transfer destination. So when you read from a buffer, or when you write from an image, when you read from an image, or when you write to an image. And hopefully the vendor does the right thing. These are some of the image layouts that exist, like transfer source optimal, transfer destination optimal. So, as in summary, we have different image layouts. What your GPU might do, we don't know exactly. It could do nothing, or it could reduce data or compress data to reduce the required bandwidth. There's image tiling. It could be in a linear memory layout, or it could use Z ordering. It could, in the worst case, it's the same as linear. So what exactly happens, only the vendor knows. There are 2 ways to access the content of an image. One is VK image view, and this is used when you access the exact pixel coordinates. Let's say our image has an RGB layout of the pixels. We could use an image view to change that so that we read PGR, so with blue as the first component. So an image view allows you to swizzle, for instance, pixel components or adjust the sub-resource range. We could have 10 mid-map levels, and maybe we only want to use 5 of them, so we configure that in the image view. Or a VK sampler, which basically filters the image for you. We can use a nearest neighbor filter that gives us the color that is closest to the query point. Or we can use linear, which just interpolates them based on the 4 pixels. We can do even more with a sampler. We can access an image through the use of floats from 0 to 1. We could also change that to 0 to 10 or 100. As we saw in the example, we can filter it during access, and we can specify out-of-bounds behavior. For instance, if we read the pixel out of its range, if we read the image out of its range, we can say repeat the image or mirror repeat the image. So now command buffers. command buffers are very important for recording commands, which are then executed on the GPU. So when a command buffer has some commands recorded, it gets submitted to the queue, and then these commands get executed. But how do we allocate such command buffers? We need a command pool for that. So a command pool is always linked to a specific queue family. And then we allocate command buffers from it. There are two different types of command buffers: primary command buffers, which can be directly submitted to a queue, or secondary command buffers, which can be called from a primary command buffer. And this is the life cycle of a command buffer. You first allocate it, then you begin the recording, you end the recording, it's ready for execution, you submit it, it's waiting for its execution, and when it's complete, it's back in executable state. You could submit it again, or you reset it. And the good thing about command pools is that you can reset all of the command buffers that you have allocated from this pool at once. And in code, this looks like this. We start the command buffer recording, we end the command buffer recording, and in between, we can record commands, like binding a descriptor set or issue and draw commands. Now let's talk about shaders. Shaders are programs that run on the device. It's a piece of code that gets executed on the GPU. There are two ways you can write. There are two mainstream ways how you can write GPU code in GLSL or HLSL. GLSL was also used by OpenGL back then and got extended for Vulkan. And HLSL is the language that is used by DirectX. As you can see, there's a Vulkan-flavored HLSL version or notation where you specify the binding locations and so on through this double column things. And this is a very easy code that just copies data from a buffer to another, to the same buffer, but multiplies the value by 2. So Vulkan consumes SPIR-V binaries. SPIR-V is an intermediate language, and the driver does the rest. So you have this high-level language, which is HLSL, for instance. It gets compiled to SPIR-V, and then it gets passed to the driver, which probably translates it to ISA, which is the instruction set architecture for the GPU. So the good thing is everyone can write a compiler, even when the ISA is not public. Luckily, you don't have to, because there's GLSL, which is the reference compiler for Vulkan, and there's also the DirectX shader compiler, which nowadays also has a SPIR-V backend. So the GLSS shader code gets compiled by GSLAN to some SPIR-V binary, which we can then use in our shader module creation struct, where we specify the size of the binary and pass in the code array. And then we can create the shader module, which we then later use when we create our pipelines. But for now, let's talk about the descriptor sets, which is a collection of resources that we want to use in a shader. So one descriptor describes one resource, and descriptors are organized in descriptor sets. And each of these descriptors in the descriptor set has a given binding index with which you can access it. And these descriptor sets are allocated from a descriptor pool. And the layout of the attachments that the layout of the descriptors, or the types and the order of these descriptors in the descriptor set is described by this descriptor layout. And in shader code, we would access these resources by using set equals some index, because we can also bind multiple descriptor sets, and then use the binding index to access the right one. Here we access a uniform buffer, which is binding 0 below. And in this buffer, we can save some matrices and some vectors. So, as I said, we can use multiple descriptor sets, and descriptor sets are bound during command recording. And multiple sets can be bound. So we would call vk command bind descriptor sets to bind the descriptor set, and then vk command draw to draw using this bound descriptor set. And in this example, we submit the command buffer to the queue, and the first command gets executed, or the first command, draw command gets executed, uses descriptor set A, and then the second vk command draw gets executed and uses descriptor set B and C. So the default way is to allocate from descriptor pools. The programmer manages the memories kinda manually. You need to specify how many descriptors you want to allocate from a descriptor pool. So there's an upper limit for that. But there are other ways to do this. For instance, with push descriptors, which store the descriptors inside the command buffer. And there's a maximum, and you can also queue this from your physical device if you want to have the exact value. But normally it's 32 descriptors per command that supports descriptors. But there's also descriptor buffer, which is maybe the most flexible one, because you can allocate your memory yourself, or the memory or you can manage the memory completely yourself. So you can move descriptors in memory as you like. It's just a VK buffer. And another important extension is descriptor indexing, which does many things, but one of the most notable ones is that you can use the last descriptor in a descriptor set with variable size. This is very helpful, especially for ray tracing, because you need to have access to all of the images of your whole scene, and this allows it. Maybe you remember with rasterization, you often bind one texture, then draw something, bind another texture, then draw something other. And you always have only one texture bound. And yeah, this is very nice. Now let's talk about push constants, which are kind of an alternative to using descriptor sets for small data. It allows to quickly update data. So, as I said, it's an alternative to reading data from a buffer using a descriptor set, which is also kind of an interaction, because you have to create the descriptor set and then you need to access the buffer. And with push constants, you can directly embed the data in the command buffer. The size is very limited. It's at least 128 bytes. But it's 128 bytes for every command that supports push constants. And the only commands that support this are pipelines, but we will talk about pipelines soon. And writing to this push constant buffer is not so trivial, because you need to manage the offsets yourself. For instance, here, if we want to update this float value, we would need to use an offset of 16 bytes and then overwrite 4 bytes with our new float value. And these push constants are recorded or set during command recording. And then this whole command buffer gets sent to the queue and executed. And in GLSL code, it looks like this. We specify this layout push constants. And then we have, for instance, a matrix. A matrix is a good use case for push constants, because the model matrix, the view matrix, updates every frame. There's also the possibility of adding offsets to this description, if you have a more complex layout, maybe. So now synchronization. I will not go into too much detail here, but because it's a really complex topic. But for a simple example, this should be enough, I think. So we have 4 commands. We have an image, and the first command writes to this image. The second command writes to this image. The third reads and writes to this image, and the last one only reads. Now we have a lot of threads running simultaneously, and the order is not given by, from just this the steps that we the order that we use for recording these commands. So we need some other way of synchronizing this. And this synchronization is called pipeline barriers, where we can put in between these two in between commands. We can add dependencies. For instance, that reads can only happen after all writes are done, and then or writes can only happen after writes are done in the stage before that. So these are pipeline barriers, but this is a very rough synchronization, because we just say that one pipeline stage can only happen after another pipeline stage. But we can make this more more precise when we add memory access flags or memory access settings to it. So we could say compute execution that writes some memory can only happen after a compute execution that reads this memory. Another thing that these pipeline barriers can do is they can transition the image layout. So here we want to copy a buffer to an image, but the layout of this image is undefined. It would be much better if this layout would be transfer destination, because we write buffer to this image, so the image is the destination. We can set a memory barrier before that call, which then transitions the image to this correct layout. Then the command reads the buffer and then writes the content to the image. And after that, we want to access this image from a shader, so it would be better to have the layout as shader read optimal, and we can do this with the memory barrier afterwards. So, but there are many different ways to synchronize commands, and we spoke about pipeline barriers now, but there is maybe the most brute force one, which is just VKQ wait idle or device wait idle, where you just wait for the device to be completely done with all work. There are fences which can be signaled on the device, and the CPU can then wait for this signal. There are semaphores which can be used to synchronize across multiple queues, or you can submit a command buffer and say, when this is finished executing, signal some semaphore, and you can specify with another submission, you should wait on this semaphore to get signaled before you start executing this command buffer. And render pass subpasses, which we will talk later during the rasterization part, and events. So, until now we haven't talked about how we display images to an image. Display images to a window. The core of Vulkan does not provide functionality for this. We have to use an extension for this, and this is called the swap chain extension. And the method that we use is the swap chain, which is just a queue of images. And here, without a swap chain, you would draw to an image, you give it to the operating system to present it. You and then you would get it back, and then you draw it again and present it. But this is kind of slow, and this is not in favor of this asynchronous computing that I talked of in the beginning. In a swap chain, you have multiple images. You can acquire the next image, you can draw to it, and then you can give it back to the swap chain for presenting. And while this image gets presented to the screen, we can already ask for the next image and render to it. So we get the next image, we draw to it, and then we present it. And this allows for utilizing the GPU as best as possible. In this case, we had 2 images, but you can use also 3 images, for instance, which makes this even better. The problem maybe is that you could have outdated frames. Yeah, but enough of that. So, and now where everything comes together is the pipeline, which is a collection. I would say it's a collection of execution states. You have some pipeline settings that are specific to that pipeline, but all of the pipelines in Vulkan share the same architecture. You have shader modules that describe the shaders that you want to use. You have descriptor layout, which describes the descriptor that this pipeline will use. And you have these push constant ranges that describe which push constants you will you want to use. All of this doesn't, the descriptor layout and the push constant ranges do not contain specific data at this point. It's just a layout so that the pipeline knows how to interface with them. And then you would bind this descriptor set, bind the pipeline, and set the push constants, execute the draw command, and send this to the queue, and it gets executed. So, any questions until now? Yeah.
You were talking about the overlap of rendering work for different frames when you were talking about the swap chain. I tried to get this working, and when I profiled it, I always saw a gap in utilization between frames and no overlap at all. Are there any common pitfalls that you know about with that?
There are I don't know what's it called, but there are different ways of presenting them. You can, like, first in, first out. I think one is called mailbox.
I had been playing around with that, though. And
say again?
I had been playing around with that. I tried various things. I could never get this overlap working.
Okay.
Maybe we can talk about it some more after the presentation. Yeah, sure. But I'd be curious if you have any insights there.
What operating system did you use?
Mostly under Linux, but I think I also tried it under Windows.
Okay. Because I knew of an issue on macOS back then, where they used this molten translation layer, and there were some features missing in Metal, and then they had this star somewhere in between. But sorry, I don't know the exact issue for that.
I'll hunt you down later, and we can talk about it a bit more.
I have a question. Yeah. If you go back just to the previous slide, where you have these commands, you said earlier commands do not retire simultaneously or in order, right? So theoretically, the command push constant could overtake the draw command. How do I make sure that the command push constant is not overtaking the command, the DK command draw, or is this just something that does not happen for those types of commands?
Exactly, it does not happen for these types of commands. I think it's because it just sets the state for the next command. For the next draw command. But yeah, for these commands you don't need to.
Okay, so they are implicitly synchronous or within the command queue?
Yeah, probably, yeah.
All right.
I already thought about this, but I have no precise answer to that, sorry.
Hi, thanks. So I had a question about something all the way back about buffers. So you have a whole, yeah, no, I didn't want to interrupt. You showed that for I think, an image that was in device local memory that it would use L1 and L2 cache, right? For host visible memory, does that also still utilize the GPU caches, or does the GPU read straight from the host visible memory without any caching?
There are different modes to that. You can have it cached on either side, but normally the GPU would then go over read this data over the PCI bus.
Okay.
So the memory is located in RAM, for instance, and the GPU would then read it over memory bus.
And if I would read it, for example, in a loop, so I would read the same address multiple times, would it keep going to host visible memory, or just read from host visible memory once, then store it in the L2 or L1 cache, and then subsequent reads would go to that L1 cache?
If nothing kicks it out of L2 or L1, then it should stay in there, I would say.
Okay.
But if you do some other stuff in between, then the chances are pretty high that it...
Yeah.
Yeah.
Thank you. Thanks for the talk so far. My question is about the SPIR-V files. So I have SPIR-V files compiled and located next to my binary. Do you have a best practice or an idea of how I could put all of that into one binary so for my users or customers to not always have being forced
one solution is GLSL, how do you call it, GL slang, has the option of compiling the shader into a header file that contains then the binary as a uint32 array, I think.
Mm-hmm.
So you could just compile it into the header and then include that into your code.
All right.
That's one way of doing it. I think on Windows you can include resources in your exe, the executable.
Okay.
That would be another way, maybe.
Uh-huh.
Yeah, but
thank you.
Yeah, or the third way would be that you have the source code as a string in your C++ program, and then compile it with a runtime compiler, and then you can just use it when you compile it during runtime.
Okay, thank you.
Thanks. So I don't use Vulkan yet. I'm still stuck in the swamp that is OpenGL, unfortunately. But I just wanted to ask if you could maybe clarify on the out-of-order execution of things in a command queue a little bit, because it's called a queue, and things tend to go in the queue and out of queue. Wouldn't it instead, maybe there's some confusion going on, wouldn't it be the case that commands are processed in order, but because the GPU being smart and doing out-of-order execution and things may be finishing earlier, that you don't guarantee what finishes first?
That's a good point.
Right. Then maybe a follow-up question, because I was curious. I was reading the Vulkan 1.3 update notes, and again, I don't use Vulkan yet, unfortunately, but could you maybe expand a little bit on how pipelines have changed since then?
We will. I will now talk about the rasterization pipeline, and there we talk a bit more about pipelines.
Cool.
Yeah. But that's, I think, a good point, that maybe they start at the same time, or start in order, but just finish out of order. But sometimes it's a bit of a guessing. Okay, then let's continue.
Yeah, I think just one comment on the recording on the commands. From what I understood, it's when you record it, it matters in which order you put them in, but once you start executing them, they can be in any order. So, for example, with the push const, etc., that kind of gets lodged together with a draw command or a compute command that preceded it, but once it starts executing, I think, it can go in any order.
That would explain also this binding of descriptor sets and But thanks. Okay, then let's talk about the rasterization. So in Vulkan you can do rasterization, you can do compute, you can do ray tracing, and all of them use different pipelines. And here we will talk about the rasterization pipeline. And the rasterization pipeline or graphics pipeline consists of multiple stages, which are listed here. And when we execute a draw command, the vertex data that we put in goes through all of these stages. Not all of them are active. You can configure this, which ones are active. But let's say we draw this triangle, the vertex processing would move this triangle around, scale it, and then it gets sent. And this is done by the vertex shader. So there are some parts where we can insert code that then does what we programmed it to do. And then it gets sent to the tessellation stage, where you can subdivide the mesh, then to the primitive processing, which is also often called the geometry shader, which allows you to duplicate geometry. And after that, it goes to the rasterization stage, where the vector kind of representation of this triangle gets then discretized to actual pixel colors. And depending on how this triangle is visible to the camera, different pixels are then shaded or marked as need to be shaded. Then we continue to the fragment processing, which can also be custom programmed by a fragment shader. And here we can implement shading, for instance, by a light source. And then the pixel processing stage just writes this to a buffer and gets sent to the frame buffer for instance, display to an image at some point. So how do we get this triangle data into our pipeline? We need to use a buffer for that, where we upload the vertex data. And when we execute the draw command, it goes through, in this case, the vertex shader and the fragment shader, and gets then displayed. So how do we specify this? We have these structs again, where we specify the stride, so how much memory gap is in between the actual data, and how this changes. So for each additional primitive that we process, we jump this stride in the buffer. And in the shader, we can then use this location index to for instance, in the vertex shader, we then get this data in, and we read that from the correct location that we set in this input attribute descriptor struct. And we also specify the memory, because the stride on top is just for moving around in the memory, and the format is then actually reading that memory. So this is the vertex shader here. We read from location 0 our vertex data. We read from our descriptor set 0 with the buffer at binding 0. We get the transformation matrix, which is then multiplied with our positions that we got and set to the GL position built-in variable. And then we continue to the fragment shader, which also takes in this uniform buffer, but this time we take the color and we write it to location 0. And what this means is we have some frame buffer bound, and this frame buffer can have multiple attachments, and each of these attachments can be accessed through this location. And location 0 just means that it's the first attachment in this fragment buffer. We will talk about fragment buffer shortly. So we can have multiple different graphics pipelines. This one uses all of the stages. This one uses only some of them. And this one uses the same amount of stages, but with different shaders. The problem here is that pipelines are quite static. So when we want to have a slightly different pipeline, we need to build the pipeline completely new. There are more settings. For instance, we can decide if we want to have filled triangles or just the lines, if we want to cull or if we don't want to cull anything. And the same happens here. So when we want to change one of these settings, we need to build a completely new pipeline. And the results from these two pipelines would look like this, for instance, shaded and only lines. But there's some way around. Some settings can be set dynamically. So when you create the pipeline, you would specify, I want to set the scissor data dynamically. That means when you record the commands, you can also record a command that sets this scissor. If you don't want to have it dynamically, you have to specify it during pipeline creation. So this needs to be activated during pipeline creation. Otherwise, set it with the vk command function. We will talk about ways around this shortly. But first talk about the frame buffer and the render bus together, because these are kind of connected. A frame buffer is a collection of render targets. It's only used by the graphics pipeline. It's a collection of images. And in this example, we have a bit of a deferred shading kind of setup with a depth buffer and a buffer for normals and a buffer for diffuse color and then a final output buffer. So all of them are collected in a frame buffer. And we would access them, as in the previous example, by specifying the location index. So now we also need a render pass, because we need to specify how these attachments are then used when we start the render pass. And for instance, you could say, when this render pass starts, I want to clear all these attachments, or maybe I want to keep all this content in the frame buffer. And a good example maybe is if you render your scene, you want to have the buffers cleared at the beginning. But then you want to add some UI on top of it, then you would specify in the render pass that you want to keep the content of the attachments or these buffers, because you want to overlay the UI. So the render pass describes how frame buffer attachments are used. And there's also something that allows you to synchronize subpasses. So in this example, we have two subpasses where the first subpass only writes to the frame buffer, to some attachments of the frame buffer, and then the second pass uses these informations and creates the final output color, exactly like you would do it in a deferred shading method. So subpass 0 writes to the depth buffer, to the color attachment of the to the normal buffer and to the diffuse color buffer, but leaves the final color unused. The second pass then reads in these images, and then does some calculations and writes to the final output color, which is then used to show to the screen or to the window. So the depth attachment is a bit special in this case, because it does not contribute to the index, or it does not have an index, so to say. Final color, diffuse color, and normals start with 0 index, 1 as index, and then 2 as index, and the depth buffer is a special case. And you can only have one depth buffer per frame buffer. So why do we even need a depth buffer? If we would render this two triangles, the second triangle would just overwrite everything from the previous triangle, even though the blue one should be in the back, because we don't use a depth buffer. The solution is just use a depth buffer. And you need to add this to the frame buffer as well as to the render pass, so that the render pass knows, hey, I need to use a depth buffer in the frame buffer that was provided. You can use different frame buffers with one render pass as long as they are compatible. And compatible means that they have the same amount of attachments, or that the render pass, when it is configured for 4 attachments, the frame buffer, for instance, would also need to have 4 attachments. And when we render this now, the shading is correctly. So what does the depth buffer do? It just saves the closest fragment that was rendered, and when a new fragment comes in, and its distance is closer than what is stored in the depth buffer, it is overwritten, and if it's farther away than what is currently in the depth buffer, it is ignored. So these things all seem pretty static, and they are, and that's why they introduced dynamic rendering, which streamlines this a bit, and it's basically a single pass render pass that can be configured dynamically. So the default rasterization pipeline would require a render pass during creation and requires a suitable frame buffer during rendering. The dynamic rendering now, which is also part of Vulkan 1.3, removes the need for both render passes and frame buffers. And everything can be dynamically specified during command recording. And it would look like this, where you have a struct which configures the rendering that you want to do, where you can specify the color attachments and the depth attachment, and then you just call begin rendering with the struct as input. So that's for dynamic rendering. And recently there was a new extension which is called Shader Object, which replaces the static version of a pipeline with a completely dynamic one. And it's like rendering in OpenGL again. So you activate this extension like we already talked about. This only works with dynamic rendering, so you can't use shader object with, I think at least, that it doesn't work with frame buffers and render passes. It provides a dynamic alternative to the static pipeline configuration. And it looks like this. So you have a lot of commands where you can set all of the settings that you normally would set in a pipeline configuration struct on the fly during command recording. And here's some of these functions that would set things that we talked about in this part. So we can dynamically set the vertex input, we can dynamically specify the cull mode that we want to use, and we can even dynamically bind or set shaders. So we could set the vertex buffer, we can set the fragment buffer, and render something and then just swap out the fragment buffer. With static pipelines, you would bind a completely different pipeline and create it also first. So, any questions? Or I can repeat the questions otherwise.
On your example where you had 2 subpasses, is the advantage of having subpasses the idea that maybe a mobile tile-based thing doesn't have to go back to memory? Like, I wasn't clear on why you'd use a subpass versus two passes.
So the goal is always to have the least amount of synchronization between things, so that the GPU can utilize available cores as best as possible. And subpasses are basically a way of doing this. I can't really go into more detail, but I hope that's enough.
And that's also why they're doing the dynamic frame, because on desktop GPUs you don't really need them. But is it because of how tiles rendering works on mobile phones that they introduced this in Vulkan?
Can you say it again?
The subpasses is because of tiles rendering. So you subdivide your screen into big bins. You bin all of the triangles that you're drawing into those bins, and then each bin is processed separately. If you know you're going to do multiple passes, you load all of the attachment, or that small tile of each attachment into some special cache, then you do your drawing. And after that, you need to write it out to memory. But if you know there's going to be multiple passes using the same resource, and you just keep it in the cache and do those multiple passes.
That's a good point.
One after the other.
For tile rendering, this could be helpful. And I also think that shader objects were created because pipelines are not, let's say pipelines are not as static as Vulkan sometimes makes them to be. And there's much more flexibility in that, and that's also why it led to this shader object development.
Okay. Thank you for the time. Maybe one question I have is regarding shader objects, actually. This takes us a bit more close to the old OpenGL API, where you're saying GL enable this, GL enable that, GL dispatch that.
Yeah.
But you're still submitting all of this to a command buffer, right? Which means what you're not doing, which nobody really liked about OpenGL, is setting global state flags.
That's true. That's why a lot of people complained about this.
That's very nice.
Yeah. That's also why the joke comes that we're going back to OpenGL.
Yeah, but I mean, you're avoiding the worst part of it in this case, which is that you don't know whether depth testing is enabled or not or whatever.
The good thing is you can always use the other things. Yeah. So I think the goal is that you make the entry into using Vulkan more easier, more streamlined. Because you probably know this meme with 1,000 lines of code just to draw a triangle.
Like, how much easier is it with that, with these, how's it called, shader object extension, like in terms of lines of code? Like, give a number of, how much do I need for the initial Vulkan release 1.0 to draw a triangle, and how much lines of code do I need with that extension?
That's hard to say. You mean in lines of code?
Or, I mean, if it's a complexity, that's what people always complain about. You need this and that many thousand lines of code to draw a single triangle in.
I can say for dynamic rendering, it changes really a lot. Like, it makes it way easier to do all this. I haven't experienced that much with shader objects yet, because I think it came out only 3 or 4 months ago. Yeah, but at least dynamic rendering makes stuff a lot easier, at least in my experience.
So I have a question.
Sure.
Would you recommend it to teach it this way, to use the shader objects?
That's a hard question.
Is it like way slower or something? Are there any real problems?
The claim is that it is equally performant, but it could be a bit worse in certain situations. It's a bit hard to read. Like, they say it's exactly the same, but it can also be not.
Okay.
One more question about the shader objects. What's the default state, and can you like batch set the options? Like,
I haven't seen anything to patch set them.
But what's the default then?
I think there is no default. You need to set it.
So you need to have all of the settings.
I think so.
Okay.
But maybe I'm wrong. Or someone else knows. Okay. Then I guess I continue with ray tracing. So for ray tracing, there's again another different pipeline, the ray tracing pipeline. And the ray tracing pipeline has the following structure. We have this, we have the ray generation shader, which spawns some rays that are then get tested for intersection using a accelerated using acceleration structures, which are just optimized structures that allow for quick intersection testing with rays. And then depending if there's a hit or not a hit, a miss or a closest hit shader is called. There are optional other stages which I'll talk about soon, but that's the simple version of it. So we can have either triangle meshes, but we can also have axis-aligned bounding boxes, which allows to implement procedural objects. For instance, this sphere, which is just x squared plus y squared plus z squared equals some radius. And you can use this formula then to implement this in this axis-aligned bounding box. So here we have our pixel grid. The ray generation shader spawns a ray, which is then tested for intersection, but it does not hit anything, and we call a miss shader, which could then shade the pixel black or whatever the background is, or just ignore it. Then we move a bit further to the right, and we again execute the ray generation shader and start the acceleration structure traversal, and this time we hit something. But since this is an axis-aligned bounding box or an procedural geometry, we also need to specify an intersection shader, and that's what I said with this formula for the sphere. Here we need to implement when this ray is a hit and when it is not. And if this intersection shader reports, yes, this is a hit, this intersection gets recorded. And if all of the intersections along this ray are tested, the closest one is chosen, and the closest hit shader is called with this object index that was hit and is also the closest. And in this case, we shade the pixel green. Again, ray generation shader, traversal, closest hit shader, green. So this time we miss again, and now it's again a hit, but this time it's the triangle mesh that we hit. In this case, we don't need an intersection shader because there's a built-in intersection shader, you could say, which is just a ray triangle intersection test. And we call the closest hit shader for this and shade it pink. Again, pink. So in order to test a scene for intersections, we need acceleration structures, which are a bounding volume hierarchy. And there are two types of this. There's a top level and a bottom level one. We will now talk about the top level one first. So the top level one only contains instances of the objects in the scene. So for instance, for this green ball, for this procedural geometry case, we have 3 of them in the scene, but we only need it once in data, and we can just instantiate it throughout the whole scene. And for the tree, it is the same, but in our scene we only have 1 of them, so we only need 1 instance of this triangle geometry. And both of these objects are in a bottom level acceleration structure. So a bottom level acceleration structure contains the actual geometry and builds a bounding volume hierarchy around that. And then it gets referenced in the top level acceleration structure. For the leaves, it's 3 times the acceleration structure number 1. And for the tree trunk, it's once the acceleration structure number 2. There are multiple different things that we can set per instance. Maybe the most important one is the transformation matrix. So we can set or move or position this one bottom level acceleration structure at multiple positions in the scene. There's also a mask which allows us to include or exclude some of these objects during intersection testing. There are flags which allow to change the winding order for backface culling, for instance. But note, in ray tracing, backface culling is not an optimization. It can make things even slower. And an offset, which is used for selecting the shader that we want to execute. We will talk about this soon. And we can also specify a custom instance index. So in the shader, when we hit some object, we get an index back, and this allows us to differentiate between different objects that we hit. And there's also already a default one built in, which is the order in the top-level acceleration structure. So for the tree, for the leaves, it's 1, 2, 2. 0, 1, and 2. And for the geometry, for the triangle geometry, it's 3. So building these acceleration structures is a bit complicated because we need to build them on the GPU. So we first built the triangle geometry bottom level acceleration structure, and then we built the procedural geometry acceleration structure, and then we get the handles for them. And then we can add them to the top level acceleration structure, and then again build it also on the GPU. For building, we need to, on one hand, allocate memory for the actual geometry, but we also need to allocate memory for some scratch buffers, which are used during building of these acceleration structures. So this is a very naive version of a bounding volume hierarchy structure, but as you can see, each of them has a bounding box. And when we do ray intersection tests, we can go through all of these bounding boxes first and then go more detailed, so to say which triangle exactly was hit. But this building of acceleration structures improves this a bit. So again, we don't really know what exactly it is doing because that's vendor dependent, but at least something like this. And then we have one big bounding volume, bounding box around the whole scene. And when we now trace one ray, the ray gets first tested for this big bounding box that encapsulates all of the scene. And if it misses, it just stops. But in case it misses, in case it hits, we go deeper down this tree. Now we test also the procedural geometry, but also the tree triangle based geometry. So first, and there's one thing, the order of intersection testing is not specific. So it can happen that things that are in the back are tested first, and then things that are in the front are tested first, later. So this can make it a bit hard to do blending, for instance, because you never know really which one is tested first. So now we test the procedural geometry, and since this one is closer, no, ignore that please. We need to go more into detail here, because this is an implicit geometry, so we again call this intersection shader, and it gives us back the distance and the position at where we intersected the sphere. And since this sphere was closer than the tree, the closest hit shader gets called for this tree, for this leaf. So now comes the hard part, the shader binding table, which is a collection of shaders that you maybe will call in your ray traversal. The address or the memory locations where these different shader tables are located are passed in when you call this VK command trace race command. This is the equivalent to the VK command draw command for rasterization, kinda. And in the shader, so this VK command trace race call executes the ray generation shader, And in the ray generation shader, you call the trace ray ext function, which then takes in this acceleration structure that is in your descriptor set and does some ray intersections with it. And as you can see, you also specify the origin and the direction of your ray that you want to test. So the shader binding table is, as the name says, just a table, but it contains different kinds of shaders. And one of these shaders is the ray generation shader that we already saw. But also we can specify different closest hit shader for the different types of geometry that we have. We could, for instance, have one closest hit shader for all of the materials that we have in our scene. And we specify this by giving the start address to the memory location where all of these closest hit shaders are located. And lastly, we also need to add a miss shader, which is called when nothing is hit. So the shader binding table is a buffer. The addresses are passed in during command recording. There are really many ways to define a shader binding table offsets. In the Vulkan specs, you can find the formula for it. And you can set it when you add instances to a top-level acceleration structure. You can set them in the shader itself. Yeah, there's really a lot you can do. And one of these shader binding table entries can refer to 1, 2, or 3 shaders. There are different shader groups. The general group is the ray generation shader or the miss shader, but there's also a core level shader, which I never mentioned before in this talk. It's basically just a shader that you can call from within a shader. I think someone once said that this callable shader is just then inlined in your shader, which makes it not that useful, I guess. But these things are always hard to say, what really happens. And in the shader binding table, for the general group, you only specify one shader. For instance, here the ray generation shader. And in the next row, you specify the miss shader. But for the triangle hit group, you have closest hit shader and any hit shader, and you can specify both of them. So what does the any hit shader do? The any hit shader gets executed every time you intersect some object. Doesn't matter how far or close it is, and doesn't matter if it's even the closest hit. It gets executed for any hit. Why do you want to use this? For instance, for transparency. If you have just a square triangle mesh, and you have some leaf on it as a texture, but there are some parts that should be visible, should be transparent. You could then hit this geometry, and then in the any hit check if this is actually something with an alpha 1, for instance, or if the alpha is 0. And if the alpha is 0, you just ignore this hit, and it will never be considered for the closest hit intersection. And the same thing you can do for the procedural hit group. There you also have closest hit and any hit shader, but you also additionally have the intersection shader, which you can use to specify what is an intersection for this procedural hit group, for this procedural geometry. So in the shader binding table, we only use the closest hit and the intersection shader. And I think if you don't specify intersection shader, it will be just considered as a box, like an axis-aligned bounding box. So there's another thing, ray queries, which is exactly ray tracing, but you can do it in any shader. For the normal ray tracing, you need this ray tracing pipeline, and you have this many different shaders, and they are called in independent order. And with ray queries, you can just do some, basically check for intersections in your fragment shader, for instance, or in your compute shader. So ray queries require no ray tracing pipeline, no shader binding table, just the acceleration structure. And it allows intersection tests to be done in any shader that is available in Vulkan, I think. Compute or fragment shaders. The performance between ray queries and ray tracing pipelines can be different. I think at least in the beginning of when this came out, ray queries were slower than ray tracing pipelines. I don't know how it is nowadays, but there's one thing that gives ray tracing pipelines the upper hand. Recently, this shader execution reordering was introduced, and this cannot be done with ray queries. The reason for that is that in a ray tracing pipeline, when you hit objects, you call these different types of shaders depending on what objects you call. And if a lot of threads do different executions than other threads, then because of this branch divergence thing, both of them need to be executed. But they are masked out for one group while they are executed in the other group, and then it's the other way around. And this wastes a lot of computation, and so this shader execution reordering tries to group similar executions together, so tries to group similar shaders together so that the GPU is best utilized. And since you don't have these different shader calls in a ray query, you can't really do that. And let's take a quick look at what how ray queries are programmed. So it is basically a query operation where you call this function in a loop, and this returns true as long as there are some intersections to process. And then you have these two functions that return. You can compare the result of these two functions if it's a triangle or if it's a axis-aligned bounding box, and depending on what it is, you choose one branch or the other. And then if you're happy with this intersection, you can confirm this intersection, and then it will be considered for basically the closest hit shader in the end, which you can then query again. And here you would then check if there was some intersection or not, or reported intersection, you would say. Because you can just ignore some intersections, and then if there's no other reported one, then of course you don't have anyone in the end. So that's basically it for ray tracing.
Can you hear me? I would like to ask you, how do you basically pass some information that might be required from intersection to shading, like normal from the sphere is a typical example? Because if once you compute a point, then it gives you the normal, or if it would be ellipsoid, it's different. Or another example is like UV parametrization for texturing for triangles. So how this is done?
So one way would be that you do all this in the closest hit shader, so like getting the UVs, reading the texture and that stuff. Or you could just pass this information from the specific shader back to the ray generation shader and do all in the ray generation shader. And there are what's it called? Payloads which you can write from the intersection shader, from the closest hit shader, from the miss shader, and then you can read that back in the ray generation shader. But you should keep the ray payload or these payloads relatively small, because things get slow quite fast when you make them too huge.
This was just basically a comment. You said that the acceleration structure had to be built on the GPU. I believe you can choose either do a CPU build or a GPU build and various quality setting effort levels.
Yeah, there's the option to build this on the CPU too, but you need to queue for if it's supported, of course.
Okay.
For instance, on my system, I think it was not supported, but I don't know. I haven't looked that much into it.
Are you aware of any compilers from C++ to SPIR-V? Because it could be a lot easier to debug your ray tracing pipeline in C++.
That's true, and that's one point that a lot of people would like to have. There's this Circle compiler by Sean Paxter, I think, and he has this experimental C++ compiler with all this fancy stuff, but he also added SPIR-V support to it. So you could write your shaders in C++ and also have it together with your host side code. The problem was just that his compiler is closed source and only works on Linux. But there are a lot of people, or quite a lot of people, working on providing alternatives to this GLSL and HLSL compilers. For instance, there's Rustlang, which is a Rust compiler to SPIR-V. And I think also the DirectX compiler team is working on integrating this into the LLVM mainline GitHub repo, mainline code. So, and they also try to close the gap between HLSL and C++. But there's still not a perfect solution, sadly. But I think a lot of people hope for this.
Hi. In one of your last slides for the ray query, you showed that you check whether you have a while loop and you check whether it's either a triangle or an access line bounding box. Is it, as far as I know, at least I'm only mostly familiar with DirectX, it only says acceleration structure. Is it guaranteed to always be an axis aligned bounding box, or could a vendor decide to do something else? I don't know, spheres, oriented bounding boxes.
So you mean, does it always have to be an axis aligned bounding box? Do you now mean for the acceleration structure, or do you mean for the procedural geometry creation?
So does this loop show? Is this AABB? Is that a procedural geometry, or is that like a node in the axis line in the hierarchy?
So this procedural geometry is always an axis-aligned bounding box.
Okay.
But you kind of build it into the axis-aligned bounding box.
Okay. No, sorry.
With this, in the case of the sphere, like this x squared plus y squared plus z squared equals 0 would equals 1 would give you the surface of the sphere. And then when the ray comes in, you can check if, based on that, if the ray intersects the sphere, and then report an intersection.
Oh yeah, so just some misunderstanding from my part, don't worry.
But it's always an axis-aligned bounding box, yeah.
So could you explain a bit maybe how does transparency work, and how do you blend together colors if something is behind it?
Do you mean now blending or just transparency?
Just if something is behind like a semi-transparent object, then how do you continue like searching for stuff?
So, okay, you shoot a ray and you hit some object that is transparent. Then the any hit shader gets called for this object, and you would for instance, yeah. I mean,
not proper transparency with refraction. It's unfortunate, but it means different things here.
Yeah, that's true. I mean, if you would model real transparency like glass or something, you would do it completely different, like with actual geometry and doing reflection and refraction rays and that stuff. But if it's just about blending some object over other objects, this is, I would say, not really solved yet. it's also hard because blending works from back to front the best, but if you, for instance, try to blend things from front to back, it suddenly becomes really difficult. There are some ways that you can solve this, but it's not 100% correct all the time. And it also depends on how many transparent geometry you have along the ray. And with 2, maybe it works quite good, but if you have 10, then the results can very differ from the correct result. Yeah.
I'm wondering, this whole API looks very similar to the optics API. So are there any advantages or disadvantages to using one of these if you're working on an NVIDIA GPU anyways?
Please say it again.
So if you, I think this whole API, this Vulkan thingy is basically an API specification, as you said in the very beginning.
Mm-hmm.
And I think it looks very similar to the optics API provided by NVIDIA.
Mm-hmm.
So if you know that you work on an NVIDIA GPU and you don't need the portability of Vulkan, are there any disadvantages or advantages of using either of those?
I think in the end, no matter what API you use, the end result is, it all boils down to the same thing in the driver. And yes, the optics API and the ray tracing API for Vulkan is very similar. They both have these acceleration structures, they both have this shader binding table. And if you're only working on NVIDIA, then it's the only advantage that you have with CUDA then is, of course, that you can program in C++. But performance-wise, I think you can do the same things, basically. CUDA also has different ways of approaching this. You have the driver level API or the more high level one, and with the driver API you can probably achieve the same thing.
Okay, thanks.
So, well, one thing is you can mix rasterization with ray tracing, which with optics might be a little difficult. But on the question of transparency, has anyone here, like, what would be the state of the art in terms of what would be the fastest path for rendering like transparent blades of grass or something like that? Would it be rasterization, or would it be ray tracing?
Maybe someone would say that maybe software rasterization is even faster.
I mean, does anyone have an opinion on this? Or here?
I think if there are many triangle, I mean, Bernhard could probably talk better about this, but if multiple triangles are within 1 pixel, then software rasterization could be better. Otherwise, hardware rasterization is better. Is this correct, Bernhard?
So in particular, transparency, so we've recently gone a lot into transparent things, but this was for a different application case. So with the explicit use case of, I guess, the target here is foliage, I'm sure there's experts, but unfortunately, both of us, that doesn't cover our expertise, so yeah.
We would need Markus here.
We're getting better at this. So maybe naive question, but how do you actually go to secondary rays using ray tracing pipeline? Like, how do I take my closest hit shader, knowing I've hit something, and say I'm building my first path tracer? How do I feed back into a ray generation shader? Do I like have a secondary buffer with like a head that I move and push data in, or does the API support this somehow?
Good question, and I totally forgot about this. There are many ways to do this. You can do a wavefront ray tracer, which you described in the end, where you do some intersection, write everything to a buffer, and then do another call and do the next depth intersection. Yeah, and you always go narrower and narrower because you can just ignore the pixels that did not hit anything. So if you shoot rays at the cube, then most of them miss, but only a few of them will hit the cube. And then you can do the secondary bounce only with those few rays that hit. And then you can also spawn less threads and utilize the GPU better. The problem is that then the bottleneck is the bandwidth. And as recent papers have shown, wavefront ray tracers are slower than, what's it called? Megakernels, exactly, yeah. Megakernel type of ray tracing. Now back to this megakernel approach. You could, when you hit something and the closest hit shader gets executed, you can call a recursive call to the trace ray function. So you start with the ray generation shader, you trace a ray, you hit something, closest hit shader get called, and in the closest hit shader you again call the trace ray function, and you can do this a certain amount of times. When you create the pipeline, you also specify the maximum recursion tapped. And I think depending on the device, and you can check this on the website that I showed, or you can cure it in code. I don't know what the maximum depth is, but probably 20 or so, or maybe 12, and depending on the vendor and the GPU. And if you don't want to do this, you can just return the data from the closest hit shader. So when the closest hit shader gets executed, you get the instance index, which describes which object was hit, and you get for a triangle hit, you get the pericentric coordinates. You can just return these informations back to the ray generation shader through the payload, and then do the second bounce again in the ray generation shader. Then you would kind of have a loop which goes from 0 to the depth that you want, and you.
But then you're basically doing a full shader that is itself the path tracer or something similar.
Yeah, exactly. Because the closest hit would then consist only of 5 lines that just passes these informations back.
We have time for a follow-up question. So does the vendor, on the vendor side, is anything done to keep rays next to each other, or to keep shading work similar in that case, when you're doing a lot of rays? I mean, if you're doing this, you'll get less and less rays the deeper you go, which is always a problem with path tracing. And there's a lot of work on vectorizing things and moving things around. Do you know if the vendor has any influence on that?
Say again, please. Vendor.
So, what's the word for it?
A vendor, you mean the
vendor. If they have any influence on moving work around to keep the rays that you are tracing similar.
By default, I don't think they do anything. Oh yeah, okay. Sure, let's all visit this talk. Something I wanted to add.
That's all right. I was just curious.
Yeah. And I think everyone that does ray tracing knows the problem, that the first intersection is fast because everything is coherent.
That was the word I was looking for.
Yeah. But after the first bounce, rays randomly go through the scene, and then things become slow. In the ray Curie, you don't have a ray generation shader. You have the shader that you used for issuing this. Okay.
Just to answer the previous question, you mentioned the shader execution reordering, and that's not done by default, but that would be one thing that would reorder the rays in between the stages to keep the coherency as much as possible.
Exactly, yeah.
But yeah,
Yeah,
that's
we need to
pretty
activate
recent extension.
Yeah. It's one of the cool new advances in ray tracing. Okay. Then I think I'm done with it, and I will forward this now to Bernhard. And he will talk about compute shaders and synchronization within compute shaders and all that fancy stuff.
Okay, let's quickly hook this guy up because he's really power hungry. Okay, does this work? No, right? Okay, it's just for show. Okay, great. So, thank you, Lucas. Let's now look into Vulkan for compute. So maybe quick show of hands, if you don't mind. Who here, just so that I can get a feel, who here has been using Vulkan before, just so we know? Okay, okay. Who's been using Vulkan in general? Compute in general, any graphics API? Okay, that's good to know, super interesting. Okay, good, that gives me a bit of a feeling for how we should speed this along. So basically I don't need to go into much detail of why you would want to use compute, because basically the reasons are known to most of you. You have this parallel power horse basically as a sidekick to your CPU now. You can use the GPU to do non-graphics related tasks, which is great. So it unlocks certain particular features. For instance, there are some specific faster memory spaces that you don't get in the graphics API, for instance, shared memory and other features. But also, this is maybe for the direction of the researchers and perhaps also the teachers in the room. It is quite educational, because when you approach the GPU, and especially with Vulkan through compute, you basically need to kind of internalize how work distribution really works on the GPU. Like, how do things work together? Why do I need a queue? How does that make sense? What is oversubscribing of the GPU with work? And all these kinds of things start to come together, and you start to kind of understand the architecture that you're working with. But also, and last but not least, it allows you to focus on performance, right? You don't have this complex setup, you just have this compute situation where you usually have some input data, you have some targeted output data, and that's all you need to solve. The pipelining and the setup is all much simpler, which we will see in a minute here. So we have a very established background here, all of the people watching. Some of you guys are researchers, some of you are students, some of you maybe also know graphics and compute from the industry. So hopefully what comes up is a solid mix of some foundations for those who don't know them, then some examples for those who are maybe looking for new applications, and then perhaps also some tools for those who would like to know how to use Vulkan efficiently, or maybe a bit more efficient than the standard conventional baseline that you have available. So computing graphics in general is on the rise. That is not a bit of a secret. Last year we had a fantastic talk at HPG by Brian Karras about Nanite. Nanite, of course, is heavily involved in using compute methods, combining them to achieve multiple great performance gains when the compute pipeline is more efficient than the graphics pipeline would be, basically because it gives you more freedom. We also have, of course, the trend and the incredibly fast advancement in the field of neural rendering and radiance fields, and these renderers, in most any cases, they are built on top of some way of compute programming, but then again to achieve some graphics goal. For instance, IncidentGP, which was last year's best paper, at SIGGRAPH had this phenomenal presentation of their implementation where they used these neural graphics primitives to do very fast nerve rendering. Also, this year, I'm happy to say that we'll be talking about our paper at SIGGRAPH, the 3D Gaussian splatting for real-time radiance field rendering, which is, of course, also based on compute. That's why I'm bringing it up here. There's also some work that we will see later this week by colleague Markus Schütz, also again using compute to do some graphics, but there's also been other previous work. So this is not new, but I would say the trend is sort of increasing. Now this was a question just a few minutes ago. What is the situation with rendering a triangle? How bad is it really? And what could we potentially do to improve this? So if you follow the original Vulkan tutorial, which is like the go-to place for doing graphics, and then you look at the comments you find underneath, you get a bit of a you get a bit of an overview of what people are experiencing going through this. So to answer the question from just before, if you follow the official Vulkan tutorial, which is great, right? But it is verbose as it had to be in the original incantation of Vulkan. It's pretty much exactly 1,000 lines to get a triangle rendered, right? So that's not an amount of time that many of us have. And it's also a very big hurdle, especially if you are in the teaching direction for students, to get that first motivation going. Like the first time seeing something visual is usually the time where you get the first feeling of success. And if it takes 1,000 lines of codes to get there, that's really tough, right? So why is Vulkan so verbose? Short answer is because it sort of has to be. If you, for instance, compare to programming for the CPU, when you write your program for the CPU, you aren't really giving it instructions. You're maybe giving it hints, right? Then it goes through the compiler, it goes through several layers of magic, and then maybe there's some neural network even built into your CPU to help with the execution along. So you're not really writing the instructions that you get for the CPU. For the GPU, things are much simpler, and you have basically a wide range of control. So this simpler set of things that you can change and that you can set and that you can modify is pretty deliberately exposed to you on the GPU, right? So it is comparably simple, but one would be amiss to basically, or it would basically not be true to compare, liken it to a state machine, which is basically what we get with the old APIs that we had for graphics, like OpenGL and DirectX. So those are by no way, in no way are they bad APIs. You can get really great performance with OpenGL and DirectX 11 because people have been going through an effort to keep them sort of up to speed. But if you go into graphics or if you go into compute through these APIs, you are very likely to perceive a version of the GPU that is simply outdated based on how things are done in OpenGL, based on how OpenGL is taught. And that's kind of an issue that makes Vulkan sort of, I would say, the modern or the recommended way to approach the GPU, especially if you want to do something for compute, because approaching Vulkan through compute makes it, as I find, quite a bit easier. And why is that, or what can we do to actually realize that? First of all, here's a tooltip I would like to provide for those who haven't heard of it, and that is, instead of using the conventional way to go into Vulkan to use the standard API, there's a wrapper called Vulkan HPP, which gives you C++ style extensions, which includes constructors for structs, so you don't have to be so explicit when you want to define something, which also defines RAII style wrappers for almost anything, so you don't have to clean up after yourself when you allocated something or when you created something, and also can help you with avoiding errors by providing clean namespaces and explicit flags and class enums for the things that you can pick and assign. Let's see, look at some code and see what we can understand from this. So the previous session by Lucas, he intentionally removed some of the code, so I'm kind of bringing it back again. Here we have, for instance, the basic setup to create a logical device that you can then use to do some Vulkan instructions and some Vulkan action, right? So this is not that much, but it's a significant amount of lines of code to get one very basic thing, a device, going, and you need the device always to do anything in Vulkan, right? So this was what it would look like with the classic API, being somewhat minimal about it, and this is what it would look like with Vulkan HPP, right? So we can be a lot more compact with Vulkan HPP, because Vulkan HPP provides you with the innate ability, or the innate ability to set the S-types, so you no longer have to specify them yourself, which was sort of redundant from the very beginning. You also have these unique RAII style objects that automatically clean up after themselves, so you just create a unique device, and then when it goes out of scope, it basically destroys itself, and that's everything that needs to be done with this object taken care of. And also it has support for STL type containers, so you don't need to build those C-type structs, and basically can work with any kind of container that you would like from the stud library, convert them, pass them around, and most of them will have some support and be working along with Vulkan HPP. So let's go through a concrete example. What do you need with this tool at your hands to build up your first compute pipeline in Vulkan? I'm going to go ahead with the GLSL route. So we would need some GLSL code to execute, get a compiled version of your code into SPV. I'm not going to go through all the steps, because let's do them like 2 or 3 at most at a time. Okay, so let's start at the beginning. Let's say we have a file with our GLSL code, so our shading language code, and we want to get that compiled and then run it on our SPV, run it on our GPU. So give me a second here. This is this maybe a bit of a mistake in the slide ordering? Nope. Nope. Okay, sorry. This is all fine. Yes. Yes, okay. So before we launch, we need to know, or before we write our GLSL code, we basically need to know how the GPU execution model works. So this is known to most of you, so I'm gonna speed through this because most of you have worked with compute already. So you know when you have a problem, like for instance this image, and you wanna do something with it, you basically have some sort of problem domain, for instance the pixels of it that you want to work on, and then you know that you can split it in the individual groups that are then able to collaboratively do some work on them. Or not, they can ignore the fact that they are collaborative, but the important thing is you have to define these kinds of groups to work on your problem domain. And you're pretty much free to design those groups with arbitrary sizes and shapes, if you will, to achieve a particular job of, for instance, computing a filter or traversing and combining or converting your image in some way, for instance. And the structure overall in the execution model is we have the individual problem domains entries, then we have these collaborative groups, and if we look at one group in particular, we know that it is made up of multiple threads. And then also, this is now a hardware execution detail, is that you have these things which are in GLSL called subgroups, which would be called a warp in CUDA, or are generally referred to as a wavefront, which is kind of a hardware detail, where you basically say the SIMD width of the GPU is some particular factor, so it takes threads and executes them and executes instructions with this particular SIMD width. And this is something that is basically forced on you, which is can be sort of good or bad. It has kind of it has some implications that you need to consider if you're writing advanced code, but it also has some benefits, because if you are aware of this, you can exploit it to kind of get a fast lane for data transfer between threads that are working within such a wavefront. Okay, but this is known to most of you in this room, so I'm not gonna dwell on it. And yeah, of course, also each of these APIs has their own way of referring to these things, but under the hood, they are all the same, and basically the execution model is always the same because it's always the same architecture underneath. So that is not so surprising. Okay, so now that we have a quick refresher on how work is structured or layout on the GPU, what does this now look like when we write the GLSL file to do some work? So let's say we have our Vulkan ready GLSL, our Vulkan
GLSL flavor. And working with Vulkan in GLSL means we have the ability to printf, right? So we can now debug printf from our shader. This is interesting to those who have been looking for any way to doing printf debug. With Vulkan, this extension has been added. I think Vulkan was the first API to add this ability to their shaders. I could be mistaken, but I think this was a big deal when it was became first available. So, and here we have now our example shader, which describes some sort of workgroup with some extent, right? So this workgroup is just one thread because it is one in all dimensions. So that's the extent of this workgroup, just one thread. And then basically it takes its IDs and writes out a message via debug printf. Then it's just a simple matter of sending this either to GLSlang or through GLSLC and can end up with your SPOV. So then in order to get something running, you need to read the compiled SPOV at runtime. There's 1,000 ways to do this. If you have worked with any kind of file I/O, you know how to load files. So again, I'm not going to dwell too much on that. From the loaded SPOV, you then need to create a module. So basically, the shader module that will make sure that your SPOV code is eventually transposed or translated into actual machine instructions that can then run on your GPU. And let's see again how this could be done, for instance, with Vulkan. We would just need to do a create shader module unique. And basically, again, you create something that you want to use in Vulkan HPP. Most often than not, it's a one-liner if it's really as simple as expressing it with a simple intent, right? I want to create an object that looks like such and such and such. It will probably be a one-liner, okay? So the module here, again, in this case, is unique. So again, this outlines one of the features of Vulkan HPP. We say here, create shader model unique. We don't have to define the exact type. So this module, when it goes out of scope, will clean up after itself. And we're basically saving up on half the cleanup code that you usually do when you program Vulkan with the C-style API. Okay, then we need to create the basic compute plan with that module. And this is, for those who are aware or are not new to Vulkan, this might come as a nice change of pace, basically, because you know that the graphics pipeline, when you start with your graphics tutorials or your graphics course, is very verbose. It has a lot of features that you can twiddle with, that you can set up, that you configure. And basically, for any stage along the pipeline, there is something that you can specify, that you can set, and that ends up in creating more source code for you to write initially and then also maintain eventually. And so if this is the graphics pipeline, then this is the compute pipeline, right? So much fewer things to maintain, much easier to set up. So actually the entire setup for a runnable compute pipeline, if we have our compiled SPOV shader, is exactly, again, this. So these are all the instructions that we need to set up a functioning compute pipeline from our compiled shader. Basically just define a shader stage, create a pipeline layout, which is, again, a unique layout with no special requirements in our case, and then just provide a stage info in which we say we want to run compute. That's all we want to do. We want to execute our module, and the entry point into the module is main. That's all that this pipeline needs to get going, okay? Then we create a compute pipeline from that, and then afterwards, it's already ready to be run and to be executed by a command buffer. Okay, then that's the last part that we need to do is record set command buffer and, record set command buffer, make a submission to the command buffer queue, and then synchronize with the entire device or until the device is done doing it. And then our GPU job has run and is finished. Okay, so the last step is then compile, set up your command buffer, bind the pipeline that you want to use, submit to the queue that you have chosen, and then eventually use device wait idle. So you see here, in the spirit of keeping this sort of light, I use the wooden mallet of synchronization tools, right? I use the device wait idle, which just says everything that I've submitted, make sure it's done, and then come back to me, right? That is something that you can in most cases do if you are not too keen into going into the detailed synchronization spiel that is available. The wooden mallet of wait idle is basically there to give you basic starting point, right? And then you can work from that and make things more efficient, make them more lightweight as you see fit. Okay, so then the result of this, because we have the printf support with those not so many lines of code, was to create a basic application that actually prints to us. So we have basically written the equivalent of hello world for compute in Vulkan, and it wasn't actually that big of a deal. So another part that is usually quite big in terms of setting up your Vulkan application is making sure you have the right development environment. And the development environment usually implies you need things that you are now aware of, which are validation layers. And validation layers are definitely your friend. They are available with very detailed error messages if you do something wrong, even if that wrong behavior is not reflected by the results, the validation layers will catch it. Because more often than not, you can program an error into your GPU application, and it might be an error according to specification, but not according to your GPU, right? Your GPU, depending on the vendor, might tolerate some mistakes, might not tolerate others. Then you write your GPU code, it runs fine on your machine, you take it to your friend or your colleague, and it no longer works, right? So the validation layers are there basically to save you there. So what can we do if we know that validation layers are valuable, but we also know that setting them up is sometimes quite an effort? This is the second tooltip that I would like to give for those who do not know it yet, that is vk-config. I can very much recommend the demonstration and the description that was given at this year's Vulkanized conference about the Vulkan configurator. But basically what it does is with a few set of clicks, it basically gives you the ability to set up your environment and to define your validation layers. You can also enable the ability to debug printf or not on demand. And basically, support or validation of your program becomes a tooling effort, right? It's no longer integrated into your code base, so that you basically have all these different switches and lines and sets of validation layers that you can or cannot activate as you will, but it basically becomes a question of, is the Vulkan configurator running in the background or not, right? And that will make the difference between, are you running your program in validation mode, where everything is checked and being secure, or are you running it basically in the mode where you're not doing any checks and just running the code for maximum performance, okay? So just to illustrate the vk-config, what it would look like, it's not super complex, so it's really easy to get an overview of all the individual features. What you want to do is basically set up the types of validations that you want it to take care of for you, and you basically want to override the layers of your Vulkan application by the configurator. And if you do these things, that means you don't really have to specify any validation layer code in your application, and that again makes your code base more readable, makes it easier to approach, and especially for beginners, you can just skip this step and just have the vk-config running in the background, knowing that it will notify you when something was done wrong. And here, down here, we see the very important feature of redirecting printf messages to the command line. So basically, when you keep that on, you can run something that uses the debug printf extension, and it will appear on your command line window. So just like that. So let's take a look at what the hello world of Vulkan Compute looks like from start to finish. So this is the entire code. So this is Vulkan Compute printing your message to the command line. For good measure, it even includes the shader code, right? So everything really is in there. And we are not really taking any shortcuts. We're not really taking any external libraries for doing these kinds of things. We're basically setting up the instance, which gives us our starting point into Vulkan. We are then picking a physical device, which means which of the potentially many GPUs in your machine do you want to work with. You take a logical device, which basically is your way of saying, I cannot take the entire GPU at the time. other processes needed it too, right? So I make a logical device, and then pick from the physical device a corresponding queue, submit some work to it, and after compiling your shader into a module, make sure that you run it and add it to the command buffer, and once that is submitted, in the very end, you just device wait idle, okay? So it's definitely more compact than what you would have to do for the first triangle, and it gives a, I would say, basic answer to the question, what is the first success that you would experience approaching Vulkan via the GPU route, right? So I would say, especially for those who are considering Vulkan for teaching, if you have the ability to approach it via compute, I would say that this is a very interesting avenue and one that also can help keep motivation a little higher than doing it in other ways. So especially for this task, I basically took that to heart and said, okay, let's try taking a course that we did previously for GPU programming. And as you would expect, this had been done up until now with CUDA applications, and basically convert it to Vulkan and see how it works. So this is basically where I decided to invest the time and come up with this list of coding tasks, so basically coding task suite that you can also, if you're interested, download it for yourself. And it includes applications that give you a basic text output. They are kind of, in a way, sort of related to the kind of tasks you would see, for instance, in Advent of Code, if that tells you something, where you sort of given a little challenge and you have to figure it out. And if you did the instructions correctly, you get maybe a secret message, or otherwise you get maybe an image that ran through an edge detector. But also not to neglect graphics too much, we also do some rendering. We're basically doing a lightweight version of Markus Schütz's point-based point cloud rendering pipeline, where we basically just render to an image and write that image out as a PNG, so we don't have to do all the Vulkan graphics setup. So we're still doing images, we're just doing it very compactly and boiling it down to the essence, right? And why would you be interested in such a setup or in such a suite of applications or exercises? I think there are several reasons why you might want to take an interest. One would be maybe you never touched Vulkan before, and you think starting with compute is actually easier after seeing this. So in this case, I would agree, and that is how I would recommend it to you as well. So maybe also you know Vulkan and graphics, but you don't know its compute capabilities yet, and I guess in this case also this would make a fine introduction to this. Maybe you are also looking to teach Vulkan, and especially in this case, I would say if that is the case and you have some liberties, maybe one could consider this as teaching material as well. This is what I use it for. Or maybe you are just genuinely curious and want to try out some new things today. For all of these cases, basically we have the test suite up, so please feel free to check it out. Make sure to remember that this is an early alpha. Actually, I revised the code base quite majorly yesterday. It certainly doesn't cover the extent of everything that can be done with compute, and if you have some sort of didactic or pedagogic recommendations, suggestions, if you find something that is just plain wrong, all of that is totally possible. Please feel free to reach out to me or make some suggestions for improvement, or maybe additional tasks that you think would make sense in there. Yeah, and for questions or improvements, please just go ahead and submit them as pull requests or as issues, or contact us as our Discord. Okay, so the approach that we took here is already fine, and Vulkan HPP and the Vulkan configurator help us basically decluttering things in Vulkan, but we're not exactly there yet, right? And this brings us basically to our next tool. When we start writing our programs, at some point we need our input data, right? Without input data, all the GPU processing that we're doing is basically useless. So the way to define input data is by creating Vulkan resources. And again, as everything, even with Vulkan HPP, finding and setting up a resource that you can use in your shader has quite a number of steps. For instance, for a buffer, let's say here a uniform buffer, you need to first define what it should be used for, what its memory requirements would be. Then you need to basically go through the different memories that you have available in your GPU, see if one of them fits your needs, and if one does, then you can pick that one, you can use it for allocation, then you have to bind that memory to your buffer, and finally you have something that you can fill with data and use in your shader, right? So this is for one uniform buffer. Here is what needs to be done in order to create not a uniform buffer, which is read-only, but a storage buffer, which in Vulkan is both read and write. Who can tell immediately where the difference is between the two? What changed? Okay, yeah, exactly. So basically, all of this setup here, all of these steps for different buffers are exactly the same. The only thing that changed to change from a read-only buffer to a read-writable buffer is basically this one flag here. That's everything. So that gives us an indication of heavy code repetition that we can either solve by writing some helper functions ourselves, and then maybe discovering later on that our design wasn't that good and we have to update them and maybe write helper functions of helper functions and so on and so on. Or we can rely on the industry standard for doing exactly these kinds of things, which is the Vulkan memory allocator. Okay? So this library is quite battle tested, is used especially, I think, in the game industry quite a lot. Among other things, it simplifies your code. It's not the only thing it does. It also takes care under the hood of managing memories efficiently. For instance, allocating only one big batch of memory when it sees that you are doing multiple small allocations and then just taking them from one place. It defragments your space over time. It makes sure where to pick memory from in the entire memory space. You can give it preferences. You can give it concrete advisements where or what kind of memory to pick. So it's really quite convenient in these kinds of things and also quite powerful. But also, of course, it makes your code quite a bit simpler, right? So this is again the setup compared to what we had before that you need in order to set up your buffer. And note that this unfortunately also includes code for destroying the resources again, because when we made basically that change to using the Vulkan memory allocator, unfortunately we lost the support of Vulkan HPP, and that means we also lost the RAII, so we now have to do a little bit of basic cleanup ourselves. There are some people out there who are trying to maintain libraries that combine basically both of them at the same time, which would be ideal, but the support for that is, or for them is not so strong that I would say they are ready to be used directly for things like industry projects or teaching projects. So unfortunately right now a little bit more of code for the sake of cleaning up our buffers because we don't have RAII for resources, I think is the middle of the road right now. Good. So yeah, just a quick sneak peek into the exercises if you choose to do them in terms of resource allocation. This is pretty much as verbose as it gets. This is one application that uses 3 resources, that is 3 buffers, and uses the Vulkan memory allocator to create all of them with the different settings, and then at the end also clean all of them up, right? So this is all of it in terms of memory and resource allocation, that as bad as it gets in the examples at least. We also still have descriptor sets, and descriptors I have yet to find a way that makes them really easy and tractable to understand, because for the same amount of code that we saw before, basically for these resources, this is the amount of code that you need to set up the corresponding descriptor sets, which is not bad, but I still would like it to be just a tad bit more compact, especially for the purpose of getting the information across. And usually when you try to teach descriptor sets and you say, okay, you need a pool, you need to allocate, you need to define a layout that needs to go into the shader, the pipeline creation as well. Then you use that layout to allocate a descriptor set. Then you have a descriptor set. You fill the descriptor set with descriptor with different descriptor rights. That's usually the part where the student's eyes sort of glaze over. Like there's like just one too many steps in there. And the potential way out of this is a fairly recent extension. That is the VK extension for descriptor buffers, which basically reveals that under the hood, descriptor sets are, again, just memory, right? So when you pass a descriptor to your shader and you use it to get information on where to pick your data from, it's, again, just using a particular memory. It might be in a special location, but it's still just memory. So with this extension, you can treat it as such, and you can basically define a buffer that acts as your descriptor set, and then basically defining the contents of a descriptor set becomes a simple mem copy, right? So that might be a very good alternative, and I'm monitoring how the development on that is a bit. But for now, it still needs cutting-edge drivers. So when I tried it yesterday, because my driver was, I think, 4 months or 3 months old, this extension wouldn't run. After updating, it's fine, but still, that's a little bit cutting it too close for me to go ahead and recommend it to be used in general. Okay, good. So, okay, so a totally different thing, or a mechanic that, since most of you have been working with compute, yeah, I kind of tried to include it as well because it's fairly interesting concept for those who don't know that much about compute, is the heavy ability to use the atomic operations and also what it implies in the context of compute shaders. So just a quick recap for those who are not familiar with the concept or not that familiar with the concept of parallel memory accesses. With the atomic operations, you basically get the method of accessing memory in a way that is indivisible. So that means because there are thousands of threads running on your GPU, you don't really get to schedule them in a very fine-grained manner, but you at least get to enforce that the accesses seem to occur in some sort of undefined order, right? And in many cases, that is all that we need. Just these relaxed atomics, which at the end of running your program, make the program end up in a state where it looks like this could have been achieved by doing some ordered sequence of operations, even though that kind of order is ephemeral and not clearly defined, but at least it seems that way, right? That is all the guarantee that you get with these relaxed atomics. So why are they useful and how are they useful for compute and the overlap of graphics? So again, this brings us back to the computations and the contributions that, for instance, Markus Schütz in the point cloud community rendering community has done, where we discovered that basically if you take many instances of primitives and you have some way of splitting them to the screen, then a very fast way to discover which of them actually ends up being the closest to a pixel is, for instance, to use the atomics, right? In this case, you could say after or during even the projection and the splitting of different primitives to the frame buffer, you can make a selection of which one is the one ending up the winner by simply and atomically always comparing their z values. And then in the end, with the atomic operations, you avoid data races, and you definitely end up with the one entry that would have been the closest, and you can then use that to do correct visibility resolution. Here's an example of that is also included in the exercises, where we basically see a very basic variant of what Markus did. It's significantly reduced, but the impression is there. So what is important to keep in mind is I gave this at some point to the students, and I asked them to try it with the standard minimum method and once with the atomic min method. And they basically said, well, both of them are fine, right? So here's, I ran this actually twice, and here's both of them, ones with atomic on the left, ones without atomics on the right. First, second, and it takes really a keen eye to see the differences here. But luckily, we have the ability to scale up, and then things become a lot more clearly, right? So that's especially when you try to convey the importance of correct ordering on the GPU. Again, it is often so that if you're doing it incorrectly, the differences can be very subtle, but they are definitely there, especially if you maybe apply your knowledge from the previous graphics session and do a runtime real-time renderer where you keep rendering this image over and over and over, and then suddenly you will see the differences like crazy, right? So that might be a nice task that you might want to do if you're going through these exercises later. Okay, so another example where we can use atomics is, for instance, for the propagation of gradients. So this is from our recent, or basically to appear or to be presented SIGGRAPH paper, where we had the idea, or where we had the approach of taking multiple Gaussian splats. So again, this is sort of coming from the same direction as was Markus Schütz had been doing with his point-based rendering, where we're taking Gaussian splats and blend them basically together, alpha composite them back to front. And in order to do this, we basically need to do, in order to end up with the scene that we see here, of course, this is not given to us from the start. That would not be a very good paper. But we are given some sort of rough approximation of primitives and start from those, and then optimize the primitives into the position so that it hopefully almost looks photoreal, right? And the way that you do this is by using a differentiable renderer. So that means in a differentiable renderer, at some point you need to compute from the loss the gradients to update all your individual attributes of your primitives, which we did here as well. Our primitives are Gaussians. So when we render, and when we render differentiably, and when we want to propagate back the error, we have the individual Gaussians that contributed to each individual pixel. And because we are doing actual alpha blending, the order is important. And that has a few, for us, I would say, complex implications, which I'm not going to go into in very much detail. But the important part to take care of here, or to remember here, is we have only the budget to run through these Gaussians for a particular pixel once, like not a very high number of times. We can run through them maybe once if we want to stay efficient, right? So we need to basically settle on a way, how do we want to propagate those gradients? How do we want to take the error and propagate it back to the individual primitives if we can only visit each Gaussian once per pixel that it overlaps? And the way that we do it is by basically computing for each individual pixel a portion of the total gradient, namely the corresponding portion of the gradient that each individual pixel is responsible for, and then they all need to get added up. How can we add them up? Of course, if we have the availability of atomics, we can use atomic adds, and this is in this case, for instance, exactly what we do, right? From each individual pixel, each of them contributing a small gradient or part of the complete gradient back to the attributes of the Gaussian. They all get atomically added back up, and that is how they get propagated back. Okay, I'm trying to maybe accelerate a little bit here. So do we need more examples on atomics? Yeah, maybe. So I think, given that you all have some sort of compute background, maybe someone can immediately blurt out what is wrong with this shader. We want to do an atomic reduction. Why doesn't this work? Oh, sorry. No, wrong answer. Actually, this does work. Sorry, it's just bad. Okay, so this is not a good application of the GPU because, yes, it works, but the way we are doing it here, that's not a great way of exploiting your GPU for doing a basic job like taking all the entries of an array and adding them together. Okay, what would be a what would be a very straightforward improvement to this kind of approach? What can one suggest? Right, okay, sure. That was even one step further than I was going for. I was just going for using the additional shared memory that we have available in your compute. So basically, starting first with an atomic shared into shared memory, and then using that in order to update a global atomic, right? So that's skipping one step. Now the question is, this is now faster, right? So we exploited shared memory on the GPU, but now it's wrong. Can you also give the straight explanation of why the result is wrong? Yes. At which point?
The if statement. So before the if statement.
Okay, is that the only place?
Oh yeah, no, sorry, and also yeah, on both sides of the atomic add in shared memory. So first it needs to be set to 0, then the thread can start adding to it. Then you need another synchronization so the first thread can read the result and then write it out to global memory.
Okay, so this new version is wrong. It doesn't work. It's being smarter, it's faster, but it's also wrong. And that is because exactly we have been implementing arrays here, right? There's a read after write hazard here, and there's a read after write hazard here in both places, basically. So this is the difference. Again, I'm sort of preaching to the choir here with all your compute knowledge, but this is something that maybe for those who don't know that much about compute is often worth revisiting. If you have your experience of thread-safe, multi-threaded programming from the CPU, you have been working with a very forgiving architecture comparably, right? You usually have maybe dozens of threads on the CPU, and the x86 model is usually quite forgiving when you write data races or don't synchronize your accesses properly, and the GPU, that is really not the case, right? So, but this might be fun. This is could be interesting so that I can get a bit more of an overview. So maybe again a short show of hands. Who knows the concept and how to apply memory fences? Okay, awesome. Who is comfortable explaining the difference between release and acquire atomics? Okay, cool. Right, yeah, okay. Anybody out there who can explain and reason about out of thin air values? Okay, good, interesting, yeah. So these are all super fun, right? And when you write for multi-threaded programs, all of these things pop up and all of those become potential danger, right? And as I said, the x86 architecture will usually kind of look away and accept if you don't use these things correctly, but the GPU does not, right? So the good thing about Vulkan, and this is one of its standalone points, is that in contrast to previous GPU APIs, it actually goes through the effort of defining a clear memory consistency model for you, right? So the Vulkan specification includes a clear C++11 style memory consistency model, which can, for instance, also do release acquire atomics, which is actually great for those who do not want to use more synchronization effort than they need to. And also it clearly and specifically forbids values out of thin air, right? So if you don't know about them, you can safely continue to ignore them, right? Because in Vulkan they don't happen. So that's good news for you, okay? Good, so if you are maybe fuzzy on these concepts, I think that for anybody who's doing multi-threaded programming, looking these things up is quite important because at some point they may creep up again. So if you're fuzzy on release, acquire semantics and atomics, I could highly recommend some very, very helpful resources that I found to be super informative on these kinds of things and really gave me an appreciation of why architectures need a particular memory consistency model. That would be Anthony Williams' fantastic book, C++ Concurrency in Action, and then also Herb Sutter's talk on atomic weapons. Okay. So the solution was already given by our colleague over yonder, which was that we have to apply a barrier. In terms of Vulkan lingo, a barrier is both an availability and a visibility operation. which means that not only does it make information or data available to others, but it also informs a certain group of others that this information is actually available and that their information might be outdated, okay? So that in Vulkan terms is an availability operation followed by a visibility operation with the scope, in the case of a barrier, of the entire work group, right? So that means the fix to the problem that we saw before, as was stated to us already correctly, was to protect this atomic axis in the middle here with a barrier. And now actually we get our, this actually includes the wrong times. I'm sorry, it should say 16 milliseconds. And now the values are actually also correct. Okay, I'm gonna skip the example of staging because it's actually part of the exercises if you're interested in knowing more about it. I want to quickly mention that we talked quite a bit about synchronization today. We said there are many ways to do it, and I just did as well. And I think there's an important difference between synchronization for correctness and synchronization for performance. So in the previous case, we saw a synchronization for correctness, right? Without it, we wouldn't have gotten the correct result. I think that's really, really important, no matter where you're coming from when you're trying to program your GPU. When it comes to performance, I'm willing to bet that in many, many applications that you do, especially if you are maybe coming in from the machine learning community, you might not need those fine-grained synchronization mechanisms until you're ready to use them, right? So synchronization, if you are able to invest some sort of time, is always and in many ways possible by simplifying your program and using those wooden mallets that we talked about, like for instance, device wait idle, right? So synchronization doesn't have to be complex. Minimum overhead synchronization is more involved and requires you to have some understanding of the basics. But the good news is that in many applications, especially if you are in the machine learning community, and I'm I'm hoping not to generalize here, or but then usually you don't care about those kinds of benefits that you get from really minimum overhead synchronization. Most likely your time is spent somewhere else. Okay, so what I'm saying is basically pick your battles. So if you really have the job of writing a job that is, or writing an application that is efficient, make sure that you don't do the mistake that many people do when they first go into compute programming and trying to use it to do something efficiently, and that is over-optimizing maybe the kernel that you just wrote, or the dispatch job, or the compute job that you just wrote. Always go ahead and find out what is actually the part of your program that is slowing you down, and then go ahead and treat that, right? That will save you a ton of time. So I think, yeah, there's also, yeah, especially for Vulkan, quick shout out to RenderDoc, which is a very useful tool for debugging. Again, if you go through the exercises, there is included a setup for you to use it to do some basic debugging of your code. The video is unfortunately not playing in this slideshow. That's a shame, but, oh, maybe now it is. Okay, so, yes, no, maybe? Nope, it's not coming. Okay, maybe I can, I can deliver it at some later point in time. All right, so, now it is. Okay, sure. Basically gives you the ability to launch your job, capture what is happening on the GPU, and then basically go through a replay of what happened in an emulated shader, basically in a shader emulator, right? And recently that emulator also includes compute. So if we ran some compute pipeline, we can actually pick a thread in our setup, and then we can step through it and see what kind of changes it went through, which is super nice, super helpful, very portable, but keep in mind this is an emulation, right? So it's nice to get you started, and it's as far as we are in terms of portable debugging in Vulkan, but it's not the entire shebang. It's not a real full-fledged debugger, but it's a very good start. There are some challenges for Vulkan in compute still. I'm going to skip over them because I think I'm already over time. If you feel like it, I'm sure you will find these issues at some point for yourself. Something that I would like to highlight, because I would be very happy to see it, would be if we could get maybe similar support in terms of functionalities and libraries that we are seeing with other APIs, right? We know that the performance of Vulkan, even and especially given its portability, can be as high and sometimes higher than really optimized CUDA libraries, which was, for instance, shown at Vulkanized by the author of VKFFT. Unfortunately, I don't remember his name, but you can easily look it up. So we know that there is a large potential, especially given the portability of Vulkan, to have libraries that are fast and could potentially run anywhere. And it's mostly a question of the community and people who would be invested or interested of taking things like BLAS libraries, sorting libraries, and making an approachable and battle-tested version that really runs in Vulkan, which would give a great boost to using these kinds of features on all kinds of platforms. Okay. So this brings me to the end. I'm sorry that I pretty much filled out the time. If you have any questions, please approach me afterwards. In general, we need to say thanks to all those who were involved in the process of developing the material for this tutorial here today, from our fellows at TU Wien up to those who started the initial journey of CUDA and GPU teaching at TU Graz. And of course, High Performance Graphics as a venue, who has been super nice in organizing and welcoming us. And they really did quite a job on setting all this up with high quality presentation methods, techniques, mics, like I tip my hat to you. And then of course the Chronoscope and its community, including particularly Tim Lewis, who is always there to communicate and make sure people exchange information and setting up relations between those who might be willing to promote more info and interest about Vulkan. And yeah, that's pretty much it. If you have any questions and they are quick, please go ahead if you think they might interest others. Otherwise, feel free to approach me afterwards. Thanks.
Well, thank you very much, Bernard. Thank you very much, Lucas, for these amazing talks. Amazing show. I think since we are on time for the break now, maybe if you want to make questions, you can stay here for a while and I'm pretty sure they will appreciate your answer. Sure. But we are we're on time for the break now, and so that's me works. Okay, thank you very much again.
Hello, everybody. Welcome back. Thank you for coming to HPG again. The first day is coming to its close. We have a reception in the town hall, the real town hall, down the road at 6:30. But first, we have our final session. I'm very proud to introduce and bring to the stage JB, as I know him, or Jan. I can't do the Dutch pronunciation; it's too hard. Jan Bart van Beek, something like that. And JB, if you don't know him, he's a legend amongst video game designers. He's the studio director and art director of Guerrilla, formerly Guerrilla Games, but I think they're now so big they're just Guerrilla. And they are perhaps the premier game development studio in the Netherlands. They're particularly known for Killzone, and then after Killzone they've had a series of smash hits with Horizon. And a little tidbit about Horizon is I believe that there was a sort of pitching process within Guerrilla to find their next game after Killzone, and JB is the sort of the progenitor and daddy of Horizon. So he's one of the most technical art directors I've ever met. And what I thought would be interesting after this morning's session, where we're hearing about like if you like, different ways of learning, different ways of applying high-performance graphics techniques, I thought it would be interesting to invite a speaker who looks at high performance from a different perspective. So although JB can probably write the best shaders with the best of us, he's also someone who can zoom out and look at the big picture of a complete game. So in fact, that's what I will invite you to do for this talk, is kind of relax. I'm sorry, JB, I didn't get you a sofa with a roaring fire and a whiskey, but I actually think it's really important to see our work as researchers, as academics, and in industry as well, in the context that it's going to go to. So when you write a paper, who's at fore, and actually many of the Guerrilla technical team are here to throw peanuts at JB, but research has to have an application, and I think that JB's here to talk about some disruptive ways to think about HPG. So thank you very much, JB.
Thank you very much. So hello everybody. I'm very honored to talk here today. It's also a little bit terrifying. I heard there are over 100,000 people maybe watching this on YouTube, which is really terrifying. But also, you know, computer graphics engineers are my favorite kind of people. I honestly think that you guys are absolute rock stars. But I myself, I'm not an engineer or a computer scientist. I can program a little bit. I can even throw a shader together if you put a gun against my head. But that's about it. So what I'm going to do today, talking to you here, is I'm going to talk about disruptive creativity. Now, who am I to think that I know anything about that? As Alex says, I'm the studio art director as well as the studio head at Guerrilla Games. And you may remember us from games like Killzone, or more recently, the Horizon game franchise. And my job is to design interesting worlds to explore, which in my mind is one of the coolest jobs to have as a job. And frankly, I owe that job to the people in this room. And I mean that quite literally, because some of those people are here in the room that I work with. So here's the super short version of how we come up with games and movies. We put a whole bunch of creative types, like artists and animators and designers and writers in a room, or more likely a bar. So here's a mid-journey recreation of that event. This is pretty much exactly like it is, as obviously we also like to cosplay during design meetings. So we chat for hours, days, weeks, sometimes even years, and a big entertaining idea comes out of it. It's a world full of characters and stories and monsters and adventures. And we can come up with these ideas without any high-tech tools. A pen helps, and maybe some napkins or a beer mat. But then the really hard work starts. The really hard work of making that idea a reality. Because often we first need to build the thing that builds the thing. A lot of what allows us to make a game or a movie are the high-tech systems that allow us to turn an idea into a working piece of software, or a movie script into thousands of meticulously rendered frames of a feature film production. And that's really hard work. And so as creative types, we gladly hand that over to you, the engineers. Now, computer graphics are a symbiotic relationship between the arts and technology. More so than ever before in history have such different skill sets been so complementary in the creation of entertainment. In my own experience, when it works really well, it has been a highly collaborative relationship in which both sides inspire each other to engage in creative problem solving. Usually to get around the limits of technology that exist at the time in order to deliver a new type of experience that we hope will delight and excite our audience. Without computer graphics, and the engineers who dedicate their careers to it, almost every single entertainment franchise in the world, from GTA and Call of Duty, from The Matrix to Lord of the Rings, from Star Wars to Avatar, none of those things would exist. And without Midjourney, this bunch wouldn't exist. And really, what the heck is up making with Darth Vader up there? Anyway, Killzone wouldn't exist, Horizon wouldn't exist, my job, most of our jobs here wouldn't exist. And so with that said, this should come as no surprise. I'm going to argue that CGI is the most important innovation and the most disruptive one in entertainment in the last 40 years. As I said, without it, video games would not have been possible, as CGI is their fundamental ingredient since we moved on from text adventures. And of course, the development of CGI over the last 40 years or so has fundamentally changed cinema and in recent years, TV as well. Now, don't get me wrong, practical effects, or analog effects, as some call them, in movies are also pretty cool. I love it when a really good practical model is used, and the simple fact that an actor can interact with it makes practical effects incredibly believable. But that does not take away from the fact that many of our favorite movies from the last 2 decades would not have been possible with CGI, without CGI. And it's really given a boost to the movie industry in general. Now, there are also plenty of film lovers that are not big fans of the popularity of these CGI extravaganzas, full of all kinds of amazing special effects. You might even, like Martin Scorsese, argue that the glut of Marvel movies had made it harder for more classic forms of cinema to find an audience. But movies are entertainment, and games are as well, and entertainment is supposed to entertain an audience. And the audience that goes to the movies or plays games are mostly younger people, and 2023 kids are simply less enthralled by stories of gangsters that lived close to a century ago. Entertainment doesn't just change because the audience changes, it also changes because the creators change. I myself come from a generation of game developers who have always worked on 3D console games. I've never worked on 8-bit or 16-bit generation games or 2D sprite-based games in general. My first shipped game was a PlayStation 2 game, and AAA video games have been my medium for all of my career. And the modern CGI spectacle movie is a medium of its own. It's a medium that was pioneered by a generation of directors who are now in their late 60s or even older. Pioneers like James Cameron, George Lucas, and Steven Spielberg. They changed the way that we think about movies. Jurassic Park is now 30 years old, and its CGI dinosaurs still hold up, which is a testament to the directors, the special effects artists, and engineers who worked on that movie. But there is a younger generation of filmmakers, such as Tim Miller, James Gunn, and Neil Blomkamp, younger, as in they're in their 50s, for whom CGI has been their primary medium. They are all great filmmakers, but imagine them as the director of 1959 Ben-Hur, where every set is physical and every stunt is done by real people, and you have a cast of thousands. Handling a film set like that is a very specific and very hard to obtain skill set. And it can be argued that freeing a generation of filmmakers from the burden of learning how to run such a complicated film set allowed them to dream beyond what is practically possible. I personally feel that, although CGI might still be expensive, it also allowed for new stories to be told by a generation of filmmakers who are allowed to dream up bigger and stranger worlds. And that trend is still continuing. The technology and the skills to create new worlds are becoming ever more accessible to a larger group of creators. Students are using game engines that they can download for free. And with a couple of years of training and watching a whole bunch of YouTube movies, they can build worlds that could have only been created by very large, well-funded development teams just a few years ago. So the movie you see playing was made by Taichi Kobayashi, who is a graduate student from Japan, and he made this all by himself in Unreal over an 8-month period. Similarly, readily available animation and rendering tools like Blender allow artists and filmmakers to play around with their own filmmaking ideas without the need for a large budget. The footage on screen is from a young filmmaker called José, and he's making spectacular looking Star Wars fan movies on literally, and I mean literally, a shoestring budget. And then there are game projects like Unrecord. It became an overnight hit a couple of months ago when they released a trailer of their demo. Built in Unreal by a small indie team who fearlessly pursued their own vision, and in doing so blew everybody's minds and challenged some of the largest development teams of the world to break new ground. Instead of mimicking the polished look of Hollywood action movie cinematography, they went for the raw look and feel of modern body cam footage. And created something that feels much more immersive and dynamic than most current-day modern big-budget first-person shooters. Our creative industries are at a critical point because of what is happening with our tools right now. I've heard people call it the democratization of content creation tools. Tools like Unity, Unreal, Blender, and even Roblox are extremely accessible, and they have large support communities of users that provide an incredible amount of support for people who want to learn these tools. You can almost say that making games has become so easy that an 8-year-old can do it, and in the case of Roblox, they actually do. So at some level, this is great. Accessible, affordable tools level the playing field for creators. For example, the development of accessible and affordable digital cameras made YouTube possible. And that changed the media landscape forever. It might actually be the greatest democratization of a medium ever. Today, you don't need a super well-funded studio to make something cool and exciting. Now, with that very boring slide, it's time to get back to the Mid-Journey slides. So it's great that new creators are able to enter the field. You see what I did there? It's people running into the field. So, and that will surely lead to a greater diversity and choice of video games. And that's great for gamers. More choice of games can also lead to greater competition. And it will be harder to stand out in that more crowded field. And in other creative industries, that often leads to a higher level of innovation, because it will be important to do something that is unique and original. But there's a flip side to the democratization as well, which is the standardization of these tools. There are many cases where standardization of tools makes perfect sense. Imagine that every nuts and bolts making company in the world would make their own unique sizes of nuts and bolts and matching wrenches and screwdrivers. The movie industry used to be a big mess like that. When it came to standards, every studio made their own cameras and even their own film formats. But the need to collaborate with other studios just made it impractical. These days, there is a limit to the amount of film formats and file formats, although there are still plenty of proprietary formats as well going on around in the movie industry. Now, of course, in software engineering, there are plenty of standards. There are quite a few programming languages, and there are new ones in development at any moment. But it would be insane if every software developer uses their own proprietary programming language. But when it gets to the tools of the games industry, that is the game engine and its matching editor, more than half of the developers in the industry create their own. They all tend to be highly unique and proprietary. So why is that? Well, let's start with the basics. A game engine is a highly specialized piece of software to make a highly specific other piece of software, a video game. And just as games can be very unique, the software that makes those games can sometimes also be very unique, because they are the result of a complex combination of balancing choices. For example, there is the balance between flexibility and performance. Unity, for example, is highly flexible and runs on almost any platform, but it's not going to have the fastest streaming system in the industry. So it's probably not the best choice if you want to make a high-speed open-world racing game. Unreal may have some awesome ray tracing features, but those may not be that valuable if you make retro 2D pixel art games. Every game engine is the result of a long discussion about the balance between feature richness and performance. And that is just one of literally hundreds, if not thousands, of discussions. Let me try to illustrate that by using the one game engine I know really well, and that's Decima. So who knows Decima? Let's have some hands in the air. Yeah, a little bit. Okay, for those who don't know Decima, that's okay. It's not as famous on Unreal, and it's also not as widely used as Unity. It's one of a dozen game engines that PlayStation Studio uses, and it's the only one actually that's used by multiple PlayStation teams. So is it any good? Well, I'd say so. Last April, it won the BAFTA for Best Technical Achievement, and it also won the Best in Show award at the SIGGRAPH Real-Time Live event last year. So needless to say, we're very proud of our game engine and the recognition it has gotten. But how did we get to this point, and where did it all start? Around 2011, we were finishing working on Killzone 3, and a small team started working on Horizon. Horizon was going to be our first open world game, and we had never built an open world game. And designing an open world game is very different from designing a game like Killzone. I've compared it in the past as a difference between designing a roller coaster, where every second is carefully designed to completely control a player's heartbeat, every heartbeat and emotion, compared to designing a theme park, where you can control the over experience through curating the selection of attractions and working on layout and flow, but you don't control the visitor's experience in the park on a minute-to-minute basis. They might start, for example, on the roller coaster and then go eat a taco, or the other way around, where they might have eaten 6 tacos and then do the roller coaster and then lose those 6 tacos. Because we had no experience designing theme parks, we hired a bunch of people who did know how to build open world games. People from Crytek, Bethesda, CD Projekt Red, Ubisoft, etc. And the first thing these people asked when they got into the company was, where is your editor? So, see, for Killzone we never used an editor. All our content creation, including level design, was done in Maya. We could build the game room by room, area by area, and string it all together to build a game. But you can't build an open world game like that in Maya. There's simply too much data and too much content. And Maya isn't designed around the concept of constantly loading new files around you in the world. But you need to do something like that to build an open world game. You need a very specialized tool. One that brings all the developers and content integrators, so programmers, artists, designers, animators, sound peoples, writers, etc., and give them a common tool set, a common language to create and express their ideas. Now, in my opinion, a game engine and its editor is so much more than just a tool. It's a philosophy. It's the manifestation of the desire of many different creative disciplines to collaborate. It combines the fields of art, animation, sound, music, acting, choreography, graphic design, cinema, and of course the magic sauce of video games, interactivity, into a world of collective artistic expression. Each game is a work of art, and each one is different and unique. And the same goes for game engines. They are the result of thousands of discussions to come to an understanding of how hundreds of people from dozens of different creative disciplines will work together to create a piece of interactive entertainment. Hundreds of unique viewpoints discussed in thousands of unique conversations, resulting in something just as unique as the game it can produce. And that's why every game engine is unique. There are probably several hundred game engines used in our industry. Out of the 15 studios at PlayStation, 11 have proprietary game engines. That's quite a lot, and it's not necessarily that typical. Ubisoft also has a handful of engines, and EA recently, for example, has moved all their development to a single engine, Frostbite. And of course, Unreal is becoming an more common solution, with Epic claiming that 50% of all announced AAA titles are now made on Unreal. But even though there are hundreds of game engines, they are an endangered species, because slowly but surely they are becoming increasingly rare. And there's a couple of reasons for this. First of all, building a game engine from scratch is insanely labor intensive. It takes many years, probably close to a decade if you start from scratch. So almost no one does that. Almost no one makes a new game engine. And if you are starting a studio right now, you most likely will choose Unreal or Unity. Second, the cost of maintaining and updating your own game engines is also very high. It requires the top engineers of our industry, and those are in very high demand. So less and less studios are able to support that effort. And that means that the older studios that have their own engine and they close down or switch to Unreal, every time they do that, there is one less engine in the world. And if one disappears, it almost never comes back. And with this decline in diversity of engines, we're seeing a monopolistic nature appearing. As you probably know, monopolies don't innovate. It's very expensive to be innovative, so it's easier way to compete in such a marketplace to buy up your competitors or make them go out of business. This is a pattern we've seen time and time again with software tool makers. Once all competition is gone, the innovation stops as well. I'm going to come back to the importance of competition and innovation later, because first I want to reflect a little bit on the history and the future of CGI. This is Don Greenberg, and he's one of the earlier pioneers of computer graphics, together with a whole bunch of other people that still have algorithms and formulas named after them. Catmull-Clark, Lambert, Blin, Fong, Cook, Torrance, or Meyer. Don Greenberg and his team came up with the Cornell box, the first ground truth test. Don is now 89 years old, and he's still a professor at Cornell, and he's still doing computer graphics. He's fully into really high-end VR, and he was working a lot on foveated rendering a couple of years ago. There's an enormous amount of energy there. That's just mind-blowing. And I'm lucky enough to meet him every couple of years as we both regularly visit the same conference. So a couple of years back, we were watching a presentation from Pixar on Coco. There's this shot in there where we are shown the City of the Dead for the first time. It's this great, lovingly crafted shot. And Daniela Feinberg, who was the lighting director on Coco, was explaining how this shot took 1,000 hours to render. Don, who really wants to see these kind of worlds in VR in real time, turned to me and said, that means we need computers that are 100 million times faster. And I joked to him, well, Pixar should probably optimize their scene a little bit first. But it made me realize something, I guess, that I already knew. You know, that super high-end, perfectly photoreal VR, it's simply inevitable. It's inevitable because it's been the course of computer graphics engineering for 50 or 40 years. Every super smart, highly optimized approximation we come up with will at some point become obsolete as the cost of compute becomes less and less of a concern. Phong, the guy that I mentioned, that came up with the Phong shading model, once said, we do not expect to be able to display the object exactly as it would appear in reality, with texture, overcast shadows, etc. We only hope to display an image that approximates the real object closely enough to provide a certain degree of realism. Yep, so tell that to Digital Foundry. I think we've moved on from that expectation. I actually argue that any approximation at that point is a temporary hack. There is certainly work to be done to get photorealistic real-time rendering, for sure. It may seem hard, but only in the context of temporary insufficient compute power. We've pretty much already solved every rendering calculation for offline rendering at this point. You know, when Toy Story was made in 1995, it took several hours per frame to render this image. And now any decent PC can render it in real time. So it might take a couple of decades, but that 1,000-hour frame in Coco or that 1,000-hour frame from Avatar will be, at some point in the future, be rendering at 8K resolution, stereoscopic at 250 frames a second. Now, lots of software engineering can help speed that up, but as hardware gets faster, it will inevitably happen anyway. And of course, there's currently still a lot of skill involved in making a photoreal character or scene. True, but for how long? Because making photoreal images is actually really simple. Everyone with a camera in their pocket, and people produce billions of photoreal images every day. And if I'm looking at advances in neural radiance fields, it seems that we're not that far away from making a photoreal VR scene a really very easy task. Soon these tools and techniques that were only accessible for big, well-funded entertainment companies will become available to everyone. And like photography or cinematography, it will of course produce great works of art, but the vast majority of it will be very mundane. Just like the vast majority of photography is very mundane. So that's going to be my hill for today. The mathematical equations to approximate ground truth take creativity, but defining what ground truth is isn't a creative process in itself. Real-time photorealistic rendering may seem hard, but it's inevitable and not very interesting. For those that are in full disagreement, I will be available after this talk to be punched in the face. So what do I think is worth our collective time? Well, for me, it's about doing something different. Doing something different is very, very hard. And it often takes a very, very long time. That first Toy Story, that was something different. The first feature-length 3D animated movie. And to some degree, it was the birth, or perhaps the rebirth of an art form. But there are more moments like that. Tangled was Disney's most expensive animation movie ever. It still is. It's estimated to have cost around $260 million to make, or $350 million in today's dollars. And it may not look that special now here in 2023, but it was released in 2010. And it was Disney's first full CGI animated feature film. And it took them 9 years to make that movie. They may remember that Toy Story 3 was actually released in the same year. So why did it take Disney so long to make Tangled? Well, Pixar had made a couple of very smart choices. They made their movies mostly about toys, or bugs, or fish, or monsters, or cars. Because doing human characters was very hard. Before 2010, the only movie to feature human characters was The Incredibles. But Disney couldn't really do that, because Disney stories are generally about human characters, or more specifically, human princesses. I don't think you were expecting a slide with Disney princesses today. So the hand-animated 2D movies from Disney have a very unique visual style, and a very expressive but believable animation style as well. It's clearly a quality that they wanted to maintain, but staying with 2D simply wasn't an option. The market had become very used to CG feature animation, and this needed to shift their paradigm if they wanted to stay relevant. And this paradigm shift of taking their classic fairy tale stories and translating that to 3D animation was one of the most difficult and costly projects in the history of Disney animation. It took them close to a decade to develop their own very unique, non-photorealistic look. Everything from skin, eyes, hair, cloth teeth, everything needed its own unique solution. And so here's a comparison between Tangled and Toy Story 3 Wiki that are from the same year. You see quite a big delta there in visual style and texturing and just look development. To set a new visual style for an animated creature it took them over a decade almost to do this. To such a point now, basically, that the Disney style has now become the mainstream look. But no success lasts forever. What cost Disney a decade to do was inevitably copied, made faster, made more efficient, made easier, made cheaper, made more common, and made less interesting. Animated features were in danger of losing their captivating appeal. The novelty had worn off. And then in 2018, a new paradigm shift happened. Spider-Man Into the Spider-Verse broke all the molds. A couple of wild minds at Sony Picture Animation wanted to reimagine what animation could look like. For them, the look that Pixar and Disney pioneered and developed had become a straitjacket, something that felt standardized. The innovation in rendering look and the animation techniques that had started to slow down. These animated features used to be the forefront of pioneering new techniques that had never been tried before. But from a perspective of moving the art and technology forward, what was really that new or exciting about Finding Dory or Frozen 2? So they envisioned something completely different for Into the Spider-Verse. They pioneered a look that wasn't based on photorealism or physically based lighting models, but one that was based around the concept of making a comic book come to life. And it found an audience who was extremely excited by that. It was the first non-Disney, non-Pixar movie to win the Oscar since 2011. The second Spider-Verse movie has just come out a couple of weeks ago, and for those who haven't seen it yet, go and see it right now. And I mean that, basically just walk out and go see that movie instead. It surpasses the original in almost every way, and it's a big milestone for the animation industry. I would not bet against it at the Oscars this year. But what is my point here? I think as an industry, there is a tendency to work on the inevitable. Problems that may seem hard, but will actually solve themselves without much effort, as the amount of available compute increases. Photorealism is such a problem. As I mentioned, pretty much all problems in relation to it have already been solved in offline rendering. And while we wait for graphics cards that can easily run those offline computations in real time, we can put a lot of effort into finding temporary hacks that speed it up. There's still a lot of value in that, of course. Sometimes being the first to do something in real time that was never done before allows the creation of entirely new experiences. Valve is a great example of such engineering-driven game development, where both Half-Life 2 as well as Portal delivered entirely new gameplay experiences through its gravity and then its portal gun. But I don't really see real-time ray tracing being such an innovation to video games, except for making things look just a little bit better. There's similarly a lot of work being put into making the costly thing, either in terms of time, talent, or money, more accessible. Scanning the faces that we use for Horizon is a process that costs tens of thousands of dollars per character. So technology like meta-humans is incredibly helpful to make lifelike CG humans more accessible for developers that do not have access to those sorts of funds. I honestly think Epic has done amazing work here to make the tools of game production more accessible to a larger group of people. It has an incredibly democratizing effect. But there's a flip side to this as well. Making it easy and cost-effective also means it makes it something that was once a really rare sweet treat as mundane as bread. It loses impact. And that is a problem with the standardization of our tools. They inevitably become more optimized to do the work that is unavoidable. If the whole world is expecting photoreal games, then the mainstream tools will become really good at delivering that. Creative innovation or disruption, like that of Toy Story, Tangled, or Into the Spider-Verse, often requires such a paradigm shift that existing tools and techniques won't be suitable to deliver on that creative vision. These kinds of innovations require a new way of thinking and talking about what we're trying to make. And that leads to new insights and discussion with the engineer who we depend upon to build the systems and tools that make it all possible. I mentioned before that a game engine is the result of thousands of unique conversations, which result in a unique outcome. Every game and every game engine is unique. And to make something truly innovative, you often also need truly innovative tools. A great example of this is the Dream Engine, the brainchild of Alex Evans, the man I was honored enough to be invited here to talk today. Dreams is a very unique tool that allows the creation of very unique experiences. But with Media Molecule ending its support for that unique tool this September, we see again how easy it is to lose game engines and see them disappear. As an industry, we need to find a balance here. Yes, it's important to democratize the tools, the means of game production, but we need to make sure that aspiring young developers with big dreams have access to great tools that allow them to achieve success without the need for millions of dollars of funding. As I said, I feel this helps innovation and competition, as developers with different ideas can make their games or their movies and find an audience for them. But it's equally important to make sure the tools don't become monolithic and standardized in such a way that they become ever more restrictive or even prescriptive in what types of games can be made. And to do this, we need creative visions that challenge the mainstream approach, that try to do something so unique that it needs a unique set of tools to make it. Alex asked me to tell you what the creative community, so the artists, the animators, the designers, etc., really need from you, the engineers, that create the tools and the technology that make our creative visions become a reality. So I have two requests. So first off, I feel there is a paradigm shift on its way in game development. We're in a phase where real innovation is at a low point. We're mostly seeing an increase in production values or novel business models, but relatively low investment in new experiences. And this means that our industry is ripe for a major disruption by someone that is willing to take risks and think outside of the box. These are big seismic paradigm shifts, and they will need a large collaborative team effort. I mentioned that game engines are the results of thousands of unique conversations, and there are going to be a lot of new conversations coming. It may be time to kill some darlings, and it may be even time to throw out a lot of babies with the bathwater. So avoid getting too comfortable. Thankfully, the second request is a little bit less scary. It's a little bit more smaller scale, because sometimes something small can make a big change. What we want to see is your weird-ass personal coding projects. They can be ambitious or audacious, or they can be small and cute. But show us your weird tools and toys that you've been working away in secret. The artists, writers, and animators, designers, and audio people in this industry absolutely love new weird tech, and it inspired us. Tools like Alex Dreams or Inigo Quiles Quill Tool are passion projects that were made by a small team or even a single person. Tools that allow whole new ideas to be expressed, or stories or worlds that were never possible before. The work you see on the screen here is by an artist called Alex Stephen Martin. And he was already an amazing illustrator, but a tool like Quill allows him to turn his illustrations into amazing immersive storytelling pieces. Without a weird tool like Quill, this wouldn't have existed. And so that's my ask for you today. Go and build something weird. Thank you.
Thank you so much, JB. Listening to that, I sort of think of it as you're granting us permission to go and do weird stuff. And
go do weird stuff.
This is the top-down view, and I think our job is to figure out the papers, the bottom-up perspective of how we allow JB to build the weird stuff from the individual pieces that we're building. You know, we're focused on milliseconds, we're focused on kilobytes and how fast we can render this or how well we can approximate that. But we're being given permission effectively to try some stranger things, and I think that would be very cool. So we have time for questions. We have to be out at past, but that gives us plenty of time to talk to JB. So has anyone got any questions? I've got the cube of destiny. It's a quiet. Oh, we've got one in the middle. I'm not going to throw it. I'm too mark coordinated. Right, thank you.
My question is related to Dreams. I mean, it's a super great game, but why is it stuck on PS4? Like if it comes out for PC or something, then it would explode.
The question would be for JB, but I no longer work there, so I don't know.
Okay.
Short answer.
Is it what is it, the question was about dreams? Oh, I don't know. Like, he knows better. I don't work with media molecule.
Yeah. Okay.
Yeah, in today's age of artificial intelligence with rising technologies like ChatGPT taking away the jobs of artists or programmers who might enjoy their work in CGI, what measures should we put in place so that we balance the passions of the people working on these projects and also the outcome of these projects? The outcome in terms of the quality of what we're trying to build.
I don't know. I'm not a legal expert. The way that I look at AI is that it is something that first of all needs a level of consent. If you're going to be training a model on data, then people who participated or lent their data need to be asked for consent whether their data can be used like that. And I think that's a really important aspect that's currently being overseen by a lot of the companies that are racing to market here. I think there is not only a legal discussion to be had, but also an ethical discussion that we need to have as programmers and artists and creators in the entire industry on how we want to deal with this. I think that is a very large discussion. I'm not the one to answer that. I certainly have my views on it, but I'll keep those to myself right now.
Well, thank you for your talk first. I would like to ask, could you maybe share a little bit of your experience on how designers and engineers and artists and engineers, how communication between those two groups goes? For example, as a game designer, you come up with this really crazy out there idea and you're all sitting at a table with a couple of beers and thinking, yeah, let's do this. And then you show it to the engineers and they all get scared.
The engineers come in all sorts of shapes as well. Some want to see a paper design that covers every edge case in existence. That is almost never possible. I think if you're a programmer and you're good at prototyping, then you're usually aren't that scared of that. You kind of love the iterative process of working with a designer directly. But if you're making something that is going to be, a 3-year project, very specific to a single feature, then you probably want to have a really good think about what you're doing ahead of time. So it's all dependent on what you're doing. In general, there are programmers that work really well with designers. There are programmers that work really good with artists. As I said, it's different skill sets on how that works with communication and collaboration.
Thank you.
Good one. Okay, thanks for the talk. Thanks for the throw. So you were talking about the death of game engines. So my question is, so for example in Horizon, what does it have that you could not do, for example, with Unreal or some of these big game engines? I'm not making any publicity here. Just
well, it's frankly still very hard to do a very large open world streaming game in Unreal. I've never worked with Unreal, but from the people that have tried to do that, they certainly thought that was challenging. Unreal does with a whole bunch of things extremely well, but making open world games is still not one of its strengths.
Okay.
Yeah, I was curious when you were, you started Killzone, and it's a completely different game. How was the process of going from a game in terms of tech and your vision? Like, you have never made an open world game like Horizon. How did you get to that point where you feel my vision can be completed and you see it's feasible to do? Because obviously it's an idea has to be turned into something that has to be real in the end. How did you manage that process?
That was first of all a very technical process. I think we looked very carefully at what was out there in terms of available tools. This was a point where you could actually download the creation engine from Fallout, for example. CD Projekt Red had given access to their tools for modding. And actually looking at those tools and picking apart how they worked talking to the people that worked at those companies and explaining what their workflows was. It was a very large part of understanding the tools that are needed to make an experience like that. But beyond that, of course, there's also a giant mind shift that happens when you go to a different model like that. The designers that worked on Killzone really understood their sort of like corridor shooter structure on how to control every aspect of the experience, and going to an open world game where people might come to your quests with whatever weapon loadout or from any direction or wherever point in the game. Was for them a very big challenge to think about that and sort of wrap that into their design experience.
Thank you.
I kind of wanted it thrown. That's okay. Thank you for the talk. I was a little bit thinking about your discussion about how we're ripe for innovation right now in the game industry. And I'm kind of wondering what advice you would give for individuals who are maybe a bit are looking at the innovation that is happening, but they're scared because the innovation can tend to be faced with failure or with not as much promotion. Like Into the Spider-Verse is very popular, but it might be very terrifying for people to innovate when they realize that they might just be faced with failure in that space. And I wonder if you have any thoughts on that.
Failure is great. Failure makes you learn from your mistakes and then try again and do better. I think that to some degree, having a hit right out of the gate is actually maybe sort of limiting for a company or a development team, because then they're a one-hit wonder and they're going to do that forever and ever. Having to done projects and see projects fail, I think makes you a more hardened, experienced dev. That is also more flexible when they're thinking about problem solving and what to come up with next.
Thank you.
How important is it for game studios to really work closely with hardware vendors? Maybe an example like Unreal Engine worked with Microsoft to get this render graph.
A little bit closer to the microphone.
Sorry. How important is it for game studios to work closely with hardware vendors or API companies that make the APIs? Because, for instance, Unreal Engine or Unreal recently developed together with Microsoft this render graph feature for DirectX 12. And is innovation kind of connected to having access to this vendor-specific things?
I don't think we use a lot of middleware anymore. Maybe you can throw the microphone to Jeroen and he can answer that question. Jeroen, could you answer that question?
What was the question again? Sorry.
How important is it for game studios to work closely with hardware vendors? For instance, we do work Sony with maybe, and
yeah, well, obviously Sony works with hardware vendors because you use some hardware, obviously from other factories and things like that. So, and we do work with teams from AMD and NVIDIA, and sometimes also with Microsoft. But it's hard to get like things worked out from the ground up, if you know what I mean. So we chat regularly about conceptually where we're going, what we think is important, and we get feedback from them. So I think it's a collaborative effort that we can't demand anything really. We can say, well, this is what the direction we're thinking in.
So you don't get backdoors or something like that for
no, absolutely not. No, there's certain like driver level things that we can't control that sometimes is done by the maintainers of the drivers, that they do for particular games or they do for all games if they can, but we don't have any say in that. So.
And I mean, I'm asking especially because like integrating AI into rendering is always a bit hacky as it is right now, and there are not really these interfaces established to do this kind of things. So in such a case, it maybe would have to work with hardware vendors, or just a thought.
Yeah, I don't. I'm not working on that right now, so I wouldn't know how to answer that really.
Okay, thanks.
Yeah.
Could you share more on what you kind of needed to justify to basically branch out and write out your own thing, like making the case to business, for example, because then you needed to hire a lot more engineers. So what did you need to sort of prove to the higher up upper management that sort of we need to make our own engine to make this game?
So we had always made our own engine, so that was our starting point. So that it's different. I think pretty much every studio that came to Sony came in there with their own engine. Some switched engines over time. That happens as well. But if you look at sort of like the larger studios like Naughty Dog, they have their own engine technology. Santa Monica have their own engine technology. Insomniac has their own engine technology. We have a lot of different engines at PlayStation.
You had a couple of references. You had a couple of references to like neural or AI rendering technology there. Have you seen any sort of tools that make authoring AI or neural materials or stuff that's good for artists, or do you think work needs to be done in that area, or how do you see that developing?
So things are in a very early stage. Right now, the sort of policy is to not really engage with these tools yet, till the larger discussion has sort of been had, on the ethical and sort of legal and moral implications of the tools. People are certainly experimenting with them in their free time, but it is way too early to start using these tools in production.
I think that's it. So please everyone join me in thanking JB for his fantastic talk. So now we just have a little bit of time. I guess we'll see you at the reception at the town hall. David, did you want to say anything to wrap up, or see you at the reception? Thanks very much, everybody.
All right. Yeah, should we kill?